Check, check, check. 1, 2. Double check, check. 1, 2. Third check because random. Say what?
Sounds great.
Thank you. Check, check, check. 1, 2. Other catch box, Mike. Check 1. Check 2. Check 100. feedback. Cool.
Hello? Hello? Can I able to, am I audible? Okay, thanks. Okay. I think I'm audible to everyone. Yeah. Um, my name is Jagan, and today I'm going to talk about DRM Bridge API to standardize for writing a DRM drivers. This is a specific talk that is rather than a proposal. Something like there are DRM drivers in the Linux kernel, so they are well stable since from years. So since these are typical video drivers, there is much enhancement to need to give to propose or something like that because it's a enhanced stack that has some fixes and enhancements. But this particular talk will underlying some changes with respect to the DRM drivers by introducing some APIs to make them as standard, so that even for even the new drivers who are willing to write on the DRM can might change if you follow something like these areas. So that is how this talk about, and a little bit about me. And I've been associated with upstream kernels and U-boot quite years, and even for the DRM from since long 3-4 years back. So I write a couple of drivers on the DSI and even the bridge drivers, something like that. So more or less, I'm an embedded Linux engineer who are particularly working for an upstream kernels and upstream U-boot. So this particular talk, the talk that I'm right now talking about, is can be an enhancement with my previous talks on a couple of ELCs and XDCs. But in this talk, I will more explain about the recent improvements in the bridge along with the DRM drivers and how we want to make the bridge API can be standardized to enhance the drivers to be enhanced more. And I will potentially discuss what are the possible new bridge enhancements drivers can be follow in the future, and also what is the impact of the existing encoder with respect to this bridge API need to be standardized, something like that. So, if we can start with the actual presentation. So I will start with the initial slide. Like everyone knows that the DRM bridge, since from Linux 4.0, it has been entitled in the DRM drivers. I will explain a little bit about in detail for the person to understand. So before Linux 4.4, there is no concept of bridge at all. So all the DRM drivers need to be in line with plain CRTC and encoder. And within the encoder drivers, we have individual connectors. It could be HDMI or it could be LVDS or any PPDSA. So the underlying drivers can be stacked by taking the encoder as an example, by taking the encoder as input. But things have changed since the display interfaces are increasing a lot. So they give more possible for the display vendors rather than the SoC vendors. So they add more and more display interface converters and the display interface bridges. So in order to enhance that, they introduce the bridge API. So the bridge API can be linked list, can be an infinite connectors up to the connector. So the encoder should be passed by the bridge. Bridge can be anything up to your hardware topology. So every encoder in the bridge topology should be a single encoder. It can be in a multiple bridges, but it must have some encoder to handle the CRTC packet from the upstream DRM. That is a simple Linux KMS pipeline with respect to display bridge. So, what are the typical bridges so far we have discussed or so far we have implemented basically? The bridge can be termed differently, like there can be host bridge, or there can be the bridge that can be supported by downstream host, but it cannot be a bridge at all. And sometimes there is a bridge that can convert the bridge one interface to another interface, like DSI to LVDS, DSI to HDMI, EDP to HDMI, something like that. So here the bridge can be a converter. Sometimes the bridge cannot be a conventional converter. It can be a non-conventional display like a projector, DMD. So those DSI to DMD, like for the projector input, that is also we call it as a converter bridge. So far we have been into the Linux kernel. These are the typical four different varies of a bridge drivers. So one can be host and another can be host, but it cannot be fully bridge. And another one is convert and so on for the topology point of view. So how we can access those bridges with respect to recent editions? Everyone knows that bridge has a bridge API, so bridge can be configured, and then bridge APIs needs to be hooked so that bridge the linked list will call one after another. But what are the improvements with respect to recent Linux? Ideally, the bridge can be attached in the linked list format, so in the queue format. So assuming there is an encoder that can convert a bridge A2, A2, A1, A2, A3, then all the bridges can be attached in a queue fashion. So the bridge that attached last can get an access to the first, something like that. So this is a bridge attachment. So there is a possibility that some of these bridge attachments can be deferred. Like uh, some bridge wants to call before the actual bridge is calling, something like that. So bridge has a different APIs. It can like pre-enable, post disable, enable and disable. So all these enable and disable and pre-enable calls of the bridge can be categorized based on the bridge attachment. So what you can see is like we have some issues in the recent kernels with respect to my PDSI. So assuming there is a bridge, A1 is calling, of that bridge A2 is calling, but A3 bridge A1 require A3 to be initialized first. This is one of the typical and unhandled case where A1 need to be initialized to A3 but not A2, something like that. So there we have some flags sitting. So the internal API calls getting changed this due to these calls. So usual scenario in this stack, the pre-enable calls should be EDCBA, but since the DSA host drivers has an issue of having the legacy or some low power state, some of the bridge needs to be called prior to the actual bridge. So these are the flags that affected the bridge chain actually. This is one of the recent API change in the bridge driver. Something like this, we have a change in the post disable as well. So the post disable bridges are A, B, C, D, E, but with respect to the pre-enable call chain change, we have a call chain change in the post disable. So these are the typical improvements in the bridge so far in the last couple of releases. So let's get into actual point why we need to make the bridge as a standard API. So there are fundamentally two differences basically. So one, the bridge, there should be a bridge driver and there should be a bridge supported driver. Assuming there is a host driver, say for example there is a MIPI driver that is coming from the encoder. So the display host bridge driver of DSI can be connected to a normal panel. It can be connected to another bridge. So in this case, the DSI host need to support the bridge, downstream bridge, but it cannot be a bridge driver. Assuming that is an example, that is what it called as a bridge supported. So fundamentally, there is no issue at all if I support a bridge supported or fully bridge driver, but there is a fundamental driver definition changes here. So if it is a bridge supported driver, assuming there is a bridge supported driver, but those operations can be categorized from the encoder. So it can pump the encoder operation to the downstream bridge. But if it is a full bridge control driver or fully bridge, but those encoder drivers can be replaced with the bridge operations, something like that. So this is where the encoder will typically dump. So from the point of DSI host, there is no encoder operations required at all. This is what is called making standardizing the bridge API, something like that. So if you see in this case of Exynos DSI, Exynos DSI is a bridge supported driver of host, Exynos host basically. So it can support the downstream bridges that is connected to the Exynos host, but it cannot be purely a bridge driver. So if it is cannot be purely a bridge driver, it has an operations must go through with the encoder operations. It must have an encoder operation. Say for example, there is another tree in the stack of downstream TC3569. It is a converter driver. So the converter driver is a purely a bridge. It cannot support. It might not require encoder operations at all. So the upstream of there another stage can support an encoder, but it cannot require any encoder operations. So the fundamental advantage of making the fully bridge aware, like you can add multiple types of bridges underlying to it rather than sustaining with a single encoder operations. So this implementation, what it makes, actually change the drivers API stack. Like you can completely remove the encoder operations on your DRM drivers topology of stack. So there is no need to have encoder operations. So you can fully use the bridge APIs. So once you make the driver into the bridge driver, and register those encoder operations with your bridge hooks, and drop the call chain of bridges if it is a downstream bridge. But the encoder becomes a dump encoder now, because for the user space to access, we need to have at least one encoder. But that encoder does not have any operations as like before. Since host driver should be an encoder, that encoder should have an operations. But in this case, once you make the bridge API as a standard, once you make your host is fully bridge aware, so we don't need to restore any encoder operations at all, because it's not required, because you already make the APIs to call them as a bridge, because in the DRM core stack we have an underlying support of bypassing the encoders with bridge operations. Actually, these are implemented basically. These are implemented in one of the drivers or existing drivers. There are some drivers from the MediaTek has already been implemented. So they have removed encode operations and make the bridges an API, single API, and I have written some of the drivers with respect to Exynos, DSI, and Samsung drivers. So where we standardize the API, like convert the fully master DSI to fully controlled bridge. So one fundamental advantage with having this bridge, to make the bridge as an encode standard API, like there are some legacy calls or conventional calls in the DRM bridge, DRM drivers, like component bind and component unbind. These are controlled by the component core stack. Fundamentally, the component core stack has some legacy disadvantages with respect to the DRM connected bridges. So those component bind drivers or component usage even can be removed from the DRM drivers. This is another fundamental advantage having the fully aware bridge topology DRM drivers. So it will impact some as I said, it will impact some driver details. Like it will change the drivers. Assuming there is a host driver, if you are using the encoder operations, those are fully removed from the host, and you can replace those with fully aware bridge drivers. So there is no point of using the encoder operations at all, but we need to initialize the encoder for sure, because we need to have an access for upper user space to have a encoder. But that encoder become a dump encoder, so that can be anywhere need to be have in the DRM stack. So the bridge APIs can be replaced with the encoder APIs which we replace with bridge APIs. This is conventional theory, and there are some areas where explicit bit chain calls need to be taken care. Say for example, if you have a host driver that support only downstream bridge, you need to handle the explicit downstream bridge calls. Those calls can be removed actually, because these things need to taken care by the bridge core itself. So the individual drivers no need to taking care or no need to call the downstream bridge drivers at all. Since if your host is fully aware of the bridge. So these are the typical two changes. will make things better for making the standardized bridge API. So there are some other advantages making them as a bridge, as a single API. So the typical advantages which we have implemented in the another driver, that is uh, another driver becomes more easy to focus on the, yeah. This is another driver where we completely remove the host and make this bridge as a single driver, irrespective of SOC vendor or SOC design it has basically. This is one example of that basically. So here you can see Exynos and NXP XM8 both use the same Samsung DSMI core. Earlier, Exynos has a separate DRM drivers where all the DRM drivers will be in the queued on their DRM core. There is an Exynos DSM driver. Now we have conventionally removed the driver and make the common driver between both Exynos and DSM. DSI, sorry, IMX item. So this is one of the typical advantages where you can have a single bridge driver that can handle both SOCs, provided to have a fully aware bridge. So they should have some encoder in their own SOC DRM drivers, but they do not require any host DSL driver because there is one DRM driver, Samsung DSM driver, that can handle both the SOCs relatively, since it is fully bridge aware. So the underlying topology of the Samsung DSM can be expanded to anything like that. So you can even expand like normal linked list. This is the main advantages that we have been followed and we have used in the DSM to make the standard API. So this is why we need to make the standard API. Does it make any changes with respect to DRM? Is simply fundamentally easy because so we can have a single bridge driver that can be possible scenario that I have explained in the Samsung DSMI. So we can even drop the encoder operations since they are supporting for a long time. And there is a possibilities to support a conventional common driver to handle a different type of scores. Say for example, we have a rock chip, we have a STM, and we have AMLogic. All these are using the same design DSM core. So right now we have individual DSI drivers and to their individual DRM driver stack. What if we have a common bridge driver in the bridge stack, assuming the all these SOCs can make use of those because fundamentally the hardware topology is that is what exactly because all these SOCs are derived from using those design-aware IP basically. So it becomes more easy if you make them as a single bridge driver. So all the SOCs drivers no need to handle no need to maintain their individual drivers at all in their individual platform stacks. That is another typical maintenance-friendly environment will be created with respect to making the API as a single bridge. So there are some potential enhancements uh, in the bridge point of view because yes, as I said, the MediaTek even some of the drivers have been followed with some of the all-in-one drivers as well. That is already I'm trying to make them as a single bridge API as well to support the underlying downstream bridges. And even if you make the master the host bridge as a host DSM or host driver to as a fully bridge aware, there can be fundamental uses of underlying support of the different bridge like HDMI in and HDMI out because those need to have a proper linked list tag to understand the host as well as in the slave. So that is another typical advantages with respect to making them as a bridge as a standard API. So we have been discussing these things in the even in the mailing list. If anyone has to need to have any more details to make the standards BGP, you can even take on those areas basically. So this is overall the critical and main points of this presentation where I can briefly explain all the details. But fundamentally, the drivers need to be change to support the bridge as a single API, something like that. So if I go further onto the potential enhancements, what we can do with respect to bridge is like I have did something like this in the past, in the 1 to 2 years back, but look like there are some requirements on the main list to have some potential requirement on this particular area, like bridge switch. So if you see in the fundamental concept of display bridge, a bridge can be host bridge or converter bridge. It can convert single interface display interface to single display output interface. That is how the bridge is called, like a one-to-one bridge conversion. But there are some applications, there are some requirements in the uh, display 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 technology, where they want to have a single display input that can mux into more than two categories, like, but each and every time we can access only one output at a time. Like there is a concept called DSI switch, where we can switch between the outputs. So if you switch HDMI, you can get a HDMI. If you switch the LVDS, you can get an LVDS. So here the bridge becomes switch here. Just to understand what is switch IGA, it is not an official name to be called as a bridge switch, because upstream layers is not supporting it all. But this is a fundamental requirement right now. Is some of the vendors or some of the stakeholders are taking care, basically, like in the medical and kiosk areas. There are some frequent applications in the recent days, but this can be difficult to understand and difficult to implement. But because right now the DRM bridge supports only linked list, it cannot be a tree. So uh, you cannot route a bridge to concatenate to two different outputs. That is not possible, basically. So if you go further onto this, that I have implemented with the switch with respect to the mainline Linux, but not upstream to the Linux at all. If you see in the display output, you can see in the runtime I can able to switch the displays by using one of the output of the HP interrupt, basically. So by far fundamentally the display, you can get only one display. That is true, that is for sure. Assuming there is one display, that is LVDS is coming out and during the uh, Linux boot up, so I can switch between the displays, like by plugging and understanding the HDMI cable, something like that. That is how I can switch the displays at the runtime. This is a fundamental use case on the display switch side. Yes, it is by far can be a different approach, and it's a different difficult approach to deal with, because uh, since DRM drivers are more of a static in nature, the upstream maintainers or even the stack does not support the dynamic changes of the display outputs at all, because it will affect the user space, KMS, or something like that. So this is how it might become, there is a change in the stack if it support the bridge as a switch. Sorry, bridge switch as including as a bridge. This might change the existing KMS pipeline. So if you see in the bridge yellow noted area, where bridge A1 can be diverted to two different outputs, A21 and A22. So something like in the conventional and in the theoretical area, like PIW2 is one of the switch that can convert two outputs, one for ADV7533, that is for HDMI bridge, and SN65DSA, that is LVDS bridge. Those are internally also bridges that will take the DS input and convert the HDMI, and this will take the DS input and convert the LVDS. So the stack remains the same, but the understanding of the bridge can be routed in two different area. That is very difficult to implement with respect to the existing DRM stack. Even some of the use cases, they don't need this runtime switch, because people who uses the bridge switch, they can statically do the things at a static time. Like if they wanted to switch the bridge, they switch the bridge and reboot the system and then use it. But that is not a feasible option. Some of the use cases where have been working, like So the medical scenario where they can choose the operation in one display and the reports in the different display. That is one kind of a use case basically. That is where these switches will come into picture. This is this is why I have taken it because these are not bridges. Bridge switches are not linked list. They are trees. The existing DRM cannot support the trees, so it can be difficult difficult approach altogether to understand and implement the things. So if I hope I have covered all the details about the recent enhancement on the Linux DRM bridge, at least on the work that have been done since from the last 3 to 4 years. And these are the typical to-do list of my projects in the coming months. So I'm trying to see there's any chances of supporting this switch in the upstream, and I can try that. And I have a new bridge project that I can supporting. So since the bridge DRM drivers are well enhanced and well supported, there is no fundamental changes in the core side as of now. But there are more drivers need to be added on the DRM drivers rather than the core area. So ideally, that is one of the reasons that we have very less talks on this particular stack, since the stack has already been established and can thoroughly been used by the various vendors, something like that. Yes, that is how it is done, and I think that is have given all the information about what I have done basically. So if you have any questions, then let me know, and it can be available even for the DRM IRC.
Questions, comments? Thanks, Jagan.
Thank you.
In the meantime, I'll just put, so that way people. There's a Chromebook. Just to have it. Yeah.
These are less convenient.
Oh, I see. Yes, yes.
So these ones.
These are.
Try to speak closer to the microphone.
How large do you want it to be? But price-wise, we're touching. Try to give it. And that's a lot. Ja, es geht noch. But then they wait together.
So I know we're going to start soon, but I just want to get a feeling before we start. How many of you are already familiar with this topic? So that way we can breeze through some of the stuff. All right, who's not familiar at all? All right, thanks. That helps a lot. All right, we'll just get started now. Well, thank you guys for coming. This is Talk on Large Block Sizes. We're at Samsung, and this effort has been by us three, myself, Louis, Pankaj, and Daniel Gomez at Samsung. We're part of a team called Ghost, Global Open Source team. Oops, that did not work. Let's see. All right. So the agenda will be to review the effort. I get a sensing of what we can focus on now, given the hands that were raised or not earlier. We're going to be covering the use cases for LBS. This is on existing storage devices and also for future types of storage devices. We're going to be reviewing the plumbing and implementation and then the testing that we've done for this. Jesus Christ.
That's the conclusion.
Oh my God. Technology. No, it doesn't.
Oh, yeah.
All right. So in a nutshell, this is what we're talking about. We're talking about block size greater than page size. We use this in as a short, acronym. So if you see that, that's what this means for those that are not familiar with this yet. Nope. Oh my God. Jesus Christ. Can't be hard. All right. Thank you. So we're reviving a 16-year-old effort. And to give you some context here, the first effort started in 2007 by Christoph Lamenter. He, however, had focused mostly on the page cache. It was adding more complexity to the VM subsystem. And there was unfortunately, no equivalent solution yet for buffer heads with his implementation. Nick Pigeon then had worked on this thing called FS block. He had 2 series of patches for that. It was an alternative to buffer heads that didn't have the limitations that buffer heads do have today. But unfortunately, the implementation was completely removing FS buffer.c file, and that's typically not how we do development. We have a lot of file systems that use buffer heads, so it was really difficult to support that. Through the years, we've had advances in APIs on file systems, which allow us to slowly move away from buffer heads. One of them has been IOMAP. And then the biggest chunk of work also was through Folios support by Matthew Wilcox. A key part of Folios is the multi-index support of Xarray. For those that are not familiar with it, I highly recommend folks to look into that. Thanks, man. The common restriction for supporting large block sizes has been the tight historic coupling of the system page size to the page cache. There's 2 contexts to talk about in these restrictions. One of them is the block device context. In the block device context, you have the restriction of the logical block size being pegged to not be greater than page size. Same thing applies to the physical block size. An example here is an NVMe driver. You have, when the driver is probing a device, you have the LBA format read, and that actually constructs and sets the logical block size for the block device. For example, if you add a 16K LBA format, you will end up with a 16K logical block size. This is an example of where we're setting the capacity. Now, if you actually run this with a larger LBA format, you essentially end up just disabling the device, setting the capacity to 0. If you try to lift that restriction today, you'll actually crash. So, however, I should note that bumping the LBA format is a bit radical. So perhaps that's not the way to support large block sizes these days. In the file system context, it's about the block size of the file system, which is the minimum data block allocation unit in the file system. We're working on XFS as a prime example for enabling large block sizes. How this ends up being implemented for other file systems remains to be seen, and of course, we need people who actually are interested in this as well. Without large block size support, to give you an example, for those that are not familiar with this, you can create file systems with large block size today. However, you can't mount them. The use case types, so we'll cover the existing storage devices and then the future type of technology, which would allow new storage device experience to be a bit more optimal. You can also work with QEMU today if you want to experiment with this, both with LBA format changes and also with NVMe hacks. An existing device use case would be this poor soul who posted something about 6 years ago where he ended up with a XFS 64K block size system where he can't actually access the data anymore because he can't get a 64K page size system. Another example would be if your workloads are focused on large IOs. One example would be if you know that you're dealing with larger files than 16K. Large folios today are used on the read-ahead path and the write path without LPS support. You already get these large folios. This is a recent implementation that Matthew enabled. However, large block sizes will ensure that no small writes for inodes for data are ever issued. So one of the things that we've learned through LSFMM and also just information in general about from database developers has been the desire to support large atomics. And one of the reasons and the rationale for this is essentially the database is already using as a default page size for their internal mechanisms larger than 4K. MySQL is an example where they're using 16K default for INODB engine. Another thing to consider are some databases don't have support for direct I/O. MySQL today uses direct I/O to circumvent the limitations on buffered I/O support in Linux for large block sizes. Here's a quote that's actually very recent, only a few days ago, November 9th, at the Open Source Summit in Spain by Jonathan Katz, where he said that direct I/O is a long-term feature in the works. It will take years to implement. It is a complex problem, sorry. This is for Postgres. So it seems that Postgres will take a while to pick up direct I/O support. LBS essentially enables support for Postgres to work with large block sizes. So an example for new device use cases would be high capacity SSDs. In SSDs, you have this concept of indirection unit. It's an internal mapping to the device. And most indirection units today on SSDs having a mapping table or IU of 4K. High capacity SSDs are using large IUs to increase capacity and to decrease DRAM costs. With these types of drives, when you align the writes to the IU, you get the best performance. In the NVMe example case, you have different parameters. You know, these are, you have to be, I think, Danish to try to pronounce these. No, something like that. NPWG would be the parameter that you use to align things to the IU. And you can take advantage of this optionally to also enable large atomics to help with databases. Large block size devices then with 4K logical block size, but larger preferred write granularity and also atomic support provides you to use LBS in an optimal way. And it's also backward compatible. So this is not jumping the LBA format. So LBS is not great for all workloads. If you're, for instance, working with smaller IOs, LBS can cause write amplification due to read modify writes. But if you do large writes on a 4K block size file system, it doesn't mean that all of the IOs are going to be issued in 4K as well. So if you look at the IOs, actually, you might see that actually they're actually pretty small. So one of the things that we've learned is that the volume is what counts. So definitely be sure to do your WAF homework and measure your IO. And that will help you with understanding whether or not you have a WAF implicated in this. LBS is suitable to storage large data that can be processed in larger IO chunks. And now I'll hand over to Pankaj, who will go over the plumbing.
No, I got it. Thank you, Louis. I hope everyone can hear me. So now I'm going to talk a bit about the whole plumbing aspect. Like I think Louis talked about the use cases and why this is needed. But now let's jump into what is the limitation, where this limitation of block size is coming from Linux and possible solution. Just as a history, like one of the things that page cache was very, very closely tied to the pages, like the page size of the device historically. And why that's a problem is when a file system or a device wants to track a bigger block sizes, they need to, there was no way to tell to the page cache where you manage it as one unit. And if you can't manage it as one unit, then you can have partial eviction of some drives and some blocks, and then you have to read it back, and which is not really optimal. And there was no way in page cache to do it. And just as a quote from Billy, like, you know, why he says like why we need large folios to support large block sizes is because you need to manage them as one unit. And so if you want to track the dirtiness, you need to track them as one chunk instead of like, you know, individual pages. And that's sort of important to know that the crux of the problem comes from the page cache and why the file system or block device cache could not handle large blocks. So this is how it always used to look before. Like, you whenever you have a block device or a file system, when you try to allocate a page to the page cache, then the minimum allocation unit was a page. But that all changed like in the past 4 or 5 years once we introduced folios into the picture, and once we introduced folios and large folios into the picture, like 3 or 4 years ago, Billy actually added support to have large folios like in the page cache itself. So when it's used is during read ahead, like when you try to do a read ahead, it's gonna and if the file system supports it, for example, XFS, SHMM, AFS, AeroFS supports them, so the file system has to opt in to say that it wants to use larger folios, then the page cache will try to do its best to allocate a bigger folio when it's trying to do a read ahead. But since 6.6, which is like pretty recently, XFS buffered writes also tries to use this mechanism where when you send larger writes, IO map, which XFS uses, tries to allocate larger folio to the write to the device, which is pretty nice. Oh yeah, I also did the same mistake. I shouldn't press the other. All right, got it. Okay, just as an example how it looks like, just imagine this is like the page cache of an inode. So at the moment, if you have a 4K, let's say you have a system with a 4K page size, you can have like multiple. Can you see the? Yeah, you can see yeah. You can have multiple smaller pages in the page cache, but also if the file system supports large folios, then you can have like a contiguous range of entries that belongs to one folio, which is a large folio. So yeah, for example, if you have an offset at 16,384, which is like index 4 in the page cache, from index 4 to index 7, it's all a part of the same folio. So it's a larger physical allocation in the memory. And as Louis mentioned before, this sort of like was enabled because of the X-array multi-index support in the page cache, which is pretty nice. And so as I said before, like one folio sort of spans across multiple indices. And the one limitation sort of is like the index must be aligned to the folio order. That's important. So for example, you can't have a folio of order 2 with 4 pages at random offset. It needs to be aligned with for example, 4 aligns with order 2, so you can have it over there. Boom. Okay, to the next slide. So so we started thinking like what is missing in XFS, because XFS supports large folios in the write path and the read path. So we started thinking what is the issue with having this LBS support in XFS. So the one piece that was missing, like when we were doing the research we saw from Dave Chinner, was like we need some mechanism for the file system to say that we need to allocate at least file system block sized folios in the page cache. So I sort of paraphrased what he wrote over there. So the missing piece that we needed to support LBS and XFS was to have some sort of mechanism to tell to the page cache that we need to have a certain minimum order when we allocate a folio. So what I mean by it is like, let's say this is the page cache. You have, whenever you try to add a new folio to the page cache, you always allocate order of like whatever the file system requested, which could be the file system block size. So the file system can set like a minimum order during it sets up the initial when it sets up the inode, and the page cache will make sure that it respects that minimum order and always puts the folios in at least in minimum order of the folio that the file system requested. I will sort of give more examples on how it looks like, but yeah, that's the idea behind it. And typically, minimum order can correspond to the file system block size for the file system, or in case in the future we want to support block devices with larger LBA format, then block cache can also use the same thing because it still uses the same page cache infrastructure, which is nice. So yeah. So how does it look like if we have a page cache? Let's assume it's a 4K system, and if you have a minimum order of 2, which means 4 pages, that's 16 kilobytes. So whenever you allocate a folio in the page cache, we make sure that we allocate at least a minimum order in the page cache. And the point here is it's the minimum order. The maximum could be higher, like so we don't really like pessimize the path where if you have a larger reach, you don't actually allocate smaller folios. So that's nice. That was that. So so LBS is a pretty loaded topic. There are a lot of things could be changed, but so we want to have a tangible sort of scope for this work, for the first phase of the work. So what we thought was, okay, we already have the multi-index support in X-rays, and we sort of build on that. So that's what I mean by having a minimum order to the page cache. So we add that support to the page cache and use and also enable XFS to have LBS support. So the good part is like most of the heavy lifting has already been done by the community. So it was pretty surprising to get to 90% to how it works, because like we had to change some things in the page cache, how it allocated things, and then XFS sort of started to work. There were some corner cases that we need to fix, but at least most of the work is already done by the community, which is very nice. We sort of make use of that effort and build on top of it. And the best part is like FS test sort of like stresses the file system in a way. So the file system is going to stress a lot the page cache. So we could actually test all the corner cases that, which we found a lot of bugs while running FS test on the implementation that we did. So which was nice to shake out all the bugs. It was having like we used as a test bed. So I'll quickly go over the implementation part. Right. So how does it look like? It's a very simple API. Like we have a new API that we're going to add to the file map to the page cache, where you can set the minimum order and the maximum order you want for the page cache as a hint. Yeah. Once I explain more, I think it will get clear. I think I can see Damien's face like squiggling like this.
No, I don't get the point about the max.
Yeah, I'll get to it. Yeah, I'll get to it. So I know, yeah. So so that's a good point. So at least for the first phase of the work, we're not touching the max. It was something really started with, like, at least for the first phase, we don't really care about the max. Like we only focus on the minimum part of it. The max is still set to max page cache order. So the page cache is okay with using the maximum. I don't know if there's use case for the maximum order, like, we will get to know if it's there, but I'm not sure as such directly. So what this API does, like when you set the order, let's say the minimum order, we sort of encode that as a part of the address space struct that's used in the page cache, and we encode from bit 8 to bit 18. It's an implementation detail, but we sort of encode the order. So the order can go from 0 to 32, which is like you can store really large. If you want to go really, you want to store huge pages, then you can do. And yeah, that's the idea here. And how does it look like from, let's say, XFS point of view? XFS, when it sets up an inode, it's going to set the minimum order and the maximum order it wants. Yes, Damien, as you can see here, like for now, we're just setting as max page cache order. Let's see, like if there's a use case for like capping it, but I don't know. But the point is here, the minimum order corresponds to the file system block size. So that's pretty nice. And I also remember having a conversation with Derek, the XFS maintainer now. He sort of indicated that it might be nice to have some sort of hints where you can control to have different order for different inodes. Like maybe there's some hint that you give from the user space. But yeah, for now we sort of set the min order to the file system block size.
Yeah, maybe. So Matthew writes in the chat a few explanations. So one thing is that there is advantage for max order, and that's because the file system, for example, due to efficiency, may want to limit the maximum size of the page cache. Like usually you need some additional data structures attached to the page, like for tracking file system metadata, and you may have limits on those, like to which extent they are efficient. Like for example, currently ext4, if it wanted to use this, it attaches a linked list of buffer heads, which are block size large, and you don't want this linked list to grow too large or it would
Okay.
get really ineffective. So that's one of the reasons why you may want to restrict the maximum order.
Okay. Yeah, thanks. Yeah, thanks. Makes sense. Yeah, but at least for the first scope that we're not adding the max support, but I think it'll definitely come. Maybe that is a use case to it, so we might add that thing. All right, so some of the changes that we need to do to the page cache is like, okay, now when we allocate a folio in the page cache, we need to align the folio to the order, to the minimum order that it was set, and we need to also make sure that the size of it is minimum order. And yeah, there were a bunch of places in the file map.c and readhead.c that did this, and we had to go and change to round down, and it's like it took some time to figure out where all to change properly. But the crux of it is this: like you need to, when you add a folio, make sure you're aligned and at least minimum order to the page cache. And some of the changes that we had to do to the read ahead. So read ahead, like when it sort of moves or iterates through an extent, let's say, then before it used to do one page at a time, but now we had to make sure that it moves at least minimum order of the folio at a time. We did run into some interesting cases where like the truncate and read head had a lot of like interesting interactions, and it resulted in crashes. So we had to make sure that this is taken into account when you're doing the read ahead as a part of it. Yes.
So yeah, okay. So you are going to touch this. So maybe I'll.
No, if you want to go back, I can go back.
No. I wanted to ask exactly about. So if I remember right, like some of the page cache operations actually, what they did at least previously was that they have split the large order folios in the page cache into single pages, so that some of the operations are simpler. Like truncate was one of the cases. But
okay.
I
have. So luckily, I have the thing covered. Yeah, okay. Exactly. So thanks for the segue. So about truncate, right? So truncate was something that we had to chase a lot to figure out to get it right. And probably this is what you're also referring to, the
So
yeah,
actually, the splitting is work of Matthew. Yeah, I wrote the thing before Matthew then took it and rewrote it for the large folios. But
right.
Yeah,
okay, got it. Yeah, like at least for now, what we do. So the issue comes in is like when you have a truncate and the truncate sort of lies partially in a folio, in a large folio, then we sort of like split the folio into individual pages, and that sort of breaks the guarantee that we give to the page cache to have certain minimum order. So for now, the changes we did is like either you completely take out the folio or not, because we want to respect the minimum order. Maybe it's a bit naive, like that's how it works for now, but maybe we can change it later and
yeah. So Matthew had just writes that there are now patches from Xian which allow the splitting of large order folio to happen not to the base pages but to arbitrary order pages.
Okay.
So then you can basically keep the current algorithm when, like, if you have partial folio, then you just split it into the basic blocks,
There you go.
and then you use your algorithm to actually just either throw away the whole block or keep the partial ones,
perfect.
as we basically currently do with the pages as well. Yeah, because nothing really forces you to truncate on the page boundary. Like
Right.
we keep partial pages these days as well.
But that support is already added, or it's going to come soon?
So it's like the patches are existing currently, apparently on the list. Like Matthew writes that Xian has patches. But Mike.
Compaction patches.
Yeah,
okay.
probably.
Okay,
I'm not sure.
That's cool. Yeah. So yeah, this is the thing that we are doing right now in as a part of truncate, and of course it took some time to figure it out where exactly we need to do the changes for the truncate, but yeah. And one of the hidden surprises in IOMAP that I encountered, like in 2 weeks or 3 weeks back, I sent a patch as well, was like there are some hidden assumptions in IOMAP, like where they sort of assume the page, like the block size to be less than the page size. So So what was happening over here is like I was chasing a file system corruption where it was writing pages next to a 0 page to the device, and sometimes it was zero, luckily, but sometimes it was like some random value. So but yeah, now I think we fixed the issue, and it looks like that's the right approach to do it. Yeah. So apart from that, we also had different patches, but these are the main highlights that I want to highlight.
Yeah, so probably for this you would need to allocate a huge page instead, yeah?
Yeah. So we are having a discussion, like to have some sort of infrastructure where you have like at boot time have some sort of like big folio of zeros, like or you want to use the huge page. The only problem with having a huge page is like it can fail.
So you have to like pre-allocated zero to each page, but that
Yeah.
already exists, I believe. Like DAX was using this because, for example, so DAX. Do you know DAX?
Yeah.
So for DAX, when you have like huge hole in a file, DAX has been supporting like direct mapping of huge pages into the page tables because that was one of the use cases for it. And when you had huge holes, then we were mapping like huge zero pages there already.
Right.
So there definitely does exist a huge zero page.
Yeah.
And you just have to be careful to use it enough. But
Yeah, I'll look into it. Yeah, I think the discussion is ongoing. I also saw Christoph. He also wanted something like this for his work. So it looks like it's like many people are trying to solve the problem by. Right now, I fixed the problem by iterating through, like having multiple zero pages added to the bio to make sure that it's at least the file system block. But I mean, I think the better approach would be like you already have the bio add folio interface. So why not have a bigger folio directly added to the as a part of the bio? But yeah, but for now, we do the iteration to add the zero page, but it works, and we can optimize it later. So with respect to testing, I'll cover the first part of the testing, and then Louis has like a lot of things to talk about testing part. Like the first one I wanted to do was a sort of like an IO distribution analysis with FIO to check, it's more of a litmus test to see if LBS is doing what it's supposed to do in terms of like sending bigger blocks to the devices. So what I did is pretty straightforward. Like I have a FIO job with 64K IO block size. It's doing a buffered IO. It creates a bunch of files, and it writes to multiple files to it, and the size of the file in total is actually bigger than the RAM I allocated to the VM, just so that it starts doing a write back and to see the splits and to see how it performs. I'll talk about the hardware a bit later, but this is the idea. So we made like a small tool with eBPF to trace the IOs that are going out of NVMe. So you have the FS here, and you have the NVMe driver, and FIO does the FIO, and we sort of measure like what is the IOs that are going to the device, and we put a probe to see what kind of IO distribution we get if we have the support. So for baseline, I had like a 4K block size ext4 with big alloc. So the cluster size is 64K to match with FIO block size. And XFS, it's sort of the baseline to see XFS with 4K, to see how ext4 and XFS with without our patches perform. And the last one is like XFS with whatever support we added, and setting the block size to be 64K on a 4K base system. And the setup, like as I said, I purposefully made a VM with a small RAM, so that like once after some point it starts doing write back and to see what kind of IOs like are they being split, or what's happening. So these are like the preliminary results I got. So we have ext4, XFS with the 4K block size, and XFS with the 64K block size that we added. How we are doing on time? Okay, we have some time. Okay, I'll be a bit quick here. So we as you see, like Linux is already pretty good at sending larger IOs to the device, and it's also an ideal test case. Like, it's not like a real workload, to be honest, but you can see that Linux is already pretty good at sending bigger IOs to the device. The block layer does plugging and make sure it merges the request, and it does a lot of nice fancy things. That's good. But but the point over here is like once we want to have some sort of a guarantee from the device or the database to have I don't want to have any splits happening below a certain block size, then we need to sort of focus on this area, like what happens in that area, right? So when I focus, so it's the same graph, but I'm sort of focusing on the smaller part, right? And here you can see that ext4 sends a lot of 4K writes, and XFS with the 4K, actually it's pretty good, but you can see there's still a lot of splits that are happening. And then the final one you can't see, which is good, is the support that we added, and make sure there is no IOs that are less than the block size. And that is, you can see that there is a small IO that are still going to the device from our patches. Yeah, I tried to trace the process that's coming from. It's coming from the XFS metadata writes, like where it does an asynchronous writes. Those are still 4Ks. I mean, but the most of the data part is like 64K, so which is nice. So now I'm going to give it to Louis about some more interesting benchmarks.
So this is just your typical stuff that you guys might expect. Obviously, benchmarks are, pretty abstract and so forth. So things that people are used to are just building Linux. So this is all preliminary, and this is why the performance tests are really just limited at this point. We got this pretty much finished a little while ago. So actually, we've had only so much time to actually prepare with actual, real tests. So this is all new. Meaning that I guess I'll get into this. So the stat, no, it's all right. Well, is it just put, all right. So basically we just build Linux. Here's an example of run on Xeon Gold server with 128 processors, 1 terabyte of memory. This is running perf stat 4 times, and pretty much you have parity. This guy, right? Here's another example, now running 100 times, building Linux. On 16K, we actually see a better performance. But, again, I really do believe that's within noise, so I wouldn't consider this serious. Don't take this as like, oh, this is better. No. Here's another example. I figured I'd try to launch some AWS instances. Here's the biggest server that I can find from AMD. I figured, hey, why not try to test with some of that PTE coalescing stuff that they have, right? So it's a really huge server, huge amount of RAM. Here's a building with 2 runs. And I don't know why you can't actually see the PTE coalescing on the AWS instance. So much for bare metal, huh? Yeah, here's another AWS instance. This is a more moderate type of system. This is 32 vCPUs, but again, there are vCPUs, pretty much parity as well. So we need more evaluation. So this is just very preliminary. Here's the device matrix of what has to be considered when testing a device on different block sizes with different LBA formats. The stuff in blue are basically things that you can already, work on today with today's technology, storage devices, if you want to work with these patches. The stuff in orange or yellow, depending if you're colorblind, I don't know, are things that would, you could actually run LBS on with larger LBA formats. You basically can do this with QEMU today. We have functionally tested, it's basically equivalent. The stuff in green is essentially what you can enable with a large MPWG and NAWPF, so essentially the large atomic as well. Sorry, just one more point. And the stuff in purple is stuff that is not essentially supported today. That's basically a 64K sector size is not enabled today in XFS, and that would require a format change. And talking to Jenner, it seems that perhaps that might be something welcomed in the future. But, for this, I think we should leave this as a side thing for XFS BOF. But yes, Damien?
So the sector size in your table here, you're talking about the physical block size on the device, or?
We're talking about the MKFS-S size parameter, which basically just sets the block device cache.
But then what's the block size?
block size
sorry, LB format, I understand. The other two, they are not clear.
One of them
What do they mean?
One of them is the file system block size. The other one is the sector size that you set on the file system. And right now, the only reason that you would set the sector size to communicate to the block device cache, what block size to use for the block device cache. That's pretty much it.
What?
Yes. It's the sector size. Yes. It's actually.
Yeah, you lost me.
Well, let's talk about in the hallway about this, but pretty much, I was talking to Chinner about this, and pretty much it's useless. We do have to work on some of these semantics because it's at this point in time that's kind of like what we're using it for. It is the block size set for the block device cache.
Yeah, but basically,
Oh, that one.
Yes,
Yeah,
yes,
yeah.
yes. It's like, oh my God, why is this so? Jesus Christ.
but practically every file system sets this to its file system block size. Yeah.
I'm sorry.
Practically every file system sets the sector size to the file system block size. Yeah.
Actually, the logical block, the sector size.
Yeah.
They set it to the logical block size typically.
Yeah.
Yes, that's true. It's true. Yes.
So about your benchmarking, I think you should also look at the amount of memory, like the memory usage and the disk
Yeah, I will.
usage.
I will cover this.
Good, thank you.
So here's the example of consideration that you would have to take if you want to test XFS today. These are the profiles on the left that we define. And on the right, you see the new LBS profiles. The baseline profiles have come through an evolution in time. And essentially, the latest update came from Chandan, who's now essentially working as a release manager for XFS. He ended up extending the profiles that we have to basically provide coverage that Derek wanted as well. So that's why you see some of these kind of odd ones there that I didn't know were possible. So we're using KDOS for RFS test testing. To give you an idea, it takes you about 20 to 30 minutes to set up a test rig to test all these baseline profiles only. You'll need about a 4 terabyte drive to test all these profiles. You'll also need about 4 gigs per guest. That's about 80 gigs of RAM. So just have a set of RAM. The more the better, basically. We have not yet needed more memory for testing large block size support. It's very, very interesting. We didn't expect that result. We were expecting a lot more. But granted, this is just running a FS-test. It's not stress testing with performance or workloads. It's just running a FS-test and making sure that we're not getting mems or anything like that from the testing that we're doing. We had to pick a baseline to focus on ensuring that we're not regressing the kernel. So we essentially picked 6.6 RC5 and just have stuck there for a while now. Our goal really is to get first the baseline to make sure that we're not introducing regressions. Our objective then is to run a fast test in a loop 100 times and to ensure that we're not seeing any new failures that will allow us to have high confidence that this is the baseline that we're working on. We're using a soak duration of 2.5 hours as well. Here's an example screenshot of what this looks like when you're running a fast test on a big cluster with all these profiles running. Here's an example of a crash that happened. So when that happens, you have to SSH in, do journal CTL-K, scrape the log, copy, paste this. I basically use a gist, a GitHub gist, and paste that there, and then just refer that into the expunges that we have. You also see before, I forgot to mention the soak duration stuff. When a test is enabled with soak duration, you will see those tests, soaking as well. The results for the baseline is what I'll cover first. And essentially, the confidence in the baseline at this point is 25 loops running FS tests. We essentially are putting all of the results also in the KDOPS Git tree. So if you want to see any of the results of any of these runs, you can go and look at them. All failures are itemized as expunges, and we also have added a failure rate notation to indicate approximately how many loops you have to run the test to fail as well. These are known as flaky tests. At this point in time, we have 443 known failed tests, 43 crashes. Here's an example set of crashes. The most common one is the assertion failure. And that happens on XFS iFree for different reasons, for different tests. It is the most common failure that we have found a lot. The second one is another assertion as well. Then we have a series of hung tasks. I won't get into and bore you with the details with this. 5 minutes? Great. Because we'll have an XFS BOF where we can cover some of these things as well. So there's really crazy flaky stuff here, like mixing buffered IO and direct IO. Insane, types of tests to run, right? Because this is just stupid, but we still have to support it. We do have crashes when this happens that I don't think have been reported before, but we will be reporting these. The results for LBS so far, we have some odd, I would call them at this point test bugs, really, because we just have to enhance them because they weren't considering large block sizes. One example here is a crazy one where we do the number of XFS attributes that are injected with XFS DB based on the block size. For large block sizes, n equals to this huge number here. It takes about 30 hours to run. It actually successfully completes, but that's just too long to take, so we have to reconsider that. I haven't gotten a feedback on the bug there. Some tests also need to be fixed for large block sizes. But the good news is that we have found 0 regression so far. The next steps are polishing the min order patches again, posting them. The block device cache needs to be addressed as well, because that's essentially what user space interacts with when you're running FS disk or whatever and so forth. I had posted patches before using dynamic AOPS. Chandra was very clear that he didn't really support that because we already learned through DAX experience that that's not actually ideal. So we have different alternatives. One of them is using IOMAP bufferhead compatibility, as suggested by Chandra as well. That requires a bit of work. That doesn't work for me yet. Buffer heads are the next target as well. If we get large folio buffer head support, we essentially get the block device fixed as well. Other file system support also needs to be evaluated. At this point in time, I've only heard interest by GFS2 maintainer to also help with large folio support. NVMe, there's also some changes that are actually relatively easy once you get the stuff upstream. We already have them implemented, and we have tested them with larger LBA formats and QEMU. Concerns, I saw earlier there was in the chat talk about fragmentation in a way. So this is where I try to cover this. I had asked, this is the thesis. So it should be possible to test this thesis now. I had asked for a simple memory fragmentation measurement, and John Hubbard was kind enough to provide a simple algorithm. So we should basically now just go out and try to implement this, do measurements, and see whether or not the thesis here was correct in the end. And even if it was incorrect, fortunately, we have Ziyang's patches who try to provide support. At this point, in the slides, it was RFC, but last night I saw this is a new patch. They're actually moved from RFC to patches for compaction for higher order folios. So there is already support. Well, not support. Patches are already posted for large folios. If you're interested, we will have having monthly meetings. The next one was set at Japan time to accommodate some folks in Japan. So hopefully, my hope is that some people that are in Japan will join us next time. And then the next time, I suspect we'll rotate to a European-friendly time zone, then back to US, and then Japan, and so forth. So just join us. We're also on Discord on a large block channel. And lastly, questions. We probably have like 1 minute or questions. Otherwise, just talk to us in the hallway. But this was a lot. Hopefully, you guys have found this useful.
Yeah. So maybe I have one quick question. If you could go back to the IO size distribution for the FIO test, because what I'm really wondering about is that, so you have there, even the one before, because so obviously we have these small IO sizes, so that's understandable. Could you go one more back? So here, what is confusing me is that the maximum IO size is 128 kilobytes, so that's the maximum NVMe request size or whatever.
I think I forgot to mention it. I put it here. The MBTS was 256K for the NVMe drive I was testing on. So sorry, I forgot to mention about the MBTS of the device that we are dealing with.
Okay.
Yeah.
But still, so we had practically no 256 requests, yeah? Because
Yeah.
like for the write back, I would expect the block layer to be submitting basically BIOS that are several megabytes large, yeah, for this workload.
It's a good point. Yeah.
And so,
That's on QEMU, right?
It's on QEMU, but passes
Yeah,
the devices passes the.
Yeah, but I think you get like a super crappy number of segments, and you can't really.
Okay.
The BIOS max size is small.
Okay. That explains.
I think at 128K is actually what you get with QEMU these days.
okay, so
that,
it's
that
really
needs
the
improvement.
QEMU limitation. Yeah, because I was really surprised because the write back layer will be submitting like basically megabyte large or several megabytes large BIOS, which then must be getting split somewhere by the block layer or the NVMe driver, basically for the constraints as like,
Yeah, like, but this is not a benchmark per se. It's more like counting the IOs, like how the things are. But I get your point. Like, it was still like sometimes we did get occasional crashes, so I was a bit scared to like it was the machine. I didn't have too much time to like put the file system and see if something like so. But the point is like I tried to do a pass through of the NVMe. So anyway.
okay.
Yeah. Thanks.
Out of time. So
Yeah. Thank you.
Oh, you got right into the chat now. Oh, yeah. It seems easier. Oh, yeah. It's fun. It's not working out. I can send this. Oh, yeah, it's a break. So we stop from the
It doesn't take into consideration that you essentially end up with a fragmented system if you're that system is fragmented. So we're enabled dynamically.
What's your plan with each pages? I think of a dividing line, like today and then after run. Because he enables people to be smaller than people. And once you turn that on, those work they don't connect to you. I mean, it's really nice. Because you can pick
Like if you look from
and say, oh, that's my big size. And now it's my block size. Oh my God. Well,
should we move up?
oh, all right. For arms, but it does tell me, well, let's see, for small sizes like that. I think something.
You actually don't know when we cover that later.
Yeah. Can also do something else now. It's a chunk of that, the size of the fund. something, and once that happens, then yeah,
Murders. Oh yeah, he said save those. heard the drumming?
We're just doing feedback on the next to each other.
Yeah, because I said this. Let me stop.
Mine does it. Kind of. This guy, like, I put him with the chairs with the way, but this guy was kind of the other ones are like, I don't know.
I get that major issue at Magnolia. Oh shit!
It's probably because the game's too high, but like, at the same time, I have to be where they're at.
Right.
She's getting pizza for lunch.
Yep.
I don't know if I'm where, but I don't eat pork, so he's getting one with cheese. And he probably is getting another with pepperoni, but he was like, "How do you want?" I was like, "Oh." He's like, "I'm not even gonna ask Angel. I know he don't care."
Absolutely don't.
Asking me, I don't care either.
I'll probably want to sit here, get me an appetizer after all this kicks off. I've been eating some terrible fucking Uber Eats past 2 days. Wendy's sucked. Like, you know, it was cold as hell when it got to me. Ordered KFC last night. All the chicken was overcooked. Uber Eats, you've been complaining way too much about your food. Maybe you should sit here and start having your people sit here and make sure that all our food is fresh. Not me sitting here wasting money to sit here and throw food in the trash. Who does that?
You walk. So like over by where we smoke, if you keep going down that street that's right there,
Mm-hmm.
you get to a place called City Dogs. You do like hot dogs and stuff.
I think about it. Charlie was telling me about this little Caribbean spot that's like about a block away from the hotel. I might just end up walking over there once my feet find the power to get up. I shall head back to the cave.
Hello everyone, my name is Kong Wang and I'm from the System Technologies and Engineering team at Baida. So today I'm going to talk about Linux kernel auto-tuning. So this is the agenda today. I know it's a lot of information, so I will try to finish everything as soon as possible so we could have more time for discussion. Okay, so before we start, so the first thing first. So the first thing I needed to clarify is, I'm not an expert on machine learning, so don't ask me machine learning questions. And also, in case you wonder, so if I'm trying to kill our jobs, no, I'm not. Yeah, I'm pretty sure there's still a lot of work we need to do here, and even if we automate everything, I'm pretty sure the knowledge from engineers is still required. Okay, let's go back to this topic. So the first one is, the first important question we need to answer is, why we need auto tuning anyway. So I think there are three reasons we need to consider auto tuning. So the first one is, when we tune the performance. So this is a very time consuming effort. So it consumes a lot of engineering effort to evaluate the performance, to understand the different parameters, to understand the different metrics. So if we could automate the entire process, so that means we could liberate all the engineering effort, and we could focus on something different. And the second thing is, even when we for our performance engineers or kernel engineers, when we tune the performance, there are a lot of difficult decisions we need to make, because there are a lot of different trade-offs we need to think about. For example, whether we need to treat a CPU with memory, or whether we need to treat the performance with, for example, power consumption. So a lot of trade-offs. So it's not that easy for our performance engineer or kernel engineer anyway. So if we could have some other way, an automated way to make a decision for us, and hopefully better decision, and in some quicker way, I think that this will also benefit us a lot. And the last point is, actually, I do believe with machine learning, we possibly could find more optimal solutions than the currently method we use for some specific workload. And briefly speaking, there are two categories of auto tuning. The first one is the rule-based one. I think most of us are already familiar with. And the second one is the machine learning one, which is not very popular. This is why I want to discuss here today. So the second question we need to think about is, why do we need to bother machine learning at all, right? So, however, to answer this question, we need to go back to the very beginning question. So, what is machine learning anyway, right? So, actually, this question is not that answer. So, it's not that hard to answer. So I'm not a machine learning expert. So this diagram actually, in my opinion, is the easiest way to understand what machine learning is, for our, traditional programmer. So, when we use the traditional programming, we have some data as the input. We need to write some programs to get the input, and of course we need to execute the programs typically on a CPU, and get some output from the computation. So this is what we are all familiar with. And how is machine learning different? So machine learning is very, very different from this point of view. So machine learning actually takes the data. The data actually is both input and output from the historical information. And the machine learning actually will do some computation, typically on GPU, and it will produce something like a program. Actually, typically, this is what we call it machine learning models. So this is very different with the traditional programming. And with that, I do believe machine learning could help in our auto tuning case. So let's take a look. So how does the machine learning process look like? So basically, briefly speaking, this is how the machine learning process look like. So it's very simplified. So we have some different features to tune, and we have some target to meet. And our machine learning engineers, they need to write some algorithms to train the machine learning model. At the end, we get some model, and with that model, when we have some new features, we could actually use that model to predict some target value. So briefly speaking, this is how the machine learning process works. So why do we need machine learning for operating system, especially for Linux kernel here? So actually, I think one of the great explanation is I quoted here is from Jeff Dean from Google. I think he runs the machine learning for system workshop. So this is one of the quotes I selected from him. So computer systems are filled with heuristics. So I think this is also very, very true for the operating system, for especially for Linux kernel. So heuristics, I do believe they have some room. Of course, they exist for a rather long time. We still have a lot of heuristics in the Linux kernel source code today. So they do work well in general, of course, in general, right? So I don't think they work that well for some specific case. So this is why we need to consider whether we should generalize this kind of heuristic for some specific case, so we could get a better performance for this specific workload. And generally speaking, the heuristics, they don't take consideration of any particular pattern or any sufficient context, in my opinion. With machine learning, actually, we could open this door to learn these different patterns, and as long as we feed sufficient data, I do believe they could consider a lot of more context. So let's take a look at what we have the heuristics today in the Linux kernel. So I selected 3 different cases in Linux kernel from 3 different subsystems. So just to give you some quick idea about what kind of heuristics we have today. So the first one is the read ahead one. So we need to decide, how much memory we need to prefetch from the storage into our main memory. So this is one of the logic we use in the Linux kernel source code to decide how much memory we need to prefetch. So pretty much, as you can see from the comments, we assume it's a sequential access. Of course, we don't know for sure, right? And the second one actually is from the networking. So at the core part of networking, especially related to the TCP/IP stack, so the congestion control is definitely one of the most important part of the TCP/IP stack. So here is this code actually shows how we calculated the TCP congestion window with the TCP cubic congestion control algorithm. So as you can see, still a lot of heuristics here. The third one I have is related to NUMA scheduling. So when we need to schedule some tasks, we need to make some decision whether we should move this task to some preferred NUMA node. So this is one of the decision-making code I selected from the scheduled code. So as you can see, we pretty much based on some retrying mechanism and try to guess whether this is a better decision. So this kind of heuristics exist for a rather long time in Linux kernel, for decades, especially like the TCP congestion control, like the read ahead one. So is there anything we could do to get rid of this kind of heuristics? I think this is possible. So if we take a look at this problem from a different angle, so to see how we tune Linux kernel, how the Linux kernel tuning evolves from the beginning until nowadays, we have the eBPF. So of course, in the beginning, probably we have probably more hard-coded values, and I think today we still have some hard-coded values. For example, in networking, the byte queue limit is they intentionally hard-code the value because they don't want to bother users to tune the parameters. Yeah, and of course, I think everyone is familiar with the how Linux kernel exposes different parameters, like PROC-FS, sysfs, if you are networking people, we use Netlink. So essentially, this kind of interface is primarily, to basically to update some kernel values within somewhere in the kernel. So which is also very simple. And now we have eBPF. I think from this angle, actually eBPF makes a lot of sense because eBPF not only with eBPF you could not only actually just simple update some values, but you could also write some programs literally to replace some kernel code with your own logic. So essentially, I think eBPF is definitely a great idea from this angle. However, I do believe we could do more than eBPF. Because why? Because we still need programmers to write eBPF code to make this happen. So what we could go further, like what we could actually, maybe we could use machine learning to generate some learned program without any engineering effort to get this. So this is actually the point I want to make today. So I do believe, with the diagram I showed in the beginning for the machine learning introduction, this definitely totally make a lot of sense. And for the implementation part, so I do I don't have any specific idea yet. However, I do believe the kernel machine learning is one of the possible implementation. So here is a quick summary. So why do we need machine learning for operating systems, specifically for Linux kernel? So as a quick summary, machine learning algorithms could actually help us to explore more solutions than the rule-based approaches. And there are 4 areas I do believe the machine learning could help the operating system in general. The first one is the prediction. So if we could do some prediction based on the historical data, that means we could actually have more knowledge for the tuning for the analysis. And the second one is the root cause analysis. So this is also a very big category for the machine learning. So the root cause analysis actually, in my opinion, could also help us to, for example, to identify the performance bottleneck, or maybe with a large language model could also help us to narrow down the bug fix as well, maybe possibly. And the third one is classification. So this one actually, if we could classify different problems into different categories, and we could use divide and conquer to solve different category of the problem in different ways, this could also help us a lot. I do believe. And the last one is related to the topic today is optimization. So we want to leverage machine learning to recommend some best of the parameters for some specific workload. So let's take a look at the optimization part. So for this problem, I think the best definition is, and the simplest one, in my opinion, is this. So our goal here actually is to try to find the best set of parameters. Let's call them X. And we want to optimize some target metrics, let's call it Y. So with different combinations of different parameters, we get different values for the Y. And definitely our goal is to find the optimal value for the Y to meet our performance target. And for the X here, actually, there are tons of parameters in the Linux kernel. for example, the TCP initial congestion window, the watermark scale factor. So and for the performance metric, actually it's a very broad concept. So for example, we could for different workload we use different ways to different metrics to measure the performance. Some workload we use latency, some workload we care about throughput, and some workload we care about the resource utilization, like the CPU usage. So I do believe the machine learning could actually help this problem, and there are two kind of approaches for this problem. So basically, there are two categories here. The first one is the stateless, and the second one is the stateful. So they are significantly different here. So this is why I need to highlight the difference before we continue. So as a quick summary, so the stateful one actually requires to memorize the past input and feed it back to the next iteration of the tuning. So it requires multiple iterations to get the optimal performance, while the stateless one, of course, does not have this kind of iterations. So there are different machine learning algorithms to fit into these two categories. For the stateless one, I think the typical one is the linear regression, which is already used by the adaptive MM tuning, and also the random search and grid search. Actually, we also explored the random search when we set up the index tuning in our specific case I will mention later. The second category is the stateful one, which is more complicated. So this one actually is, as I mentioned, it requires multiple iterations to get the optimal performance. And during these iterations, it may have some regression as well. So what does this mean? This means we need to have some guidance for the optimization. So we need to tell the optimization algorithm, hey, are we heading to the right direction? So to answer this question, actually, this will introduce another piece of puzzle here. So how could we evaluate the performance automatically? So, typically we rely on the performance engineer or Linux kernel engineers to evaluate the performance, whether with some diagram or some charts or some data. However, this definitely does not work, when we need to interact with the machine learning algorithm. So we need to have some automated way, and we actually use some statistical tools to utilize this. And briefly speaking, these tools actually is simply to compare different data distributions, and we still need the engineers' knowledge to tell the statistical tool, hey, which is the best. And of course, there are different statistical tests for the performance evaluation as well. So I'm not an expert here, so I will go over this very quickly. So and I think maybe it's the time we should take a look at some specific use case. So the first use case we have is the Damen one. So it's a very simple, and it does not require any machine learning stuff. So that in case if you are not familiar what is Damen, I think Damen is pretty much the new subsystem for the memory access monitoring and optimization. So we leverage Damen to tune our MySQL memory. So and the Damen actually offers multiple schemes, and each of the scheme actually have different parameters. So at the end, we have a lot of parameters to tune. So fortunately, we already have some adapters available to search for the best scheme. And we actually modify the simple adapter for our purpose, which is for the MySQL. And we evaluate different schemes based on the MySQL performance metrics. And fortunately, the simplest one already worked for us. So because we don't have any, swapping, actually we have to leverage the ZRAM to do this kind of, swapping and to offload or compress the pages to save the memory. So even with this, at the end, we got about 30% of the memory reduction. I think this is also very impressive. The second use case we have actually is a complicated one. So for this case, we want to tune the performance for the Nginx server. So we set up some HTTP latency benchmark for the Nginx server, and we hand selected 16 kernel parameters to tune here. And to evaluate the performance, so we got some different data distributions. So like I mentioned, we use some statistical tools to evaluate the performance. Here, just give you some quick idea about how the distribution look like. And here is the final result we have. I think this is the most interesting part. So I think if you take a look at the baseline, so the baseline we selected is very interesting. So because we want our goal actually is not only actually to beat the default value provided by the Linux kernel. Actually, we want to beat the Linux kernel engineers. So we actually asked one of our Linux kernel engineers on our team and to spend about 30 minutes to tune, this kind of 16 parameters. Yeah, I know 30 minutes is not that sufficiently long, but hopefully it's sufficient, as a comparison. And on top, and then we use the Bayesian optimization, and we apply different acquisition functions, and we compare the performance of the different functions here. So the final result is also very interesting. So the last one actually eventually produced more optimal results than our kernel engineers. And more interestingly, actually, the machine learning algorithm takes shorter time than the kernel engineer. So this is very interesting. So the next topic I want to bring up is, the kernel machine learning. So what is the kernel machine learning? So this concept is not actually introduced by me. So actually I found this kind of concept in multiple papers. So the most impressive one is this paper's kernel machine learning, using machine learning to improve the storage system. So I think this diagram could explain what the kernel machine learning is. So briefly speaking, so we want to bring the machine learning into the kernel. So why do we need to do that? So of course, this is not an easy problem. So there are different pros and cons. So if we do the machine learning in the user space, we definitely have a lot of freedom. We don't have literally we don't have any restriction, right? However, if we do this in the kernel, I think the game will change significantly, because kernel space have a lot of kind of restriction. For example, I think the most important one is the floating point. In kernel space, we could use floating point in some restricted way. However, if we use the floating point, that will bring some additional overhead to the Linux kernel. And more important, actually, in user space, we don't need to worry that much about the CPU and the memory overhead, which typically come together with machine learning. However, if we bring this in the kernel space, that means, we will not have this kind of tolerance. For example, if we use a lot of CPU in the kernel, that means we will possibly trigger, some like a soft lockup or something like that, right? And of course, the last thing is, the Linux kernel actually, our machine learning engineer asked me to add this point. I think he's right, actually. Linux kernel actually is written in C, currently mostly in C. I think, we are moving to Rust, maybe a little bit. However, our machine learning engineers, they typically use Python or Java, to write their machine learning algorithms. So if we force them to switch to C, so this could be another consideration we need to think about. And of course, there are also some advantages if we want to do the machine learning within the kernel. For example, we do everything within the kernel. That means we no longer need to transfer the data between kernel space and user space, which usually requires copy. And of course, if we do this in the kernel space, that means we could do everything online and in some more real-time way. So speaking of the floating point, other than the overhead, there are still some other considerations we need to think about. For example, if we could actually choose not to use the floating point. And of course, this is, we need to trade off. If we don't want to bother the floating point, let's say if we use a fixed point computation, that means probably we need to lose some, accuracy or scalability. So there is no one right answer. So I think this kind of question largely depends on the use case. So depends on some specific use case, whether maybe you don't care much about the accuracy, right? If that is the case, I think it is definitely possible to use, to avoid the floating point, for example, using eBPF to do this kind of machine learning. And of course, if we really want to use the floating point, I think it is possible because we already have some code specifically in the crypto subsystem. We already see a lot of, kernel FPU begin, kernel FPU, FPU end. And we do believe the kernel machine learning will also open a door for us to explore the machine learning in different scenarios. So the page-free patch one is what I already mentioned, to whether it is to prefetch the memory from the storage to the memory or from some remote storage to the local. And of course, it could also help the scheduling, whether it's CPU scheduling, whether it's IO scheduling, whether it's NUMA scheduling. And also, it could help the caching eviction. So there is some research related to learned index. I think they could help this category of the problem. And also, like some other use cases I mentioned, the network congestion control, the intrusion detection. I think we could also explore the kernel machine learning. So as a quick conclusion, so we do believe machine learning is important for the operating system tuning, whether we want to do the machine learning in the user space or in the kernel space. And although there are many limitations we discussed, and I do believe the kernel machine learning one is not only possible, but also necessary for some case. So this is all I have today. So this is not my own work. So I want to use this opportunity to thank my colleagues. They are not here. However, this is a team effort. So I want to thank Jasmine, Chris, Bobby, and Yaxin for all this kind of related work. Thank you.
Questions, comments?
So in your Nginx example, you pre-selected 16 features. So why not just start with all features and find out what's best?
Yeah, great question. So actually, we didn't have much time to dig into all the related parameters.
For the 16 features that you did try, was there anything surprising about the results?
I'm sorry, I don't get this question.
For the 16 features that you did try, was there anything surprising about the results? Like, did you actually learn something like, actually, now we should put 27 here instead of 15 or whatever? I don't know.
Oh, great question. So I don't think we noticed any surprise.
Okay.
Yeah, thank you.
So if I understood the results right, like in the example of optimization you had there, so it took you like 17 minutes to optimize the parameters, yeah, to come up with better suggestion, let's say. So this is one of the, I would say, obstacles, because like it's a lot of CPU time, yeah, for something that tends to be dynamic. Like the workloads are constantly kind of changing. Yeah. So here you had like basically static workload. Yeah, you are serving engines, web pages. It's pretty non-changing workload. So for that, you can take 17 minutes to optimize the parameters and fine tune it. And like, obviously there are use cases where this is great, but like if you want to wire it up, as you said, to the in-kernel auto optimization of the parameters, then as the workload changes on the machine, then 17 minutes is just, or if you had even more parameters to optimize, then the time would actually blow up to hours, yeah, and then it's not really practical that you take 2 hours or 5 hours to optimize the parameters only when the workload changes in 20 minutes, yeah. So that's one of the problem. I'm not sure if you have some thoughts how to overcome this, because in kernel we use these trivial heuristics exactly because they can react fast. Yeah, that's the whole point. Like if we had time and resources to do the complex analysis, then sure we would be doing it. But because we are so resource constrained and the reactions need to be fast, that's why we use the trivial heuristics, which are obviously wrong in quite a few cases. But
yeah, and the use case we have actually, like I mentioned, is pretty simple. So we use some simple benchmark, not actually any real workload. Yeah, so this is why I think it already makes some difference with such sort of a period of the training. Yeah, and I do believe when we have some real and more complicated workload, definitely it probably takes more time.
Oh, there we go.
One thing that I'm particularly concerned about, like with machine learning model in general, but specifically in this context of like machine learning for kernel, is that a lot of those models are essentially black box, right? You're gonna have a really hard time like interpret those models result when things go wrong, and debugging kernel is already complicated. So imagine if like, I don't know, we export like bunch of knobs that you optimize for, and then it regress our performance, and now what, right? Like have you considered any thoughts or opinions on that?
Oh, this is a great question. Yes, I think machine learning is definitely not the ideal solution. I do believe there are some disadvantages as well. Actually, the paper I shared in my presentation, actually that paper we did some our own research. Actually, that did not this paper. This is the paper I mentioned. So this paper actually. Based on our experiment, actually it goes to a wrong direction. It could not work well. Yeah, we tried. Yeah.
I have one more question. Is like when you have this using this kernel, machine learning, you get a better result. And have you ever also trying to see different areas, like maybe you're running different workload, maybe scenario changes? Does that that tuning the result may not be the optimal one? This is my first question. Second one is like, do you ever do a insight analysis, say why this is better, right? Because of you have a longer network queues, because of you have better, more CPU resources, is that process, done in this paper or in this research? Yeah, thanks.
A short answer, not yet, because we only tried the simple cases we mentioned. So we are exploring more use cases. However, nothing has finished yet. Yeah. Okay, thank you.
Thank you. Okay, so I have a question about the like the end product of the machine learning. So my understanding is that with machine learning, you get a model which you can ask questions. For example, like if I have like 4 vCPU and 2 GB memory, and what's the best kernel parameter I could choose for the Nginx workload. So is that, but from your presentation, I think it's actually something different. Is you use that machine learning to do automatic tuning. So I just wonder that does your method actually have this model to answer questions like for different VM size, different memory, and to give you the answer which of which current parameter is the best, or you just use that machine learning to tuning for a particular VM size?
I'm not quite sure if I understand your question correctly. So the parameters are still selected by our kernel engineers manually. And we also needed to set some, safe ranges for the different parameters. In case, it goes.
So my question is that could you method use the data point from like one VM side, one CPU, one machine side, and do a prediction for a different machine side? Like, can you method do that? Handle that case? Is that handled by your method?
I'm sorry. What side?
So, I mean, can you use machine learning to analyze data point for a particular VM size or machine size? That means the number of CPUs and the size of memories and the network hardware, and then it will give you answer to like the best kernel parameter that you want to use, right? And then can you also use that same model for a different machine?
In my opinion, I don't think it's very related. However, maybe there are some complication within the kernel, like, the a watermark scale factor that is definitely related to the total memory we have.
Okay.
So it depends, I think.
Okay.
Yeah.
Thank you.
Thank you.
Yeah, just a question from my side. I didn't understand the setup. Like usually, like there are a lot of workloads running, but you are optimizing for like one specific workload. So is the expectation here is like there is one dominant workload among many that are running on the system, but you want one of them to behave better? Or is the algorithm going to optimize for all of them in one go? And there is the factor of all the noise that's happening in the background because, for instance, in 1 hour, maybe this is like the backup daemon will running, which is not running all day long, which can impact all the tuning results. So like, is the expectation, the question, is this static or dynamic kind of system?
Actually, we simplify the problem here. We isolated all the performance tests in some virtual machine or container. Yeah, so actually, I think the mixed workload is a very difficult problem to solve with machine learning. So if we want to tune multiple workloads together, to meet multiple goals, this is very difficult in my opinion.
It is difficult, but that's the practical way because you cannot isolate one workload in one machine, especially if you have like a newer machine reserved for one workload. That's not going to work out.
Yep.
Okay.
Thank you.
Questions, comments?
Thanks for your presentation. We have been trying similar concept for years. I just want to predict 4 type of workloads. And last, we tried for at least 2 years. We are not successful. I don't know what's your experience? Like he said, it's not about one workload. One workload is fine. But, like in laptop or your system, you don't learn one workload. And what the problem we see is you predict something and you don't know how to back off. because, like you predicted, oh, I'm like bursty workload, but actually it is sustained workload because of something else. Then the whole prediction actually misfires. That's why it's important. It's not just one workload. It's just a mix of workloads. It's what you really want to do. Maybe server, your specialized servers is fine because you're only doing one thing. But into wider deployment, that's the big challenge we have.
In ByteDance, actually, we have some service running on the bare metal, and they are totally isolated. They don't share the bare metal with any other workload in our cases. So actually, the simplified case I have in the presentation is not unrealistic. It's real for at least for our case.
Yeah, it makes sense. Yeah. Thank you.
This might be more of a question about the literature of kernel auto-tuning than particularly the talk, but this slide is actually a really good example of it. I imagine some people have also tried to use non-statistical ways of doing kernel auto-tuning, and the first thing that I came to mind as an alternative when I looked at this diagram was just a PID controller, and I was curious, and I'm sure there's lots of reasons to use possibly machine learning over non-statistical techniques to use, traditional control systems instead. But what advantages does a machine learning provide that these traditional control systems are not going to be able to provide?
To be honest, actually, I don't understand, the PID controller stuff. Yeah. However, I do mention, there are some comparisons with the traditional one. I think the machine learning could have more opportunities than the traditional one. So, very in general, yeah.
Control the PID control variable. One control variable works. You have 15, 16 control variables. Then it falls apart.
Thank you. Thank you.
In your talk, you were mentioning that you would like to move that in the kernel. The only reason is to have access to more variables? That's only that? Or do you have other interests of moving all this phase in the kernel? Because I'm not sure that which kind of benefit that will provide you to be in the kernel compared to right now being in user space and using this kind of CSFS parameter, for example. Why would you like to go to the kernel instead of just staying in user space for doing your machine learning?
I think I mentioned here about whether we should use machine learning in kernel space or the user space. Let me see. Specifically here, so there are different pros and cons we need to consider whether we.
So, and when you say more real-time ends, what do you mean exactly? Kernel compared to being in user space.
By this point, actually, I mean, when we needed to make some decision, if we do that in kernel space, we don't have to going up to the user space and make a decision and get it back. So there is some latency. Yeah.
It's an hour, and then it's done, and you're not touching anymore your parameter. So, okay. I'm not sure to see the benefit of this real-time capture of the parameter compared to being user space. You can be in user space and being quite efficient as well.
I think you can think about the network congestion control. So all the congestions and connections will probably change within milliseconds or something. If we go back to the user space, I think that will possibly not that accurate.
Meters are changing in real time. So like you. it looks like the parameters are actually then changing constantly. So like it's not like you have a set of values, you set them once and you forget it.
I think for the
They can change in milliseconds time frames. Is that what you're saying?
I think for the congestion control, we definitely need to update the parameters very frequently, like the congestion control window. Yeah.
So towards this direction, I think it's hard to get if the web server is better than worse. For that, you need to do a lot of data massage to figure out that it's trending upwards, that in user space somehow. So and this is an expensive operation. So somehow you need to have this data in user space that you are going to consume in kernel space. Why not the other way around? User space.
Yeah, this is a good point. Yeah. Yeah. Yes, if we move, the machine learning into the kernel space, we also possibly need to transfer the data from the user space. Yes, that's true. Thank you.
We're running out of time, and thank you, Kong.
Thank you.
Technology. What's I don't know. You can try. For some reason. Okay. Arrows do work. Space doesn't. So you want me to ask them to remove the video and the chat?
So, welcome everyone to the last presentation before lunch. And my name is Ahmed Darvish. I work at Linotronics for 5 years now, mostly working on BSPs and kernel development and other things. And for today, I would like to actually talk about some of the things that we were working on in the last 3 months approximately regarding CPU ID and the open source x86 ecosystem in general. So the first thing is I would like to quickly review the CPU ID instruction for people who might possibly be not aware about it and quickly discuss its semantics. So the x86 architecture provides this CPU ID opcode, and it takes basically as an input a leaf, which is the main input of the instruction, and it takes something called the subleaf. And the subleaf is an optional input, and it takes it in the ECX register. So In x86, there is the common EAX, EBX, ECX, and so on registers, and the input is EX, and the optional input ECX. What it does output is information regarding the CPU and supported features. Runtime, of course, and the output format is actually a number of bit fields, and the representation of the bit fields depend on the leaf, and these output are in the 4 registers, the EAX, EBX, ECX, and EDX. The same register's output is also on x86-64. So traditionally on x86, if you have other instructions, there's something called extended registers. Not in this case. So even on x86-64, the output is still on EX, EBX, ECX, EDX only, and only that. It is available on all modern x86 CPUs. And by that, we actually mean x86 CPUs released on the last 25 years or more. So most of the software on the ecosystem actually assumes its availability. Technically speaking, Intel and AMD asks you to check some E flags, but practically speaking, it is available and most software assume it is there. Most importantly, it can run not only from kernel space, but it can run from user space. And okay. I guess I asked actually to make my slides full screen, so maybe someone is working on that. So. Okay, it's well. Okay, mysterious person, thank you. So. Okay, so then I should go on. So I just need to remove some disturbing toolbar here on my side, and I hope it does not break things. It's okay. So I was talking about the permissions, and I was saying that most importantly, the CPU ID instruction can actually and is frequently invoked from user space. So it is not a privileged instruction. Okay. The last thing, it is also, yep. Yeah, nice. Thank you. Who is doing that in the room? Or? Oh, okay, thank you. So thanks a lot, much nicer. So the last thing, it is a serializing instruction. So just for your information. So actually, there are some strange. I promise. So, yeah, okay, not bad. So there are some GCC and LLVM in strings to help you information. So there is actually a CPU ID count macro that it is provided at CPU-id.h. And CPU-id.h here is just a header provided by the compiler, just like var args over standard arg.h, for people who know that. Both also GCC and LLVM implement in strings called built-in CPU supports, and you can use that to query, does my CPU have, of course at runtime we are talking about, does my CPU have SSE3, SSE4, AVX, and other features? And these strings are also extensively used in the ecosystem. A caveat, this does not cover all the CPU ID bit fields. This only cover around 30 or so of the most important features on x86 architecture. So I would like to show you now a demo implementation of the instruction. It is not really that complex. This is an inline GCC, inline assembly GCC expression, and you see in blue, this is the CPU ID of code itself, and you see in orange the A, B, C, D. This actually stands for EAX, EBX, ECX, and EDX, and this is basically the output of the opcode, and this is where we tell GCC to marshal the output. Yeah. And the input is in green, which is basically EEX, and this is the leaf number as we discussed. And then there is the ECX, which is the subleaf number. By default, I will talk in more detail about subleaves, but by default, it is 0 for leaves which do not have any more subleaves. And if you actually disassemble this function, you will see in the disassembly, it is just 2 bytes, 0FA2, and that's it. So it's really not that complicated instruction-wise. I'm just bothered because part of my slides here are covered by a stupid toolbar, but it's okay. So if I continue the demo, there is here, I am showing this, listing the CPU ID in 3 leaves, leaf 0, leaf 1, and leaf 2. And basically, I am invoking the inline CC macro that I showed in the earlier slide. This is the invoke CPU instruction. And then I am printing the output, as I mentioned, from EX to EBX. And this is actually the output of this. It's updated here, but not here. That's my bad day. It's okay. Okay, now it's updated here. Yeah. So this is actually the output of the demo of this small program, and as you see here, there are some bit fields in the 4 registers. I am only detailing for demonstration purposes the first leaf, leaf 0, and you see in EEX there was a single bit field that was 16, which stands for, and you see it in bold black, and this stands for the maximum standard leaf. So basically, this CPU supports standard leaves up to leaf 16. There is something called extended leaves we will talk about later. And then the EBX register, the ECX register, and the EDX registers, these actually contains the vendor ID string. And I was running this in my laptop. So this is basically the genuine Intel string. And you see it in blue. I am matching in blue, green, and orange what stands for what. So that's it actually about the instruction, input, output, nothing more complicated. But the interesting thing is the amount of data that this opcode can provide you on the x86 architecture. So here I would like to show you some sample data to just get a feeling of the instruction and the return data and what does it provide. So here, for example, I am on the Linux. Yeah, it's still updates only here. Did this happen with everyone, or is it just me?
Just you.
Okay. So as you see here, this is the Linux command line, and on user space there is a really nice tool created by Todd Allen, and he has been maintaining it for almost 20 years. It is called Todd Allen CPU ID, or just CPU ID, and it is quite ubiquitous that it's actually in Debian. Even the package is just called CPU ID. So you just do an apt install CPU ID and you get it. And here I am saying, please, parse for me the information from CPU ID leaf 1. And here saying, okay, in the output register EDX, here are the number of bits and all the standard features. And for people who are aware, these are the same feature strings that you get. You see it in the standard proc CPU info on x86 and so on. Similarly, so I'm continuing the output and waiting for my slides to refresh. And and you see here the ECX. So the tool is so there was more data on the ECX register, more bit fields, and here there is also other features, SSE3, virtual extensions, speed step, and so on. So if I go a little bit deeper, and I'm still using, yeah, and waiting for my slides. So I'm still using the Todd Allen CPU ID thingy, and here I am saying, okay, please parse for me the information from leaf number B, and this time subleaf 0, and now we are beginning to encounter subleaves, and here it's saying that, okay, so this this leaf actually 0B on x86 usually lists the CPU topology. So usually, especially on advanced CPUs, there is not only like 2 levels of topology, there can be up to 6 levels of topologies. And this was an old development server in Unitronics. So at topology level 0, so you see I'm doing CPU ID subleaf 0, and here it is saying that your level type is thread, and this is, we are talking about hardware thread. So this is the hard logical CPU, Intel calls it hardware thread, AMD manuals calls it, it's hyper-threading. And here it's saying number of logical processors at 2. So this means I actually have hyper-threading on this development server. Okay? If there was no hyper-threading, the number of logical processors will be 1. So this is talking from a theoretical level, at the topology level, how many CPUs. Not across the whole system, but as a topology hierarchy. And then I'm saying, okay, please do the same, but for now, give me the subleaf 1. And here the output is for the upper topology level. And here, okay, the level type is core, and the number of logical CPUs is 56. If I actually continue and say subleaf 2, then it will tell me invalid. So there is an invalid marker, of course, so that you can navigate the topology. And the important part here is that in this development server, the number of cores is 56 times 2, 112. Yeah, and yeah, that's basically it. But please, of course, note that this calculated number of CPUs might differ from proc CPU info, because proc CPU info shows you the online CPUs only due to the CPU kernel, the kernel CPU hot plug. Might also differ from nproc or sched affinity, because both nproc and sched affinity basically tell you the number of available CPUs. So if you have also a container and C groups and so on, so the number will be less. So, and this is why actually in make files, you know, so people use nproc specifically. So I will go on quickly. Also, I'm trying to give you a taste of the data that's returned by CPU ID. So, and more specifically, the subleaves. And here you will see that the concept of a subleaves is most of the time used to enumerate hierarchical hardware structures. Okay, and on modern hardware there is a ton of such hierarchies. So, for example, leaf 4, it will tell you the deterministic cache parameters for the cache level. So another hierarchy, and then subleaf 1 will stand for level 1. Subleaf 2 for level 2, and so on, and subleaf 3 for level 3, the last level cache mostly. Then, for example, leaf hexadecimal 10, this is the Intel Resource Director thingy, AMD platform quality of service, and in these things there is like resource IDs hierarchy, and resource ID 1 is typically for cache segmentation at the L1 level, resource ID 2 is for cache segmentation at the L2 level, and so on. Yeah, and it goes on like that. So maybe I can then jump directly to leaf 1F. And leaf 1F, for example, it allows you to enumerate the entire CPU topology. This is actually V2, so this is only on modern Intel CPUs. And you can see that the topology on modern CPUs can go deep, actually. So we have hyper-threading, we then have cores, then modules and tiles, then dies, and die groups, and so on. So this was only a sample. So it looks nice from the start, but the amount of data that can be extracted from CPU ID is really huge. So far, up to today, there are 52 standard and extended CPU ID leaves. And we talked that actually some of them also have subleaves, so it's even more complex than that. The total number of bit fields is actually up to today, publicly known, is in the range of 830 to 850. And the reason I'm saying publicly known is that if there is a CPU vulnerability, usually a microcode update will then introduce a new bit that will tell you that, yeah, whether the vulnerability exists or not anymore, fixed or not. So, so this is why some of these bits are also only listed in security advisories and stuff like that. Yeah, a lot of them are also vendor specific. So yeah, we mostly care about Intel and AMD these days. And yeah, the data is actually scattered around 15 manuals or so. So there is, of course, the main Intel SDM with the main listing, but there is a lot of manuals which mention other bits. So, okay. So the title of, so this was only just a quick summary of CPU ID for people who might not be aware about it. So the real talk actually is standardizing such data. So first, why do we want to standardize it? And also the origin story of how did we reach today? So, and I will just see. So there is a lot of challenges today in how the Linux kernel is dealing with CPU ID information. The first one is actually possible future hardware designs. So heterogeneous cores might be a reality. We don't know, but given how the industry is moving, this might happen. For now on x86, all cores on a die group are actually the same feature-wise, but there is this known difference between P cores and E cores, performance cores versus energy cores. We don't know, we don't have internal information if this might change, but the rest of the industry is moving in that direction. And even Intel actually, CEO and such, had multiple public speaking engagements where he mentioned Intel chiplets, where you can have multiple nodes on the same chiplet, like 3 nanometers and 5 nanometers and stuff. So the industry, we might move into an extremely heterogeneous future. We are already there, but it might even move to a next point. Yeah, but I already wrote a disclaimer there that this is not based on internal information. This is just our interpretation of how the industry is moving so far. Second thing that actually is pressuring how the Linux kernel is, how the CPU ID data is represented in the Linux kernel is CPU vulnerabilities. And the first thing is live microcode updates are becoming more common over the time. And there is actually a lot of case studies from hardware vendor customers who are really happy about it. But in the case of a CPU ID vulnerability, this might mean that you can apply a live microcode update post operating system initialization, and then one of the CPU ID bits can appear or disappear. And this can be tricky depending on the CPU ID bit. The second thing is operating system masking. And we might need in the future, if there is a CPU vulnerability, and we know that that vulnerability, user space should not use that feature, there might be interest from Linux to actually mask that bit. Right now, AMD CPUs actually provide the capability of only being able to run the CPU ID instruction from kernel mode. And they give you the capability to actually trap the instruction. So there is a CPU ID bit, ironically, which can actually tell you if the CPU support only privileged CPU ID invocations. And in that case, we might actually move to a future where we can trap the CPU ID instruction and actually report it.
Thomas?
I'm sorry.
Intel have that ability since ID bridge, it's just not enumerated.
Ah, okay, nice. So it's private information, huh?
Sorry. Yes, for the call. Intel have had that since Ivy Bridge, and before Ivy Bridge, they also have some masking MSRs. The AMD one is actually an override. It's not a mask, so you can also make features appear with it, which we occasionally use for fun and games.
Yeah, thanks. And is it possible actually that we will want to at least provide the CPU features across like a Linux own thing instead of letting user space just run with CPU ID and do its thing?
There are some cases where that's necessary, and it's really, really, really slow.
So what we are asking for many years is basically give us a shadow CPU ID memory space where the kernel can write to, and that's what exposed to user space.
Oh, okay, nice. Thanks.
So they say, oh, it's too hard. Yeah, I mean, it took us only 20 years to get stable TSCs, so why?
Yeah.
Why are we expecting CPU ID to be fixed in 5? I mean,
So you got it from the source. So, so
at least on the hardware side, doesn't SEV have a CPU ID page in memory they pull out to send to the guests? So yeah. So if Intel is saying it's hard, we just have to point them over to the AMD implementation.
So, yeah, so these are, to get back in context, so these are actually the second challenges of how the kernel is representing CPU ID information now. The third thing is actually the existing Linux kernel code itself. So there is no central authority for CPU ID information. All the drivers just manually invokes, not all, a lot of the drivers manually invoke CPU ID everywhere, which is okay for now, but if we are moving again in the future to a heterogeneous architectures, then this will be a problem because now you are running on a CPU and next time you get scheduled, you are on a different one. There is a lot of ugly bitwise handling on the kernel recently for CPU ID data. Sadly, a lot of code does what you see here in orange in the second point, which basically just like read leaf one, do some bitwise operations, and it's quite ugly. There is it's not the worst. Let's call it this way. So there is also feature bits. This actually was it is still the main way in the x86 tree to check build the feature table and check features. Some of them is synthetic, but most of them actually has a one-to-one correspondence with the CPU ID bits, but they are incomplete. So they are there, but they are incomplete. Also, for people who do the usual cat proc CPU info, these flag names that you see, they are defined also at CPU features.h, but they are actually done in a very ugly way in some comment. And then there is a post-processing bash scripts that actually, bash or Perl, I don't remember, that actually generate C header from that. So it's, I'm not saying this to criticize anyone, of course. This code just organically grew since the original Linux 0.1. So it is the state of the world right now. So Linux kernel-wise. So so there were efforts from the x86 maintainers to actually start to clean up things a little bit, given all the challenges or things that people know that needs to be fixed. Boris actually, when he was back at SUSE, actually started some basic cleanups of the C99 of the CPU ID bit fields, which basically he added clean C structures with bit fields, and then the rest of the code can at least do that instead of doing the ugly bitwise operations. This was around 2018. Around 2000, just recently, some months ago, Thomas actually said, okay, he asked me if I can look into that branch and actually try to build an in kernel the CPU ID data model that can handle or can start to handle some of the challenges we discussed. It's actually a very long-term effort here. And what we basically want is some data model that can actually, of course, have leaves and sub-leaves, also x86 vendor filtering, so we need to know automatically whether this bit is Intel only, AMD only, or both of them. And also, we need to encode the name of the proc CPU info flags because sometimes they are different from the feature name. So there is a lot of interdependencies, and we tried. So I actually started prototyping some models. So just basic stuff, to be honest, some C structure stuff, and try to do it in a clean way. And if you see here, so this was like a representation of the multiple levels. Of course, I cut it down just to fit the slides. And you see I'm doing still the same ugly trick. For example, the SSE, the XMM3 here, this P and I is actually the name of the feature in proc CPU info. But at the feature level, the x86 feature flags, they are called XMM3. And marketing-wise, people call them SSE3. And there is a lot of these, basically. So we tried actually encoding the information in C as much as we can. And actually, like I iterated like 4 or 5 times, and I would go back to Thomas, and we tried to make it work. But there was a point where we actually realized that we can't just do it at the C level, honestly, at this stage. Of course, in the end, the information will translate to some C representation, but we need some form of a machine-readable format. And this machine-readable format can actually encode all the things we talked about, the x86 feature bits, the proc CPU info, the vendor filtering, and even more things. So in Prague, I guess, the EOSS, the Embedded OSS conference, Thomas also met with Andrew Cooper, main Zen maintainer, and they actually prototyped some initial data formats. So not that this only fits the Linux kernel, but also the Zen hypervisor. So as a starting point. And not only that, but to make it also extensible enough to support other software, and not just at the kernel level. So for example, at the user space, I mentioned the Todd Allen CPU ID tool, so we even want to target that. So, okay, we want to build a CPU ID database, right? So it should be easy. So we had to evaluate actually several languages. Mike, please.
So you might mention that we ask around if there is machine-readable information available at the various vendors. So there is, the answer was from both big x86 vendors. Yeah, we have some PowerPoint and some Word documents, maybe PDFs, and
that machine readable.
yeah, it's all machine readable. Still need to have to parse 15 PDFs to get all of the information. So it's implemented in microcodes. I can decode it from there. Yeah, sure, great. Next time.
So as we said, actually Thomas asked, and so there are some things, but not ideal. But so we want to actually represent this information. And remember when I said that there are 850 bit around 850 bit fields, right? And each one has attached information about the feature flags the CPU info, other usage needed by Linux, other usage markers by the Zen hypervisor. So it actually is a complicated task. And what we ideally need, so I talked at the start of the slides that the CPU ID data, especially the subleaves, are deeply hierarchical, right? And that's just a feature of modern hardware in general. So we needed something that can represent an extensible annotated tree. So extensible tree is understandable. A tree structure is also understandable because of all the hierarchies under each leaf and subleaf and so on. And I really evaluated, given these constraints, JSON, YAML, TOML, S expressions, the Lisp thingy, and XML. And it was only XML and S expressions which we were able to do a hierarchical structure and do annotations on these nodes. Okay. So, for example, for YAML, you can, of course, do a hierarchical structure. But the moment you want to add annotations per node, you need to encode that annotations as part of the tree, as part of the hierarchy. Okay. And this led actually to an explosion of vertical lines per node. So you would look at one node, and then you will not even be able to understand your position in the file, and so on. So, and the same for JSON. TOML actually was even worse. Its support for hierarchies was extremely primitive. And it was only XML which was able to have this tree structure, of course, but also with annotations per node, which is something like attributes. And also S expressions, because actually you can have a one-to-one mapping between an XML, even a really complex one, and S expressions. So even when XML actually was introduced, the Lisp guys showed it just a little bit noisier S expressions. So now actually the filtering is, okay, we have JSON, YAML, TOML, S expressions, XML. Now it's filtered to S expressions and XML. And from there, of course, the XML ecosystem won, even though the S expressions actually looked nicer, even for, especially for someone like me who like Lisp. But in the end, there was the benefits of the XML ecosystem. You had a great schema language, whether you want to use RelaxNG or XSD or whatever. You had extremely powerful, and I will show you some examples of query language and a transformation language. And the rest of this talk, I will show you extremely, I will show you extremely beneficial usage of such XML tree. So this is actually some of the sample. Oh, I got time moved quickly. So this is actually one of the samples. So what I did is, okay, we agreed on a representation for all the leaves, a schema, of course. So we really prototyped multiple schemas until we reached what we believe is the optimal schema for our use case. And in that schema, there is something like that. And as you see here, there is the leaf ID and the leaf ID. And the leaf ID is 1. And from there is the subleaf ID 0. And then this is a description of the output registers. Okay. So you see here the EAX output register, and these are the descriptions of the bit fields within the EAX register. And from there you can see that here is bit 0, and here is the ID and a short description. And this bit is actually supported by both Intel and AMD. And on the second field, it's also the same, and the length of the bit field. And we did that for the 850 bit fields. So each bit field in the database that we built actually has this level of detail. Okay, that's the first part.
What does the vendor mean in this case?
what does the vendor actually mean here? Does this mean that like you have to do a vendor check before you read this bit, or does that like which vendors this bit might appear on?
It's supported by that vendor, which means that this bit actually in Intel have the CPU model ID string. And it's the same on AMD, but outside of this, we don't know what its interpretation. And if this only was like one line Intel without the others, then to our knowledge, this bit is only interpreted like that for Intel CPUs.
Okay, so it's more documentation than to say before you read this bit you have to do a vendor check or something.
I mean, we will talk about generators and we can utilize this information, but so far it is documentation. Yes.
The idea was that we want to enable the people like running web pages on CPU ID and whatever or user space tools to be able to filter on that. But for in the first place for the kernel purposes, it's mostly documentation right now. But we choose XML on purpose, so even people who want to do web pages with extensive description.
Ah, 5 minutes. Okay. So, and then there is also here another XML, actually a continuation, and you see that we also have usage hints for the Linux kernel and the Zen hypervisor. And here, for example, we say that this bit is the x86 feature bit, and the proc command, the proc CPU info actually exists for that bit. So, and for the Zen, we have similar attributes. This is a more complicated case. So it's also, we don't also do vendors, we also do hypervisors. Like there are some bits which are only supported by KVM or Zen and so on. So we also list this to the best of our knowledge. This is a nice case of the topology we talked about. So here, this is actually leaf1f. This is just Emacs, the name of the file there. And you see that, okay, the field, domain level, blah, blah, the field. And you see here, these are also the possible interpretations for that field, to the best of our knowledge when this was written. There is, as I mentioned, all the 830 plus bit fields are actually extensively covered. I also wrote generators for multiple components. And the first generator was actually a C header file generator, which we plan to use at a certain point in the future, also in the Linux kernel. So we do not want to have this tool as a build dependency of the kernel. So we don't want to bother anyone with XML and stuff like that. So the expectation is that the output of this tool will be committed, and then the maintainers will inform some discipline that if there is any bug fixes or updates, you actually update it on the upstream. So the Linux kernel will be our downstream, and the Zen hypervisors and other areas. And here, for example, I'm using XSLT, and yeah, I only have 4 minutes. So, and XSLT is an extremely powerful transformation engine because XSLT basically give you the XML tree, and then you can have total control on it. So, for example, this is just a very quick example, the second line. Here I am saying in just one line, go to the XML tree, go 2 levels deep, and then give me the local name, filter this by all the elements which start with bit, then then extract the ID attribute of that element, then take its length, then actually give me the maximum in the whole file. Okay, and all of this is actually in the second line. So it's extremely powerful. I was actually personally surprised. And so the generators are very small. So the C structure generator are 150 lines of stuff like that, declarative language. There is also another generator. This is basically the tool that this is just an interface, but internally, as I mentioned, we have the XSLT transformers. And this is also another generator which I wrote for the Linux kernel KCP-ID tool. It's a small tool under tools ARC x86. And originally there was only 200 fields or so covered. There is a patch series, which I will send after this talk, which actually covers the entire 830-bit fields that are scattered over actually these 15 plus documents. So, and this is another example also of the listing and all the bit fields and so on. This is also an example of the generated header files. So this is, so this is leaf 4, sub-leaf 0. It's in the bottom, the name of the structure. And this is the EX, EBX, CCX, and so on. So most important for me to notice is that this is extremely flexible. So we actually spent really good time internally iterating to make sure that we have a strong foundation. We can generate whatever we want. So seriously, so not exaggerating. I will send an announce to the Linux kernel mailing list after this talk. This will be about the project. There is a URL there, which will also be, for now, a redirect to the GitLab project, when you can also talk with me, and I can also show you some nice demos if you want after the talk or tomorrow. That's it from me for this talk. So if there is any final questions or...
I did not understand how to add a new CPU ID. Suppose I have to add a new CPU ID feature. Shall I send to that website, or how does?
Oh, you mean the project? Where's the
project? How do I add a new one?
Yes. So this is actually just a redirect to the GitLab project, and it's a project hosted on GitLab.
So I send a pull request or something to do that?
Yes. So if people in the kernel want to also send the normal patch over mailing list, it's also okay.
So you can send to x86 mailing list, and you can pick it from there?
I didn't get the final approval, but this is the plan. Yes.
Yeah, so the thing what I want to do in the future when this is really available, and it is, so everything which comes new into the kernel and has a new CPU ID, whatever thing, go there, update the database, and generate the data structure for you. Let it generate a data structure for you, and then use it in your code. Because I'm so tired of decoding all these 50,000 different unreadable, unparsable, incomprehensible macros. It makes my brain boggle. And just these data structures are so nice because they tell you what it is. Somebody claimed recently that the macros are more efficient. This is total bullshit. I tried it, and actually the text size generated with a bit field-based data structure was roughly 15% smaller than the macro mass created one, because the compiler can't even look at it correctly. So because it's too late to actually think about optimizations. You wanted to say something?
No.
Okay.
On ARM64, we have an in-kernel table, not as advanced as this, but one of the things that we have there is a bunch of information on how to decode the field. So, for example, if you have a field that's a signed field or an unsigned field, if it's packed and shifted and that sort of thing, do you have that information today, and is that in scope for future?
Basically, yeah, all of our bit fields are just unsigned, so we don't have any typing system regarding the actual bit fields. If there is a need, maybe, but we assume that, I mean, the bit fields themselves actually are, like C-wise, the bit fields are like a subtype of U32, so there is...
Oh, sure. It's just that one of the issues that we found, which is why on ARM64 we introduced something very similar, is that people were unpacking these bit fields incorrectly. So they'd extract the correct bits, but then fail to do the thing to convert it to the correct type to interpret it correctly. And I'm not sure if that's a problem for you or not, but I'll pass
Why would they...
For some of the leaf, it's a problem. We still have to figure it out, but that's the basics. So the most important one that I wanted to have, it's 6 bits here. and not I tapped some macro and got it wrong, the magic constant.
I was just going to say, off the top of my head, I'm not aware of any signed data in x86's view here, but not beyond the realm of possibility to add information like that.
Good. Yeah, you have it. So you have a unit factor on it. That's true. It's not it's in the documentation. It's not encoded right now, but that's something which can be added on top easily.
Guys, we are running out of time a bit, so sorry.
But yeah, we have a break, so I'm available if anyone.
So
wants
if
to-
anybody wants to continue and they don't go
Yeah,
to
yeah,
lunch,
of
yes,
course.
it's up
Yeah,
to you.
yeah, of course.
Thank you.
Thank you very much.
Thanks a lot.
Wanting to translate my current advice to them is well, you know, we have a problem. Well, no, we just take the word in English. Yeah, it's our approach. It's a French word.
They stay on.
I'll get a mic at this point.
Yo creo que así como todo el trabajo.
Hopefully I didn't destroy anything by using less.
Okay. Hopefully I didn't destroy anything by using last year's procedure on this year's BBB, but anyway, here we are. But we have slides now, so that's a good thing. So we're here to talk about hunting Heisenbugs, and these are kind of like, it's kind of the Impressionism school of software engineering. Because in both cases, with Impressionistic art and with Heisenbugs, the closer you get, the less you see. And in case of Impressionistic art, I guess that's the intention. In the case of Heisenbugs, that's frequently considered a problem. And so we'll talk today about ways of solving it. Now, this is still very much more an art than a science, but we should at least get some techniques that may be helpful to you. Okay, we'll go through a few topics here. Of course, one important thing at the very end, if hunting Heisenbugs is great, but avoiding them is even better. So, Heisenbugs at one time in my life, like 30 years ago, were horrible life-changing experiences, but after a while, you kind of get used to them. And so, Tuesday, right? What Heisenbug do we have today? Large fleets are actually pretty good at detecting Heisenbugs. This is something that's just straight mathematics, but it can be surprising sometimes. If we have a 100,000 or 10,000 year bug, that's 100 hours on a million system fleet. All right. So if we have a 10,000 year bug, it's happening every 100 hours on a million system fleet. I'm not allowed to tell you how many systems my employer operates, but I'm allowed to tell you that it's at least 1 million. So if we have a 10,000 year bug and it's something that's consistent, like a warn-on, I mean, if it's memory corruption, it just does a different thing every time, well, whatever. That could be a hardware failure, wouldn't know the difference. But if it's something that causes a warn-on, we will see it and we will decide what to do about it. We may decide this is something that is more risk to fix in this release, so we may just do a fix and upstream and let it come down later. Or we may decide we're going to fix this bug, but we will see it and we will decide. Okay, so how do we detect it? Well, console output is a common one, as it is anywhere. There's a lot of automation that collects that up. Of course, you can use BPF. You can put a kernel patch out there to detect things, but that's a real pain because people like Chris Mason, rightfully so, ask you lots of hard questions about a debug patch being shipped out to that many machines. And you could potentially set up a kernel debugger. So what I'm going to do is I'm going to talk about a bug that Chris asked me to fix a few weeks ago. It was actually very welcome. I can't remember what I was working on at the time, but it was extremely frustrating. So it's kind of like, yeah, Chris, I'll take a look at that. My problem. And it was one of these things where there was some console output, and it was late in the afternoon, so I looked at it, went to bed, woke up knowing what the problem was. It was a fun process. Of course, it would have been more fun had it not been my bug I was fixing, but you can't have everything. The thing was, this was one failure per 4K systems per week, right? Which was enough to say, all right, we're not rolling this release out any further. That's 70 years, single system, MDPF. Mean time to failure, MBTF, or between failures. Mean time between failures, MTBF. So, but it was an easy fix. It's a fix, so we can send it immediately. If it had been an enhancement, it would have to go upstream first, and then we bring it down. But fixes we're more lenient on. I sent it off. Ingo took a look at it and says, let's see. Well, it's a regression, but 70-year MTBF, we can wait till the next merge window, right? It's kind of like, yeah, that's fine. Now, you could potentially set up a kernel debugger, but a million instances of KDGB, I haven't figured out any way that could possibly be anything resembling fun. Depending on if you're masochistic enough, I suppose, but that's going to be a real pain to manage. And if you have a fix, waiting for that fix to deploy through enough machines to detect the problem is also not going to be particularly fun. And so really you want a better way than just doing that. And of course, there have been better ways for a while. I'm doing a lot of summarization here. Now, one thing you may ask, well, wait a minute, I don't have a fleet. What are you talking about? Get out of my face. I've only got 15 systems. I've only got 1,000 systems. What is this garbage? Well, I was hunting Heisenbugs for a long time before I had a fleet. And so maybe you guys are in the same situation I was in the early 90s, where I think Sequent had at most 6,000 machines, maybe it was 10,000 machines out there at the peak, at its peak. But we still had to hunt Heisenbugs. And the other thing is that my employer's fleet is a rather small fraction of the total Linux kernel install base out there. A guy named Dave Rusling told me in 2017 there were 20 billion. That's billion with a B, as in 10 to the 9th, and 20 times that Linux kernel instances in the world at that point in time. It would be good to have fewer things just kind of failing randomly. So it'd be really nice to fix some of these problems, because you think they're happening a lot on a million systems, try 10 billion, right? Now, we do have hardware failures masking many of those, and there are a lot of appliances and other embedded systems that just sort of reboot themselves if anything bad happens, so you might not notice. But still, the other thing is, whether we like it or not, whether we approve of it or not, the Linux kernel is increasingly being used in safety critical applications, and has been for more than 10 years. Now, as far as I know, I hope it's not being used for like avionics. For avionics, they tend to have very strict coding style guidelines. In fact, the last time I had anything to do with that, if you wanted to add an if statement, you were going to be spending a lot of hours in meetings justifying why you needed that if statement and why you couldn't do it some other way. Because that if statement was going to increase the complexity of the program and make it more difficult to verify. Memory allocation, forget it. You do not do memory allocation, certainly not once things have started running. At initialization, while the plane's still on the ground, okay, maybe, but not otherwise. And the thing is, though, that in a lot of jurisdictions, I don't know about this one, but there are some other jurisdictions in the world, where if you have a mechanism that might include a computer and might be running a Linux kernel, if it does what it's supposed to for a test spanning some number of years, 5 is the one that was relevant in the case I know about, certified safety critical. The Linux kernel can easily do that, easily. So we'll be continuing to see the Linux kernel being used in low-level safety critical applications for a long time. And well, I think it'd be good to get rid of some of the bugs, even if they don't happen that often for safety critical things. All right, so what's the key technique here? Well, first off, why is this thing a Heisenbug? Why do we even call it a Heisenbug? Well, because when you add debug, it disappears, right? That's kind of the definition. Well, and the reason for that is that the bug is often timing dependent. And if you add debug, you're changing the timing and you may be masking the bug. Now, sometimes you can add the debug and make the bug more likely to occur, but we don't remember those quite as well as the other case, right? Yeah, it's one of those things, you know? And so slight changes of timing can reduce incidents. And one way to deal with that is to reduce the MTBF. In other words, increase the rate at which the bug is occurring. This always feels kind of backwards when you're debugging. You want to try to make the bug go away. But in this case, if you make the bug happen way more often, you can make it so you can add the debug and not make the bug go away, right? So figure out why it's happening, make that happen more often. Okay, well, how do you do that? And there's another motivation for this. And in my case, for my current job, you'd like to be able to run a small test on a small number of machines, like maybe a 1-week test on 50 machines, and have some assurance that you've gotten rid of a lot of the bugs that would be seen on 1 million machines. All right, that'd be convenient. Well, if you do the math, that means that the MTBF on the test machines had better be 6 orders of magnitude smaller than the MTBF on the production fleet. 6 orders of magnitude. The funny thing is, in many cases, that's easy to do. Not always. I mean, sometimes life is hard. I'm sorry, this is more an art than a science. But there are cases where you can do some fairly simple things and get many orders of magnitude decrease in MTBF, and thus turn the Heisenbug into not a Heisenbug. We'll talk about a few. Okay, so how do we really do this? I've been giving the sales pitch up to now. Let's get some real stuff or something. What we're going to do is we're going to leverage the philosophy of my old high school track and cross country coach way back in the day. And our practice sessions were tough, right? So we were running 2.5 mile races in cross country, and also eventually turned into 5,000 meters. You know, some fool French measurement system came in. I don't know. Anyway, the thing was that the race days were the easy days. The practice sessions we did were much, much harder than a 2.5 mile or a 5K run. And we do the same thing here. This works for computers as well. So one of the things that happens, since many of us are focused on the Linux kernel, if you go and take a look at the utilization of the Linux kernel in the system you have, so we're going to talk about the kernel non-idle utilization, all right? It's unusual for that to be above 10%. I mean, I'm sure there's workloads where it is, don't get me wrong, but in many cases in production, the actual kernel execution time, non-idle kernel execution time, is small numbers of percent, maybe even less than 1%. If you talk to an application person, that's the way life should be. That's what God intended. Because they want to run their application, and as far as they're concerned, the kernel is tax. They don't want to pay it if they can avoid it. So they're going to work hard to make it so the kernel is not running much of the time, which is really good for us kernel guys, because that means that we can get a 1 to 2 order magnitude reduction in NTBF just by making a test that runs the kernel all the time. Right? So they've got something, they exercise the kernel in a certain way. If we can make it so that we're doing something sort of like that, but only running the kernel, we get an order of magnitude or 2. And that's one of the things RCU torture majors in. It's a kernel module, and its user space is, the user space is a root directory and an executable, a small executable, and that's it. All the rest is kernel. And so one anti-Heisenbug, so if Heisenbug's from the field of physics, it's really the observer effect. It's has nothing to do with quantum physics or anything at all. It's really just the observer effect from classical physics. But the name is there and it's stuck and it's kind of fun anyway, so why not? So if we're going to have Heisenbugs, we got those from the field of physics, whether classical physics observer effect or real Heisenberg and certainly principal Heisenbugs, doesn't matter. Either way, we're going to have physics give us an anti-Heisenbug, all right? And one of them is to increase the workload intensity. We increase the intensity of the workload, and what that means is going to vary depending on the workload. But if we increase the intensity, we'll decrease the MTBF, and we may get to a point where we can actually put debug in and have the thing not go away. In the case of chasing bugs in the kernel, just make it so the machine's running nothing but the kernel, hammer it hard, make it only run the kernel, and you should get an order of magnitude or 2. So this is kind of a special case of testing suspicious subsystems in isolation. In this case, the suspicious subsystem is the entire kernel. But you can do better than that. You can focus on parts of the kernel. You can also sometimes just configure the application so that the work it's doing is trivialized. Maybe it's doing some huge database stuff with massive disks. Okay, we'll make it use an in-memory file system and have a very small database. Maybe that'll work, right? And then you get that stuff. Now, at that point, you lose the disk I/O. But again, based on the workload, you can look at what the suspicious stuff is and try to focus on that. One thing you do is take traces from the application and have a tool that just runs those traces against the kernel, presumably using a lot less CPU time than the application did. And that's one way of increasing intensity. One thing is to run more CPUs than you would in production, have more memory, do more I/O. There's a bunch of stuff, depending on what things, where are the failures happening? Are your failures funny SMP things with CPUs? Maybe add more CPUs. Maybe add more sockets. Sockets increase latency, all right? Okay, so the key thing is, you want to ask yourself, what's caused trouble in the past? Now, this is backwards looking. We'll get to the forward looking a little bit, but let's start by looking back, do the easy thing. What's caused trouble in the past? And your anti-Heisenbug in this case is look for and promote trouble. Again, this is kind of a counterintuitive. You're debugging, you want things to work right. But to get past this phase, you have to do it backwards and make it worse. You make it so bad that your debug actually does something for you, right? The other thing about this is that if you can make it more intense and make it happen more often, when you find a fix, you don't have to run anywhere near as long to have some confidence that fix actually is changing behavior, maybe even really fixing it. Statistically, of course, it's not possible to prove that you fix the system, but you can get some level of confidence that you decrease the rate of occurrence by some number of orders of magnitude. This is the real world, after all. What can I say? Now, you got to be a little careful When you increase the intensity, you also increase the number of delays normally. You got scheduler queuing increases, you got more tasks maybe if you did that. If you cranked up the number of CPUs, you might have more lock contention. You might have memory contention. And there's these things you might run into, soft lockups, RC CPU stall warnings, things like that, And if you're trying to trace a bug, having that tell you, by the way, you increase the intensity really high isn't really what you want. You can disable them. And that's one way to look at it. But let's first take a look at what this is doing, because it gives us another anti-Heisenberg bug if we look at it properly. So this is in theory. This theory is really violently abstracted from anything in reality. We're assuming MM1Q, we're assuming kind of exponential arrivals. No matter how many people are in the queue, the chance of an arrival showing up is random. The servers get, the things that pull stuff off a queue happen randomly, totally random, just the exponential distribution. And there's only one queue. And the queue can be infinitely long. Other than that, it's perfectly realistic. And what you can do is, the reason theorists like this so well is it's got a really nice closed form solution. I mean, 3 pages of paper, you can derive it from almost nothing else, and that's wonderful. Probably fewer if you know math better than I do. But that's what you get. Okay, so on the bottom, we're looking at the utilization. How heavily we're using the system. 1 says we're pushing it right against the wall, I can't do any more. 0 says we're doing nothing. And the latency is in terms of number of people ahead of you in line, kind of. Okay, so if 0, there's nobody there. So if you show up, you're the first one in line, guaranteed. 0 people ahead of you in line. At the far end, if they're just being slammed, everybody's ahead of you in line. Except that there's an infinite number of people. So this looks kind of exponential. We should be so lucky. You see, an exponential curve doesn't go to infinity until you go to infinity. This thing goes to infinity at 1. That thing just goes straight up, Yeah, something like that. It's utilization divided by 1 minus utilization. So yes, it goes right up there. Okay. Yeah, so the latency blows up at full utilization. This is a little bit unrealistic. This is theory, so we can do a little bit better than that. We can, if we add a k at the end and say that our queue can be at most a certain length, and if somebody shows up and the queue's full, we throw them away. This is kind of like a hospital. You only got so many beds. Sorry. I'm sorry, that's the way the world works. I didn't say you had to like it. Usually they send to another hospital, but sometimes I don't know what they do. But in any case, that's where this model came from. That's the real world thing that led to this particular model. This one's a little more obnoxious, and it has a kind of a cases solution, but this is what you end up with. Now we've got our infinite thing showing there going up to nowhere, but the thing is, if you only have so many elements in your queue, you can, if you're lucky enough to get in the queue, that's the problem in this case. I mean, if you get in the queue, you wait for the length of the queue. Up here, of course, your probability of actually getting in the queue is quite low, as some people who get health problems at the wrong time of year can attest. And so it flattens off the same time, but still, you might need to adjust your timeouts, because 10x your normal latency might cause problems. But that's something you can do, right? You can adjust the timeouts, you can disable RC CPU stall warning, there's a sysfs thing to do that, and so on. Just be aware that you may have to. Another thing you can do is strategically inject delays. The key part is, I mean, before we're talking about intensifying one part of the workload, but that might not be possible. I mean, it may be as intense as it can get, in which case sometimes you get the result by de-intensifying some other part. If it's a race condition, you may be able to make the race condition happen more often by making the vulnerable part of the race condition take longer time. U-delay, it's a wonderful thing. Now, some examples. I mentioned multi-socket before. If you're going to run normally in production on a single socket system, which my employer is mostly single socket, then running your testing on a multi-socket system will inject delays, and you'll find more bugs and have a better chance of it working better in production. RCU torture actually, we'll see some stuff, slides where I talk about this some more, but RCU torture actually will inject delays on some of its scenarios to promote race conditions that have been troublesome in the past. In the old days, back in the 90s, we would just take different CPUs running different speeds and plug them in the same bus. And for certain types of race conditions, the clock frequency ratio gives you that much of an increase in the probability of bug happening. We could get up to like 3-to-1 clock ratio. Now today you should be able to do that straightforwardly, although the systems have a tendency to grab control from you and make the clock be what they want, regardless of what you're doing. You have to work a little bit sometimes to make that work. Plus, it's difficult to automate, so I've tended to avoid it. Plus, guest OSs don't. There may be a way of doing it with the guest OS, but I haven't found it yet. So the key thing about RSU is that RSU has to wait on CPUs to get to certain places, and in some cases threads as well. But if a CPU is offline, RSU doesn't have to wait on it. And if the CPU comes online after it started its grace period, it doesn't have to wait on that either. Right? But it's okay. I mean, if it waits on a CPU, it doesn't have to, as long as it does something, that's all right. The key point is that RSU has this combining tree data structure that has that allows it to reduce block contention and still see a global state change. And it's really important that RSU be consistently clear on whether or not it's waiting for a CPU up and down that entire structure. It's a really bad idea for the upper levels to think it's waiting on a CPU and the lower levels not to. In that case, the lower levels will never report the CPU doing anything, and you'll wait forever on that grace period. And that can be frustrated. Take my word for it. Or you can make it happen yourself if you want to. Okay, so the way that looks, normally, I've abbreviated here, the ABCHO is apply buffered CPU hotline hot plug operations, and IBCWE is the initialized CPU waiting bit mask. Normally, those happen really quickly. It's just goes through and grabs locks on every 16 CPUs and goes to the CPUs, does something, goes to the CPUs again and does something, and that's going to get done in maybe 10 microseconds, probably faster than that. Whereas a CPU hot plug operation normally takes hundreds of milliseconds, maybe even seconds. And so normally there's races that just aren't going to happen. And so there are some things that stick a big delay between those two phases of initialization to force CPU hot plugs to get done in that time so we can see the problems, the bugs that would be exposed by that. Okay, so insert strategic delay as one way to do it. The issue here you may object is, well, I have to know where to put the delay, so I have to know where the bug is, and that's true. But a lot of times, you wrote that concurrent code, you got some idea, you might not want to admit to it yourself, you might really be in denial, but you have some idea where, the part of the thing where you kind of got tired, didn't want to go any farther, or the part where I think this works, that's the part you put the delay in, all right? Or you try to explain it to somebody, it's a place where you have to get really complicated and they're going, what are you talking about? Put the delay there, all right? So it's straightforward. That doesn't always work, but it's a good heuristic. Counting near misses. So we'll get back to the airlines again. We talked about them for safety critical. The U.S. Federal Aviation Administration requires reporting of near misses. If two planes come closer to each other in flight, the pilots of both planes are required to file a formal report about the incident, and it gets investigated. The reason for this is that near miss was unintentional, and there's probably some problem that caused it to happen. But there's empty chairs over here, by the way, if you guys are tired of standing, and there's some around here too. But if you like standing, don't let me get in your way. The thing is that near miss may indicate a problem. And the problem didn't cause a collision this time, but it'd be good to fix the problem before it does, because and the same thing could do with software. If you can find some indication that there was a close call, then that means you can more quickly evaluate commits, configurations, and so on. If you're bisecting, that means you may be able to run shorter runs and make the bisection happen faster. And especially if you got an alleged fix and you can rely on the near miss counts instead of the actual problem counts, you may be able to spend a lot less time verifying, validating, and still have some confidence you reduce the MTBF of the bug by whatever amount. And in RCU, we have a near miss counter. It turns out that the thing we have, normally what happens is RCU torture does a call RCU, and then when it gets the callback invoked way over here, it says, okay, change of state, right? So we increment a counter, and then the readers, if they see the counter advancing too far, say, we had a problem. The thing is that the reader detecting an error, I suppose the RC reader isn't actually erroneous, it's detecting the error, but sometimes you got to blame the messenger, Sometimes you got to shoot that messenger. In this case, we have to have that full span for it to detect it. The counter had one value and had to go way over here to get the other value. Now we keep a counter when we start a grace period. It counts when the grace period starts and when it stops. If we sample that counter as well, then we can detect a near miss, right? And a correct RC reader would not see any of them. Now, the thing is that grace period counter stop is not synchronized. There's no memory ordering on it. So we might see a near miss that's a false positive. And the way that RC torture handles that is if it sees one near miss in a run, it says, yeah, whatever. But if it sees a bunch of them, it says, you know, we might have a problem here. In this case, the cool thing about this is the near misses are like 2 orders of magnitude more frequent than the actual bugs when we have problems. And that means way shorter runs, you know, and that's on top of the 1 to 2 orders of magnitude running the kernel solidly. So that's not all the way to 6 orders of magnitude, but we're at like 3 or 4. So that's getting there. So count near misses is a good anti-Heisenbug when you have software that has some indication that things got close. So we've talked about making rare events happen frequently. We'll look at utilization. We'll go through a few other ways. And then at the end, we'll look at the nuclear option. Okay, this is the same queue we had before, the finite one that didn't blow up to infinity, but just came to the things. And we've got a state transition showing we're going from one state to another. And what's happening is the queue is growing in length. At the far side, the queue has 0 elements in it. At this side, it has k. We were calling kb 10 earlier. We'll use 10 again. And the lambda is just the probability of, or the rate of getting another element. The mu is the rate of removing an element for a queue. All right, and why bother? Because we're going to plot probabilities of being in those states. So now you know what the states are. We're going to choose k equals 10 again. And now, if we have the utilization equals 0.1, 10% utilization, which is high utilization for a kernel in production, right? If we have that on this queue, then the probability of having 10 elements in the queue is 10 to the minus 10th. 10 to the minus 10th power. Very small. If we can increase the utilization to 90%, 0.9, we get 9 orders of magnitude increase in the odds of being in that state. 9 orders of magnitude. All right? Again, this is kind of theoretical, but the effect is real. Now, how many queues do we have in the kernel? Well, the networking guys have lots of them. I've got some for callbacks, but RC doesn't care how many callbacks are in the queue, really. So, but it's not the only thing there, all right? So, again, an anti-Heisenbug, that was kind of a double take there. Anti-Heisenbug is swamped queues, but it's not just queues. This applies more broadly than just queues. It applies to anything that has a probability distribution, kind of like what I showed. So let's go back to 1993. We were redoing a memory allocator, this was a simple thing. It's a 32 bits. You'd be amazed what murder you can get away with a memory allocator on a 32-bit system. It doesn't work at all today, okay? But we took full advantage of it back then. And it was similar, though. We had per CPU caches, and we wanted to work hard to make sure that you normally just went to the per CPU caches, then as now. We had a global cache, and when we added NUMA in the mid-90s, we had per node caches as well. And then eventually you would take the blocks and put them back into pages, and eventually you'd be able to take the pages and plop them into a 2 meg region, which you then free the physical memory, and eventually you could actually free the 2 megabyte virtual range. We worked really hard to make sure the system stayed way over there. Really hard. All right. And this is actually a similar structure to that queue, right? You have a really high probability of being over there, a low probability over here, you move up and down. I mean, the state space of a memory allocator is much more complicated. You got stuff going around there, but you can kind of project it onto this simpler diagram if you want to. And that turns out to be useful in this case, or would have been useful had it realized it in the mid-90s. So we had the big thing for Sequent in the mid-90s was shared disks for availability. So we'd have 2 servers, we'd fiber channel to connect so that each of them had access to the SCSI chains of disks. And the reason the memory allocator came in there because we were doing a distributed lock manager that was used for a certain database, so we could run a distributed database. And the nice thing was that if you lost a database server, you still had access to all the data. Of course, if you have something like this where you have things going down, you want to test the failure mode fairly often because otherwise it won't work when you need it. But for some reason, one of our customers objected to that happening on their system every evening. Right? Fortunately, it was right after backups completed rather than before. Okay. And okay, so what do? We send them a debug kernel, right? They were happy with that because that suppressed the error. We were somewhat worried it might show up in other places at other customers, maybe not, maybe before backups rather than after. So we figured we better take a look. So of course, then as now, you send a crash dump, right? You guys still do that. You distros, you guys work in distros, you still get crash dumps from users, right? Sometimes, maybe. Okay, maybe not. Anyway, that was what we did back then. The problem was this crash dump was a total disaster. I mean, normally if you get a stack trace, you expect a couple things. You expect the stack trace to actually have some functions in it. And you'd also like the function at one point of the stack to be calling the function at another point of stack in case there do have any two functions in the stack trace. These crash dumps did not have that property. It was just a total disaster. It's like, you know, I'm not sure what happened here, but it isn't what we wanted. So what we did was we replicated their workload as best we could. Various legal things meant they couldn't just give us their workload. So we had to fake it as best we could based on the description of it. And eventually, after some weeks, we got to where we could reproduce the problem in like 5 to 27 hours of running this thing. They managed to make it like that every night. And it took us 5 to 27 hours. The problem with that is it was take a long time to test an alleged fix. So, like tens of times longer. It was taking many, many weeks for that to happen. And finally, what happened is that we were getting a lot of stack traces to this thing, and the lines are just very visible. I clearly need to upgrade this. The arrowheads have lines going backwards from them, believe it or not. And eventually, we got a stack trace that had two functions in it, where one function called the other one. Yeah, yay, that's right. And that unfortunately, I figured my code. Can't have everything, you know. And it was this code, and this is kind of a reconstruction from memory. There's several reasons for being a reconstruction from memory. I'm still not allowed to look at that code for legal reasons. Those of you remembering the events of 2003 will know why. Anyway, it's one of these things where memory is scarce on 32 bits, so you don't align the 2 megabyte sections at 2 megabyte boundaries. So you have the case where you might have the little yellow arrow there between 6 MB and 8 MB. And if you divide that by 2 megabytes, you'll end up with the wrong element of the array, one element of the array for each region of memory. And that's not a big deal. You look at the pointer, and if the pointer is bigger than you are, you go to the previous one, like that code over here says. You know, straightforward. Unfortunately, compilers weren't quite as aggressive then as they are now. But the 8386 doesn't have that many registers. And the compiler says, hey, my registers are full, forget it. I want to fetch that thing twice, thank you. Yeah, oh yeah. You'll and so it would fetch it once, and it would say, oh, it's non-zero. So I go look at the other part of that if statement. Now it's null, right? Oh, that's less. Great, I'm in the right place. And life went downhill very quickly after that, and it totally accounted for the total memory just being trashed, which is why our crash dumps weren't doing us any good. In Linux kernel, use as any fix, you make that be a read once. Tell the compiler, get your hands off this thing. You don't know what you're talking about. Now, the problem is that we just used a volatile tag on the variable for that. But this is a rare event, and the trick was to make the reproducer make that happen all the time. In other words, to kill the fast path. Okay, and that wasn't too hard to do. I wrote a focus test. It's probably some of the most involved parallel code I've ever written, but it was, you know, it made it get down to where it was like every 12 minutes. So we had 3 things were happening. The existing test didn't find the thing. So as far as we know, the MTBF was infinite. Based on past experience, a lot of systems, but it handled a lot of different things. It found a lot of bugs of various kinds, just not this one. The stress test that we developed based on the user workload was 5 to 27 hours. It was based on the customer workload. It had a few large systems. It took a few person weeks to put it together. The affability was modest. I mean, it was that workload, but it had I/O, it had the scheduler, it had a whole bunch of stuff happening in it. It also put a heavy load on the system. The focus test, the MTBF was 12 minutes, under 12 minutes. I didn't bother doing stats. The longest thing I had was 10 and some odd minutes, so I said 12 minutes. I had to know the exact bug to write the test. The hardware, a very small system did it. A few CPUs and almost no memory. Took me a day or two to write the test. The applicability was probably narrow. Who knows? It might have caused other bugs, but it was clearly going to be mostly, it wasn't going to be anything with I/O because there wasn't any I/O happening. It was involved user space, no user space happening. And the impact was that system was kind of unusable while it was running the test otherwise. So there's a trade-off. You have to choose wisely here. But the big question, I said earlier, we were looking at what caused trouble in the past, and that's kind of backwards looking. What do we do about the future? Well, you know, a question to ask yourself, are your fast paths hiding bugs from you? And the answer is yes. I hope you're insulted. Well, you can be insulted if you want to. Be insulted. Maybe you'll be insulted enough to find and fix the bugs. That'd be great. But your fast paths are hiding bugs from you. And so one of the things in testing is to make those fast paths not happen. Of course, you might object that, so that's the Heisenberg, de-emphasize your fast path, make fast path not happen. One objection is, okay, what's happening to performance and scalability when I'm doing that? And the answer is bad things, okay? But this is a test. Besides which, you've got some workarounds. You can run on smaller systems. There's some stuff I do for RCU testing that Jan Horn said nice things about. I don't know if he's had any bugs with it, but he said nice things about it. That's restricted to 4 CPUs for that reason. You can accept massive contention. In some cases, that just, you don't care. You let the system run and eventually you kill it, and that's fine. The other thing you can do, surprisingly enough, is run code developed for old systems on new highly integrated systems. And the reason that works, in 2008, the system I was using had 4 sockets, 16 CPUs, and about 100 nanosecond compare exchange latency. You know, a single cast took about 100 nanoseconds to get a cache line from one CPU to another and back. In 2017, I had 56 CPUs in a socket, and that got me about the same latency for more than 3 times as many CPUs, which is not bad when you think about it. In 2017, the same system, if you used 4 of the sockets on the same board, you're about 400 nanoseconds. And today, there's a system that I got some time on that for that same number of CPUs is only on 2 sockets, and it gets 150 nanoseconds, almost 3 times better latency for the same number of CPUs. So it's also quite possible the fast paths we wrote 10 or 20 years ago aren't really needed today, or aren't needed as much. And it's also maybe that the contention that would have killed you in 2007 might be tolerable today, at least in a test system. The other side of that argument is the systems are getting bigger, so we may take it back in the shorts with more CPUs and more sockets. An 8-socket system of this size would probably have pretty nasty latencies. Of course, it would have a lot of CPUs. So newer systems handle contention better, so you may be able to just get away with disabling your fast path and not having bad things happening. I'm running out of time here, so I'll skip that. There's a bunch of other rare events that could happen. I'm not going to belabor them. But the key thing here, the big point is, if you have one rare event you make happen more often, you get a certain reduction in MTBF, a certain number of orders of magnitude. If you make 2 of them happen more often, it's multiplicative. So if you do 2 sets of 3 orders of magnitude reduction, you get 6 orders of magnitude, potentially, theoretically. I mean, in real life, bugs can do whatever they want, okay? But statistically, they sometimes are well behaved in some ways anyway. And this is something to try and might get you something useful. So an anti-Hesden bug is to do your testing and compare and combine the rare events, so they're happening all the time. If you have to choose, there's a lot of rare events out there, right? Choose the ones that have been causing the most trouble, or the ones that have had the most development most recently on is another one. A detect, then instrument. One of the problems you had the instrumentation, and that changed the timing. Well, a trick is, if you have something like an RC CPU stall warning that detects the problem, put the instrumentation in the beginning of the RC CPU stall warning. In theory, that doesn't affect the MTBF of the bug. I mean, yeah, you can have code side changes and it can still, but you've got at least some chance, right? So if we look just at the initialization before, if we spread out a cartoon of the full grace period, we initialize the grace period and we repeatedly do a force quiescent state operation, which looks for idle CPUs and occasionally whack CPU over the head and enlists help. And then after the while, we get done and we clean up after the grace period, and then we start another grace period or don't, depending on whether one's needed. Except that a few years ago, we just kind of got stuck there. It would go along and the task would be waiting. It hadn't woken up. It had a 3-second timer or 3 millisecond timer. The timer hadn't fired, and what's going on? The this was like hundreds of hours. I don't know what the MTBF. I know that it was at least high hundreds of hours. And if I added debugging, it got worse. So it took me a year to go around and look, do configuration changes and futz around with things and change boot parameters and so on. But I got the MTBF down to 300 hours, which was sort of reasonable. But I still, if I added debugging, it went away completely still. And the thing was, the RC CPU stall warning that detected it, suddenly it got better and went ahead after that. The actual warning code itself kicked the thing and made it happen. So the trick was to, again, put the debug in the RC CPU stall warning at the beginning, and then we could dump out the state and find the bug. In this case, what we did was we said, hey, this timer, it was in timeouts, interruptibles, scheduled timeout interruptible. There we are. I might get it right one of these years. I might not have got it right then, but you can check. Basically, if the timer took at least 8 seconds and it took 3 times longer than it was supposed to, we said, all right, let's go dump the state. And then that's obviously heuristic, but it was good enough in this case. And this bug was due to an interaction between timer, CPU hot plug, and RCU. We've got one going on right now that might be somehow between work queues and RCU. Maybe somebody else is using work queues. We're not sure yet. But we use the same technique work today. Oh, well, not today. It was a few days ago. Okay, so the thing is, you add the debug afterwards, that does not increase your MTBF. And so an anti-Heisenbug is, instead of just putting debug in the system, have some way of detecting the error and put the debug in then. Crash dumps are a special case of this, a very important high use one. And in the white box, I'm going to skip that. Let's check your memory here. What's better than being proficient at hunting Heisenbugs? Very good. Yeah, somebody got memory or just is able to figure it out. Yeah, not having Heisenbugs in the first place. All right. And there's some ways to do that. They aren't, they're kind of, this is kind of like your vegetables, eat your vegetables kind of stuff, all right? But, eat your vegetables, you'll feel better, all right? So there's some ways to avoid that. It's never going to be perfect, all right? You can do that as hard as you want. You still have a few, but, getting rid of half of them ought to be worth something, right? And so the other anti-Heisenbug is don't randomly hack concurrent code, okay? I mean, if you really want to, fine, but, accept the consequences. Okay, so there's some things we've talked about. There's no silver bullet. This is not a science, but there's a lot of useful techniques, and hopefully some of these will help you. They've helped me in the past, many times. With that, we got a little bit of time for questions. Yeah, we got one over there. Throw that man a catch box, quick, before he gets away. Throw him 2 catch boxes. Let's see if we can catch 2 of them.
So you mentioned currency first design. What are some good resources on reading that, especially for operating systems?
The Linux kernel mailing list has a lot of some fairly acerbically worded discussions of how to do that. Oh, you got a hand next to you. Why don't you give him the catch box? Maybe he's got a good answer.
TLA plus. So Leslie Lamport's TLA was something that actually got used for the current outstanding glibc pre-thread convar concurrency bug.
Let me summarize that quickly.
Yeah.
Basically, if formal verification applies,
yes,
to your problem,
you can do a reduced version.
yeah. So right there, verification if applicable.
Yeah.
Okay. The problem, and it works really well. There's also the Linux kernel memory model has some of the same problems. It's less powerful, but it's easier to use. Okay. You can just put C code into it. TLA, you have to work at it a bit. On the other hand, the queued spin locks in the Linux kernel were actually verified with TLA, and they found some bugs and fixed them as a result. But the other thing is just understand what the concurrency things are, follow designs, all that stuff. Okay, other questions? That was a good question, by the way, and good follow-up. Yeah.
So when you're hunting a Heisenbug, and it's a very rare event, how do you know that when you start adding instrumentation or something else that you're still, or increasing the load, that you're still chasing the same bug?
You might not be.
Yeah. And then
be careful, it's a real world out there.
And I think they mentioned, what was the initial? It was 1 instance per 4K of machines for a week.
Yep.
How do you know it wasn't just alpha particles causing you?
Because the alpha particles wouldn't have said born on once on this particular line of code all the time. But you're right. If you have a Heisenbug that's just like a memory corruption error, it's going to be really hard to determine it's the same one. But again, there's no silver bullet.
Thinking of all the laptops.
Oh yeah, yeah, all the consumer devices. More questions?
So before I got involved with kernel development, we had this like in the Rust world, we had this nice library that we developed we had this concurrent code. We have this library where you just take a test written in Rust using your code, and then it runs all of the permutations to see if it can find any bugs.
Yeah.
Do we have
that's
anything
excellent
like that in the
technique.
kernel?
I don't have something like that in the kernel, but there's a funny data structure used to track RC callbacks. And I pulled that code into user space, filled out stubs for all the kernel functions I was calling, and just did exhaustive testing based on the state of the queue. I would run the functions and verify they came out the way I expected. We should probably use that more often than we do, to your point. White box testing. I wish I could remember the name. I was talking to somebody at Kernel Recipes, and they were doing exactly that for a bug. They had a state that was legal, but rare, and the bug would happen after that. And so they cheated, initialized the data structure to that, and then let the bug happen. But yeah, that's white box testing is an excellent technique.
Yeah, and especially useful if you can, get it into the language itself, or like at least run code written in the language instead of having to.
This wouldn't happen to be a paid advertisement for us now, would it? Sorry, I couldn't resist.
I'm sure you can do the same thing in other languages.
Just might be.
The question is if anybody has done it.
In some ways, yeah. Other questions? I think we probably, yeah. I've used up the next person's time a little bit. I apologize for that. But the handing out of the mic.
I know that I type
So who knows how to get my slides? Who's the room person?
I'll do what I did. Which ones are your slides?
They're not there. That's what
Okay,
I'm
great.
Oh, I had to go in, download it onto there.
You know how to great. I want to do it.
Yeah.
It should be on the other slide.
That's all right. This will not be as entertaining as Paul. This is a talk about sort of a follow-on to the talk I gave last year at Plumbers. Last year was more of a, hey, look at the stuff we're going to do. Well, this is hopefully we've done most of the stuff we said we we're going to do. So the main talk, the core of the talk is about the Nouveau project, where we're going with the thing called the GSP firmware. And then there's also a section on work we've done as part of that project to sort of like make a GPU virtual memory address allocator manager, because yeah, everyone should have a virtual memory address allocator in their life. So the first up is, well, what the hell is this GSP word? If anyone, the Nouveau project is like the NVIDIA reverse engineered driver that we ship on Linux. For years and years, there's been, our relationship with NVIDIA has had ups and downs. They started giving us, well, originally we used to reverse engineer our own firmware. Over the years, that kind of got harder. They started using signed firmware. You could reverse engineer, but you couldn't re-implement it. You couldn't put it back on the device. So they started giving us firmwares that we could use, but those firmwares were generally not fully featured. Those number of years, we got these semi-featured firmwares that were enough to turn on the screen and do some acceleration, but you couldn't reclock. The device was slow. So that situation is that where we were on it's like we had our user-based driver, our kernel driver, some little firmwares, and the hardware. And the kernel driver talked to the hardware, it talked to some of the firmwares, and it kind of worked, but it kind of sucked. And that's where the project kind of really stalled for a few years, because there was no real incentive to develop fast user space stacks or new features, because you couldn't do anything with them. I think the main feature I developed in those years was the ability to turn the GPU off to save power. It was like, that was the best thing to do with it, was switch it off. So yeah, we didn't have a lot of motivation. And that changed kind of recently. NVIDIA re-architected their GPU designs, starting with Turing, and they added a RISC-V processor that was slightly larger than previous RISC. The little microprocessors they had a bit more oomph, and they decided to move a bunch of stuff from the driver into this firmware blob. And that firmware, they told us we could use. So we're like, okay, well, we're allowed to use this firmware. It does all of the reclocking. It does all of the hardware initialization, talks to the hardware. The driver doesn't have to do that stuff anymore. So it was like, well, there's some pros and there's some cons in that decision. The biggest pro is reclocking is now possible. That means we can at least start to compete with the proprietary driver that NVIDIA developed, because yeah, you can go fast. You can actually get your GPU to run at the speed it was designed to run at, and the RAM to run at the speed you want it to. And that opens up a lot of things for us. Another big pro of the GSP path versus what we had before was the firmwares NVIDIA were giving us before were not the actual firmwares NVIDIA used themselves in their driver. So a lot of the time it was like, this is broken, and they're like, okay. And then 4 months later they go, oh, we found that bug. It's like one guy, they didn't care that much about them, because they weren't using those firmwares. They were specially written for Nouveau. They might have been used internally for other stuff, but they were not very useful for getting, especially when a new chip had come out, that they'd say, this definitely works with that firmware. And you're like, no, it doesn't. And then 6 months later, like, you're right. And you're like, okay, I know. So yeah, so the big thing with this is the same firmware that they're shipping with their driver. So we at least know if it works with their driver and it doesn't work with our driver has a bug. It's like, or we have to figure out what the hell we're doing wrong. Unfortunately, with the pros comes the cons, and the cons are quite long and not fun. So I think the biggest, well, actually, I don't know which one of these is worse. I'll go with the first one though. There's the firmware design that NVIDIA kind of chose is standard NVIDIA driver has, it has like a version that goes all the way from the kernel or from the hardware all the way to like up into Vulkan, OpenGL, CUDA runtime. So they lock all of that into one thing and they build it all themselves from like one place. So it's like they don't really have ABIs. It's more of a, oh, I need an RPC to call from here to here. Oh, we'll just add another RPC or we'll just change that RPC. And it's like, so this may change, but the current firmwares we're getting from NVIDIA have absolutely no guarantees at all of anything remaining stable. Some stuff might, but you can't like, and it's not even like, oh, yeah, I don't know if I was familiar with the NVIDIA versioning number, they go like, they've got a 535 stream currently and a 545 stream and a 550 stream coming. In the middle of the 535 stream, they completely rewrote how the message passing worked. It's like stability to them doesn't actually mean anything in terms of that number. Like their internals of their driver is just what they do, and they decide themselves what to ship. So they don't care about redesigning everything right in the middle of a thing. So you can't. When we first looked at this, we're like, oh well, we could just take a 535 driver as our baseline, and we'll just put new versions of that into the firmware tray. So we just got one of these, we just up it, and the kernel should stay compatible because they won't change it in this. No, they did it straight away. So I was like, okay, well, we know not to do that, but that brings a big problem. So these firmware files are large. You're probably used to like, oh yeah, 64K, 256K firmwares. I think these are in the 20 meg to 30 meg range. And there's two of them. One for Turing and the first couple of Ampere cards and one for Ampere, ADA, and onwards. So guess what? You do not want to have a lot of these sitting on your system. You don't mind them sitting on your system, but you definitely don't want them in your /boot partition or in your initramfs. Or if you're on most distros, your initramfs has, you might have 3 initramfs. You might have 5 initramfs. Every one of those initramfs will have every firmware we list as a requirement for the driver, because that's how we've always generated initramfs. We just take the list of firmwares that the driver requires and stick them all into the initramfs. Again, if the driver, so say we're on this 535XY and we also want to ship a 545XY and then we want to do a 550 as new hardware comes out, we have to keep all of those on the system because the kernel has to be able to work. Old kernels need to still boot, new kernels need to be able to fall back to the older firmwares that they can't find the newer ones. So your system ends up with, from now on, it will be an ever-increasing number of these. Hopefully we can minimize how many of these over the years, but it will be we need new hardware support, we need a new one. CVEs, we need a new one. So it's like, it's going to be a lot more of a problem. Our current plan for that is no plan. Half a plan. What we're doing right now is we are not changing it willingly, easily. We are like going to be very, very strict on when we rev this. I've sent the one to Linus that was like the one that I had finally gotten working after 2 weeks, and I was like, no, we're not moving again. But we can't control that completely. My sort of secondary plan is I've done a couple of patch sets that let the driver put a list of firmwares together, and it will provide that list to user space, and user space only has to pick the last one of the list and put that in the initramfs. At least that'll give you a little like reduction. It should only have 1 or 2 in the initramfs as opposed to 7 or 8. Still, though, 20, 30 meg firmwares are going to piss off people that configured their /boot 10 years ago at 500 megs. So, yeah, don't have a good answer to that bit. But yeah, we have considered a couple of things in Fedora. Maybe we could pull the firmwares out of the separated initramfs and put them into a common initramfs. So then you would have your just one per kernel and one with just the firmwares. That would at least reduce the multiplier of having multiple kernels. Someone has suggested we just leave the firmware sitting in /boot somewhere and hope that we can get to them, but not sure that flies too well. So we had some suggestions that we just do not load the driver until we've mounted root file system. But unfortunately, there's a lot of system, well, not a lot of systems, but one of the corner cases we get a lot is you get a laptop that has the external displays are all connected to the NVIDIA chip, and the BIOS doesn't turn it on. And if you boot, you can't type in your passphrase if you boot with the lid closed on your laptop, and people apparently do this. So, yeah, would be nice. But yeah, these are the cons. We will try and reduce this. We will try and work with NVIDIA to help them do ABI design, but who knows? So what's the current status of this GSP work? Well, the first thing that had to happen to use this firmware was we had to refactor a bunch of work in the driver. So I don't know if everyone's heard. So Ben Skeggs was the Nouveau maintainer. He just recently retired from that position. He did all of this work before that. So he refactored most of the sort of the lower level stuff wasn't so bad, but the display code needed a complete revamping. To like about 10 years ago, we were like, oh, NVIDIA do display quite different than us, but ours works. Now we have to do it exactly like they do. We had to redesign that. And it was a lot. It turned out to be some random ass display port feature that we had never thought implemented that was causing a load of bugs. It was like, okay, we implemented that and it suddenly started working. So weird corner cases. But yes, all of that refactoring and preparation was done. And then the GSP patches were layered on top. The refactoring and prep work went in the start of the merge window. And then I sent a begging merge request to Linus going, please, 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 please. And obviously he was so enamored after Bcache FS, he was quite happy to merge it. So, okay, sorry. He was like, well, I've already done that. This won't matter. So it's merged in 6.7 RC1, which is good. It's only enabled by default if you own an ADA card or laptop. For Turing and Ampere, you have to pass a command line argument just to turn it on. There will be a point, I think, where we will just switch over because at least some of the Turings and some of the Amperes just never worked with the firmware we had. And NVIDIA were like, well, you can either have us work on that or we can help with this. I was like, okay, we'll just push forward, try and leave that behind. But we will try and, I'd say what will happen is we'll give an option for distros to switch over and we'll just let them do that instead of the upstream kernel. And maybe in 5 years we'll do it. There are unfortunately a few missing features in the regressions we've had just because we haven't figured out exactly what we have to call in the new API to do all of these things. Proper replayable faults don't work, which means like the SVM feature that we kind of have in there that no one really has used too much yet. So it's not, you're not going to really notice it in normal use. We need to get proper fault handling. So yeah, with the old driver, if your game does something stupid or your app does something like puts a pointer to the random place, you used to get a sort of a detailed little bit of logging. Now you just get a crap happened, sorry, you've lost your context, but we're going to work on that. It shouldn't be too hard to figure that bit out. Sensor monitoring doesn't work at all, so we don't know how to talk to the thermal subsystem, whatever the hell's on the other side of the thing. There's possibly a bunch of, that could be done anyway. I don't know whether there's like a bunch of API calls we have to call periodically, or whether it's something we can set up to report it through a separate status page, or we have to probably figure out how that actually works. But one of the, so that's kind of where we are now in terms of like regressions compared to the mainline. But one of the future things we have to work on. So when I said we had all these firmwares from NVIDIA, they come with a whole load of include files. And the structs are all in these include files, and the structs always have the same names, and the structs don't always have the same contents. And although John doesn't like hearing it, sometimes things get added in the middle of structs. So there's, how the hell are we going to deal with that? We have a bunch of C code that needs to include a bunch of header files with the exact same struct names. Do we fork all of the C code every single time NVIDIA changes the headers? It started getting into like, oh yeah, we could get away with this once, but after about a year or two of this, it's going to be an unmanageable nightmare. So I have raised with the team that's working on this and considering, especially with the work that the Asahi Apple GPU driver has done, and they're interacting with a similar kind of problem in that they have a fixed firmware with versioning that they have no real control over, an ABI that doesn't actually exist either. That maybe we should consider a reboot of the driver into Rust, just a GSP only driver that would just be going forward with Nouveau just on these firmwares. Even if we don't get as far as a complete reboot of the driver, we would consider maybe at least writing the piece of the driver that talks to the firmware horribleness in Rust, so we can at least dynamically do a lot more of the, if we don't do it in Rust, we'd probably end up having to use Python to generate the C code. So it's like, not really sure which is going to be what's. I kind of feel doing it in Rust would probably be a lot nicer than trying to get Python into the kernel tree just to generate C code that I'm going to compile. So yeah, we will see. But I'm pushing in that direction with the team that I have at Red Hat, and we'll see how we go. So that's pretty much the GSP part. GSP was it's a pain, but it will.
There actually is already Python in the kernel tree.
I know, but it's in the good part, isn't it? I don't think it's actually in the like building part. Linus doesn't see it, is I think how you put it nicely.
It's just the stuff I know about is debug tools. Okay.
Yeah. So
Fair
yeah,
point.
It's I had that. It's like the other option is you can use Perl. No one was interested for some reason. So that's the GSP. It's where we are with that firmware. It's getting there. So, but the other part of it is, well, now that we can reclock, how can we make a modern, useful driver? Well, what's missing from Nouveau? It hasn't really had a re-architecture in 10 years. We should probably, look at what's happening in the area. So I'm just going to give a little small, short history lesson. Graphics cards generally in history has video RAM, and they had a thing called GTT, which is graphics translation table. Well, what it means is system memory in like a page table where you can make things that are in random places in system memory look like linear objects inside in the graphics card. And for years, that's all we really had. We had physical memory management. How we dealt with that from the user space was the user space would submit a bunch of like handles to the kernel when it was submitting a job, and the kernel would then go through all those handles and relocate to the actual physical addresses. It worked for a lot of years, but it's slow and takes a lot of overhead. So finally, GPUs grew virtual memory. It was like, okay, now we don't actually have to do these relocations anymore. We can actually get the address of the object and just put the address in. Saves a lot of overhead, makes things a lot easier. These generally, the virtual memories were like per context, per process. We would generally do per file descriptor open, and that kind of works. But again, we started off with them with a couple of technologies we had in the kernel. We had these are just good overview of the terms. So we had GEM as like our buffer object management. So this is when a user space wants to create a buffer, which was just really a bunch of pages, either in VRAM or physical memory. We call it a GEM object. We had the TTM layer, which was more for managing the sort of discrete RAM and dealing with evictions between video RAM, evicting to system memory, evicting to swap, and how all that worked. We had a bunch of generic code that does synchronization objects and fencing, which is like where I'm using this memory right now. When I get to this fence point, you can move it. But as long as I haven't the GPU hasn't reached that fence point, you can't move that memory. And then the initial work, the initial thing that everyone nearly did with their virtual memory, which Nouveau had done, and I think Radeon and everyone had done, was they tied the allocation of a buffer object, so a GEM buffer object, they tied the allocation of that to a physical or to a virtual memory allocation at the same time. And this was sufficient when we were just dealing with OpenGL. It gave you the ability to, it was easy. I think it's probably the best way to describe it. It was like, I don't have to change much. When I create an object, I just give it a virtual address space. But the world moved on. And a thing called Vulkan came along. And Vulkan is a new graphics API. I say new, it's possibly 7, 8 years old, is it? Yeah. So it's around a while now. I think I can stop saying new. A replacement for OpenGL. And one of the features that like baseline Vulkan pretty much brought in was a thing called sparse memory. And sparse memory is user space virtual memory. So the user, they manage it. The user process is in charge of managing the virtual address space for it. So it can say, I just want to allocate this virtual memory in this address range, and then I want this object in this bit, or this object in this bit, or I want to drop that object out of that bit. And it also brought the feature of having both synchronous and asynchronous updates to that virtual memory space. So you could you could set up a pipeline of GPU, do this work, and then make all these page table adjustments, and then do this work, and then make all these page table adjustments. And in between those jobs, you'd have fences to say when to set go, when to stop, when to go. That's kind of gets complicated. It's starting to get, the drivers suddenly had to do a lot better. You couldn't get away with every time I allocate an object, it gets an address, because they weren't 1:1 anymore. They had to be, you had to be able to put objects anywhere in the address space, and you could put the same object in multiple places. You could put ranges of the same object in. It just wasn't sufficient. So I think the term for what we came up with as a solution was this thing called VM bind, and I think that just came out of this. Someone named an ioctl that one time, and now we all just call it that. But it was before I get into the details of what that is, I'm just going to little digression. So if you look in the DRM code base, we are very, very big on trying to get as much commonality as possible between drivers. We don't tend, if you look at a vendor driver that comes out, they generally try to do everything themselves, and they're trying to do reinventing wheels is like their thing. It's like, we've got a whole team to reinvent that wheel, let's use it. We don't really have that luxury. So we try to keep the one wheel per implementation of something. And we did really well at that with mode setting and the atomic work. That the initial few implementations of that, we did a lot of common code. We had but for the acceleration side of drivers, we weren't so good. GEM kind of had a bit, TTM a bit. We had a GPU scheduler that was common, but used by one driver. And attempts to use it in other drivers got hard, but at least it was in the right namespace. And I had found a lot of drivers had started to do their own VA management. I was like, okay, AMD sort of got this right. And then I saw, I think it was Freedreno, I started seeing Mesa bugs come up going, these guys have, the VA doesn't do something properly. I'm like, that should be common code. Like what? There's no reason you should get that wrong, because we should all be doing it the exact same way. There shouldn't be a choice for a driver author here on how this works. Everyone needs to be doing the same thing. It's dictated by the Vulkan API. If you're doing something different, you've probably done it wrong. So it just happened at this stage, the Nouveau stuff came up, and I was like, oh, if I'm going to write a VA manager for Nouveau, I'm going to write a generic VA manager and use it in Nouveau. And then I had a better idea. I'm going to get someone else to write it. It just happened at that time that Red Hat had hired a very competent engineer called Danilo, and he was put in my team. I was like, I can get you to do this. This seems like I can tell you what I think it looks like, and then you can tell me what it will actually look like. And we sort of looked at the AMD GPU code for inspiration. It was like, yeah, this seems to mostly get it right. But we made a very specific thing at the start that we would try to be useful for as many drivers as possible. It happened at the time that Intel was working on a reboot of their kernel driver called XE. They were like, oh, yeah, we're doing this. And yeah, we're good to do this in common code. There's the Panfrost team was looking at doing something similar with ARM. So ARM had been starting up a new driver. So that team got on board as well. So we actually managed to pull, and this is what I like about when we do that sort of common code thing, and is that it's not really about common code. It's about the fact that you have multiple people who understand the common code and can talk about it. It's like, that's the bit that's more, when you have a driver and you're doing everything on your own, you can go into the woods because you can, convince teams, people on your team that, of course, you know what you're doing, and they're all subordinate to you, or something. Your manager tells them you know what you're doing, so they don't really dig in. But when you've got that multi-vendor community of people and who are willing to, actually look at your work, it makes a huge difference to especially the velocity and getting the bug fixes. So that it really has worked out in this area. At least we've had 3 or 4 or 5 people that know what they're doing and really got invested. So it's been good like that. We're going to hopefully, not saying Alex, get someone to port it to AMD GPU at some point. We tried to make accommodations as much as possible for how AMD GPU worked. It was the first driver to do this, and they had a lot of different requirements. But I'd really like MSM to port it if Rob ever hears this. And one of the things was I wanted Daniel to don't just go nuts, learn. We want to figure out how these things can work. So he did a lot of trails, ran a lot of different corners, and like we made decisions. We tried it. I was like, well, I've heard about this maple tree thing from Liam, and I've met Liam a few times. It seems like it should be cool for this. It's for virtual memory, you know. So, and he did, and he went off and spent like a month or so. We went into maple tree. We sent patches. He got it going, and then we hit a big and we had to back it all out. But it was like, no, it's okay. We learned what we need to do if we'd ever want to do it again, or we learned, you know, it was a lot of good learning experience, especially for him to get into the kernel and knowing other people and, you know, connecting him to other people. So you may ask, what did we hit? Oh, I jumped over it. That's exactly what happens in life. I'm just going to give this slide because it's because Liam kind of asked for it. But we have this thing called the fence signaling critical section. And so I suppose the concept is we've got this thing called DMA fence. And the whole point of a fence is when you put a fence in, everything before the fence, all the memory that's before that point is pinned. And when the fence is lifted, you can move the memory. And that's how so your general submission of work to GPUs is you sort of, you know, you get a hold of objects, you fence them all, they're all fixed in time, you submit the work, and when the work is finished, the fence gets pulled up and all that memory is able to be moved. In reality, what happens is work, fence, work, fence, work, fence, work, fence. So it's not like you really can ever, you know, but you don't ever want those fences to, like, you can't have them like last forever because, well, what happens if your system's under a lot of memory pressure? GPUs generally will pin 80–90% of your memory if you give them a chance. You know, they don't mind using all of your RAM, especially if you're running Chrome or something. It's like, yeah, GPU will pin the bit of RAM that Chrome hasn't used. So one of the problems with this critical section thing is that it gets called in from, so you can be in the shrinker. So I've got a fence, I've got all the memory, and then the shrinker gets called, and it's like, oh, I need to free some RAM. I need to, give me some RAM back. And it's like, can you wait in this fence? And I swear, when that fence gets signaled, you'll get all this RAM back. You'll be great. The shrinker, so it does, and it waits on the fence. And then the code that's going to signal the fence decides to allocate some memory. And it's like, oh, I don't seem to be able to allocate memory right now because the other guy's allocating memory stuck in the shrinker and waiting for me. And guess what? Your system dies, deadlocks. So there's this is the critical section is, yeah, you backed yourself, you can't make forward progress. We've had a few attempts by drivers. Again, one of the reasons why I love common code here is I've had a few attempts by drivers to make those fences into something that user space could signal. And then it was like, well, I mean, I've gone into the shrinker, waiting for the fence to signal, and then user space goes to signal, and it wants to allocate some memory. So the process that's going to signal it is stuck in malloc, waiting, never gets to the signal, and then the kernel is deadlocked. But you can't even detect that one. That's like you can have, it's a graph through user space of what could cause that. But the suggestions given often were from people that with those driver implementations was, well, we'll just timeout and try again. And it's like, yeah, that's not really solving the problem. It's like, so, and I just found out, I just read this scenario because I convinced someone to write some documentation, and they did. Not alone can we not only not allocate memory in that fence signaling path, we can't take any locks that other people might lock and allocate memory under. And that makes it even more annoying because you're very limited what you can do in this critical section. And one of the things we kind of want to do in that fence critical section was update the page tables. And with MapleTree, the problem was you generally had to fall back to, you could pre-allocate stuff, but if you got there and you hadn't got enough nodes and you had to split stuff, it would try to allocate. And the pre-allocation side, you either have to use GFP Atomic, but you had to use it a lot. And it was like, okay, this is probably pushing what you should be doing with GFP Atomic, or you had to pre-allocate a lot of stuff. And the amount you had to pre-allocate was quite a lot if you had to do it for every page table path that you had. So I'd like to see if we could resolve that over time. But for now, we fall back to an interval tree, which may have the same problem, but has it in a lot less of a problem. it just needs a lot less pre-allocation. So what's the current status of this work? Well, the VM bind API for the Nouveau kernel driver, the initial implementation of that, which pretty much covered this GPU VM work, the synchronization objects and the scheduler integration, that all went upstream for 6.6. And that kind of enabled the Vulkan driver to get moving. There was a bunch of improvements though that like the initial one was like, we had some naive things and we were like taking a lot more locking and reserving objects a lot more than we needed to. And someone pointed out, you should just do this. And we're like, oh yeah, we should just do that. But then it took us 2 kernels to actually go from, oh, we should just do that to actually figuring out how to do it and getting it right. The scheduler has seen a lot of changes as well. This is the generic scheduler that went from being one of these in your system talking to one hardware ring to one of like X number of these per file descriptor. Everyone has one. It needed a lot of work to scale up to that, and that work's being done now. So that's in progress for 6.8. I think it's all in, well, all the generic bits are in DRM MISC next, but the Nouveau bits are waiting for me to read them, approve them now. But with that, it's like we've got the sort of core of a modern GPU driver for the NVIDIA hardware. There's, for graphics and Vulkan workloads, compute's a bit more, probably a bit more work, and there's a few other things like host pointers and stuff that we don't quite do yet. But yeah, it's most of the core. That plus reclocking really sort of sets user space free, at least to start considering. So what happened in user space in that time? So I'd like to say most of that work that's been done prior to this was done with Danilo at Red Hat and a couple of people from Collabra and a couple of people from, one from AMD interacted, and a few from Intel. So it was a good group of people working on that. I was more of I was just standing around watching it and testing it on my laptop and going, it blows up a lot. And yeah, getting it ready for Linux. But so the user space driver, Fate Extra and the Collabra took this task on and has pretty much done most of the work. I think myself and a couple of others have, jumped in every so often, added, a few little extensions, done some groundwork to get it going. But it's a Vulkan driver for Nouveau. We initially brought it up using this the old compiler we had. The old compiler was not very well written. It was probably 6 or 7 years since anyone really had done anything with it. So Fate had designed a new compiler, which is called NAK. It just got merged into Mesa last night, and it's running already much faster. I think we went from like 20 FPS to 1,000 FPS with lots of like demo apps and stuff. So it was like, yeah, we really need this. I'm hedging this because I'm not actually sure how close we were. There was a conformance run that completed and was successful. I can't remember if it was 1011, but we're close to doing conformant Vulkan 1.0, 1.1 on Turing. Ampere needs a little bit more work, but yeah, it's pretty close. So it's come a long way in the year. I think our forward-looking is just get Vulkan 1.3 out the door. I think the kernel's going to need a bit more. I think the GSP work's going to need a bit more integration, and I think there's going to be a lot of bugs to fix. Ben's departures kind of mean we have to move people around to try and cover that gap for now, but I think we've got a bit of coverage on it. It might slow some of the work down that we were trying to do, but I think we're in a good position to move forward. But yeah, if anyone has an NVIDIA laptop and wants to try, get 6.7 RC1, get the new Mesa. Unfortunately, the new Mesa needs a new Meson, which needs a new Rust, or it needs a new Meson and new Rust. So it's really that. Yeah, one interesting thing is the NAC compiler is written in Rust. That's another sort of like we're trying to use Rust for more things, and that's an implementation of a Mesa compiler written in Rust. Any questions? I do have a demo, but it's in my bag and I don't know how to plug it in here. So I'm also afraid to plug it in because I haven't actually plugged the monitor into that laptop yet. But I can take the laptop out and hold it up.
There's one correction that NVK will be conformant in a couple of weeks.
There we go. So that's Fate conformed in a couple of weeks if no one in Kronos complains. So we're just waiting for the 30-day timeout. All right. So it's already been submitted at 1.0 for conformance. Thanks, Fate.
Any questions?
So, at the risk of learning the answer, why does signaling offense require allocating memory?
Oh, no, no. Signaling offense should never require allocating memory. But
Okay, that's okay.
the problem
we can
is
talk about that
people
other time.
didn't get that message because it wasn't well documented that you shouldn't be doing that in there, and then all of a sudden we found out later.
Is there a way that we could get some amount of like static analysis for that kind of callback where you could say, I know I'm never calling through a function pointer and I'm always only going to call these things that that cannot hit kmalloc?
We have a very sketchy lock depth annotation that Seema Vetter wrote, and unfortunately, the minute you put it into any driver, everything explodes. So we're trying to work our way through putting that into the drivers to make everything explode when you're developing rather than when you're using it. But
okay, thank you.
I'm sure you don't want to hear this question, but can the new driver API work with old NVIDIA cards such as like a first generation Maxwell? Will that work with with this new Vulkan API and so on?
So so the Vulkan driver currently is Turing Plus, but we plan to get it going Maxwell, Kepler. Yeah, back to Kepler probably. But unfortunately, the reclocking won't be there.
But like, there are old like first generation Maxwell had reclocking, so
yeah.
So
Yeah,
you could get it working.
yeah. If you've got an old Kepler or a first gen Maxwell and you got the reclocking patches and they work on your system, yes, then you would be able to reclock and get Vulkan. But yeah, unfortunately, everything between Maxwell 2 and I think it's probably Volta, Pascal or Volta, it's going to be a wasteland, unfortunately, for reclocking.
Would not blocking shrinker and just returning that, hey, I can't really shrink anything, would that actually avoid that deadlock?
No, well, it would avoid the deadlock, but it would also, unfortunately, just have your system run out of RAM because the whole point of I think Liam, you asked me that question yesterday. It was like, yes, but the GPU is probably locked 90% of your RAM. You're not going to make any forward progress. You're just going to start failing kmallocs all over the place. Like you really want it to stop doing what it's doing, give you back the memory so you can get forward progress. And it's like, yeah, it would be nice to just go timeout, but no.
Yeah, it's usually.
Yeah, you're going to get your desktop blown away pretty quickly.
Is it something, I don't know anything about the shrinker, is it something where you could say reasonably like, I submitted a job to hardware, I'm pretty sure it's going to complete in a second, go ask other subsystems and then wait before invoking the killer because I know this job is going to, I believe this job is going to advance.
Yeah, I think the shrinker often doesn't get to us first, but yeah, it could be something, but generally it's our fault.
Oh, yeah, absolutely.
You know, and I think the workload that I keep hearing about from people is if you've got one of those low-end Chromebooks with like 4 to 8 gigs of RAM and you're just browsing the web, you are constantly in reclaim, like constantly. And but that's the actual state of being for the machine. It's like you open an extra tab and it just swaps you out and reclaims and reloads the whole tab again. So it's the default state of being in those laptops. So you have to not crash, you have to not deadlock, you have to be able to make forward progress. So it's like, yeah, and the GPU is probably using 99% of your memory on those. So it's
okay. We're out of time.
Yeah, grab that microphone right now. How's it going today? So far, so good. Taking a break from the marathon walking I've been doing. I'm assuming you're the next presenter? Okay. Cool beans. Everything's good to go. I'll be back.
Huh? Yeah, exactly.
Nobody cares about because it's huge. And there is no second word. It is the only one. Like if I told you, oh, yeah, okay. Let me be a little bit of specific. There are projects like this that will compile to some sort of do that is well ancient, and that is not itself important. You could have your front end built down to an old version of CUDA that you can also port. I think it is. Where we looked at our things, we're looking at like various ways of doing it. Yeah. It's actually something I was looking into myself very recently because I don't want to discourage anybody from I happily can know where I was sitting. CUDA is a vendor that reduces the value of things by this part. Yeah, nothing else positive. Yeah, that's it's like out of all patches in one, it's like difficult to do, and we don't want them in one because that encourages them to lock in. So that's I think it's like when we my whole job is to do translation layers. What's like our translation layers on top of DL.
And so that means okay, so that would be more
No, nice. I had a desktop. Right?
So you were asking me the question I was having.
Anyway, nice meeting you. Right, like.
Yeah.
Yeah. All I have a text is every architecture, right? Right, but you have to just other variables in there. Yeah, well, it turns out the ground test is very spectacularly Yeah, that's exactly what I did, yeah.
I don't know. You know, I mean, the thing is, you got so the closest thing I know of what was supposed to be and I don't know what's the little okay, look, so I'm not sure. You're asking me stuff. I where you're gonna go. So if you're going to road that, I don't know whether you want to go that way or that way. Okay, that's the problem. My He did it. He did it. Kick out those people. But you have to do the whole word and do it correctly. Yeah. But I'm just trying to pass it away.
Yeah.
You are on microphone.
You can't hear me.
Well, I can hear you,
Yeah,
but
you can hear me. That means you're
Hopefully. Yeah. No, I am. It's the green light which lights up. Okay. Here. I would start the session putting Linux into context. And as you could see, there is not only the work by me, it's from a bunch of contributors within the LISA project. To give you short background on who I am, I'm not a traditional kernel developer. I've been writing bootloaders like 10 years back, and then I got to the dark side. Now I'm more in the product manager role, but in my spare time or not, I'm also the chair of the technical steering committee within the LISA project, which is the main part of the talk. I'm also the member of the Linux Foundation Europe advisory boards. Linux Foundation Europe told me I should say this, so I did this here. Yeah, as said, main part which I want to talk about is the ELISA project. That's the Linux Foundation project, and ELISA stands for Enabling Linux in Safety Applications. Quick check for the people sitting here. Who knows the difference between safety and security? Half hands up, that's good.
it's spelled different.
So I had a few like Ask the Expert sessions and others, and then I got a lot of questions about cybersecurity and how we're handling this, and then I explained that safety means something different than security. I come from Germany. There's actually exactly the same word. That's why we often say cybersecurity and functional safety. Functional safety means causing risk to human life and avoiding this risk. So this means not, basically I'm fine if someone intrudes in my system as long as my function remains operating, which typically will not do anymore. But if I can even see that something goes wrong, it may be a chance that this is safe. So there's an overlaps in safety and security. But here it's really about the functional safety as such. We have a bunch of members in here which deal with functional safety, which have an interest in putting more responsibility for Linux into safety critical systems. And they are from aerospace, from automotive, Red Hat as someone pushing very strongly, and then you have a large set of these members working in. And they all subscribe to a mission in the project, where you can see it says it's to define common set of elements, processes, and tools. And this basically means, especially processes and tools, that we also have to do a lot of things around just writing code. So basically what set of elements means, this can be the source code which we're providing. And the end goal is that it will be amenable for safety certification. We're not providing a safety certified Linux from within the project, but we help others, integrators, to do so. And to do this, we split the work into several topics. We have a bunch of safety architecture. This is really going and looking into how kernel operates, how subsystem calls are made. I tell a little bit about this later, where we used it. The Linux features is a very interesting part. So here it goes more like when you come from security, you know about C group, namespaces, and so on. And we would like to identify further features and say, if you have these kind of features, they support your safety argumentation. And if you have the security view, you know that just because there is the feature of namespaces, C group, and so on, it doesn't mean your system is secure. You still have to do and configure it properly. So we also want to provide more guidance on this. Tools investigation, code improvement, this is more also the area where we look how tools are used, that the tools are doing proper things. Sometimes you need to qualify tools. So we check what could go wrong with the tool, or also to set up our CI system. The thing I'm not touching today is the open source engineering process. This really checks into how is the development process of the kernel, how does it match with the standard safety standards which they demand. And the system thing should bring different things together. And when you need to create a system in safety space, we often talk about safety elements. And in the automotive, they say safety elements out of context. But to say this, there's nothing which means out of context. You always need a context in which you operate. And that's the start of the talk where I said putting Linux into context. So these are use cases. And this was a little bit fast. We have basically 3 use case groups from the aerospace, which is led by Boeing. There's not the dedicated use case yet. They are in a founding phase and considering which use case to take. For automotive, we started with this work from automotive grade Linux. You see these instruments cluster, the black one in the top. You may wonder what this speedometer things have to do with safety. In principle, it means the gear which you put in the car, it's indicated that you always know that you're having either front or rear gear in, so that you're not having the wrong gear by mistakes and hit someone, or also that the check engine signs are there. And this actually is safety functionality. And you need to guarantee that these things come in a certain amount of time. From medical devices, this is a very interesting one. I have a little more work of this also in there. This is called Open APS. It's an artificial pancreas system, and it's there and connected to an insulin pump. So if you have a glucose monitor and an insulin pump, normally you get notified by your mobile that your blood sugar, glucose monitor, whatever changed. And these systems are very, very expensive. So out of the demand and need, Dana M. Lewis, you can check for the name and some TED Talks, very impressive. She created an own system based on a Raspberry Pi, put on a script of a few hundred lines, and let it operate her glucose monitoring and then the insulin pump, which often by medical device manufacturer is that expensive because it could cause a risk to human life. If you have an overdose or something, this is really horrible. But here you see that it's impressively running, quite stable for many people. They decide on their own to take this risk. That's maybe the difference, that you're not selling it directly as a product, but they set it on demand. I think they have a few thousand users, and they are on a path also to certify work of it. But that's a very important element. And these 2 examples are more pure Linux system as of now, but there's more work where system complexity increase. And some challenges are, also let me see where it goes. Yeah, there if you use Linux. So normally you would bring this with a certified, typically real-time OS, bring this functionality in. And now it's more used for Linux. And why is there the question for Linux and asking to use Linux? So some may say it's cost savings, because if you pay for a commercial OS, you want to save some money, but there's also demand of having more features in. So you know about autonomous driving. You have very complex, many core computing systems, and at a certain point of time, these certified systems don't scale anymore. You don't find proper libraries. You cannot look into this source code because it's typically closed source binaries. And so when you want to approach complex use cases, you either have to go into the, I get more enhancement of the safety certified OS, which is very hard to influence, or I bring a safety parse towards Linux and then put it in combination. To get a feeling on what means safety for Linux, here some topics are definitely memory management is seen as not safe. Dynamic memory allocation, not safe. Caches, not safe. Interrupt handling, also not safe. Real-time scheduling, well, we're doing progresses there, but if you talk to the safety guys, sometimes they would also say Zephyr is not an RTOS and it's not real-time, because real-time is really when just do bare metal. So this is something where we have clash of worlds a little bit by this, and where later also would like to request certain support from community also to get a bit more understanding on topics. Right. What helps us to work around these things is a lot of tools. So we need to increase the understanding. We need to understand what goes wrong in systems, what are crucial elements. STPA is a system theoretic process analysis. I spent 2 slides on this here, and then also on the S-Tray C-scope, something which we did as workload tracing based on the results. KSNAV was an extension of this. So we have these kind of things in the ELISA project. Some parts are upstream, some not yet, but just on our GitHub. SDPA is a very interesting thing if you're involved in designing systems. So this basically is a handbook for Nancy G. Levinson and John P. Thomas. You can just search for it. It's free, and I also have the link in the slides. So you can just click on it, and it's worth reading like the first parts up to page 50, and then somewhere in the appendix on why you should analyze complex systems. And it actually also works to do your electricity in the house properly. So it's a quite flexible approach. The idea of this is that you are jumping over this, that you have some elements like a controller and a controlled process. And this you will do for your complete system. So you have something which sense and control action, sensor actuator model, and then you get feedback because you want to know what happened. And you basically check what are unsafe control actions. So what could go wrong? The nice thing about this one compared to drawing really formal models is that you can put in people or hardware, software, environment. You could basically give everything being a controller or also being a control process. This is an example of the open APS system at the first level of analysis, where everything was just put in like, oh, we have an application developer. And this is also something involved in this whole topic. So you can say here's an application developer, here's a user, and you put all this in there. And this was the first level, and this blue box was then further extended to just check what is the Raspberry Pi really doing on this? And what is the algorithm doing? What is in the interactions between? And we wanted to go one step further and check what the kernel does, and we failed, basically. So it's getting very, very complex to just use this analysis without any usage of further tools. And here we came up with the workload tracing with work from Shua and Shefali. They both did a lot of work on this. They mainly used S-Trace and C-scope. And what we extracted was what are relevant system calls for this workload. So when open APS system is in operation, what can happen, which calls are there, how often are they called, why are they called? And this also, yes, I do have it on the next slide. Yeah, so this is something which later on in general case was upstreamed also. So you find it now in the admin guide. And it's also the place where we plan to have more things uploaded in the coming years and work we have. So We see that there's a lot of things still open. Other updates are also in the field of man pages, because we see there's not always a matching implementation to what we see in the man pages. This will also help to improve safety quality. And for workload tracing, as said, this is mainly on seeing what's running, but we also sometimes want to see what is left and right, what could be called, but maybe was not called by the workload. And for this, there was work from Alessandro and Maurizio, I guess, yeah, I hope, at both. Alessandro and Maurizio at the end. This is something which we haven't upstreamed yet. We were wondering if it makes sense to put it somewhere. Basically, it's a tool which can be used to do a static analysis of your kernel configuration, and then you get incredible call trees sometimes, which you need to narrow down to what is important for you, but you can really get a feeling on what do I need of a kernel, what do I don't need, because if you are in safety critical system, you need to strip down things really to the detail of what is needed. So I made it bold. Is there a good place to upstream? Maybe we can discuss later if there's a view in the audience. And this was one thing where we had some upstream, but we also came up with further topics. So if you have a use case, this brings different ideas on what to focus on, what is important to look at. There are also some topics which may be independent of the use case, which every use case shares. So it's something which we recently started to discuss, if there is a core of a kernel. And this could be in this, what's in the orange box, like synchronization, timing, interrupt, exception handling, resource management, memory allocation. Basically a lot of things which you have also seen in what is considered as not safe by the safety community. But also additions like initialization parts, how does a bootloader place into the game? So we had this talk yesterday morning from TI where also the bootloader was really brought into the topic of safety. So this is something which we haven't touched yet. What we touched was work on preempt RT and real-time analysis toolings. So this is something where we are also still working in, where we want to progress. All the results should be upstream documentation part at the end, and it should help integrators, people who build system, that you get a better system understanding. And I hope it's also helpful for others, not only in the safety environment. Here is something which I just saw. It says add link to their presentation here. I missed this in my review. So on the uploaded version, you have the link to the presentation which Shua and Alana gave during the years this year. It gives you an hour overview on basically things they have analyzed, how to use preempt RT, how to configure things, how to do analysis of workloads which you have. And this is the base where it should start on getting more upstreamed. And there was a request also by Alana as a work group lead. She said, if you're there, promote that we still look for people who are really using it in practice, who are experts also, that rewrite the proper documentation on it. So it's always good to have more than 2 eyes or 4 eyes in there. And yeah, if you look also in the admin guide, you see currently there is nothing for preempt RT as really something in user admin guide. Okay, yeah, real time is something which you find in many different systems actually. And this is now also the part of this really system creation. So you can see that I put different scale of use cases. So the most simple one would be maybe a lawnmower or also your vacuum cleaner at home, which actually involves, due to app functionality, due to getting cameras involved, due to having sensor data, it's not really a safety use case if it's not hunting your hamster or something like this. But it combines already multi-chip, multi-core processors with microcontrollers with certain real-time capabilities. And basically it's not too much different if you see a vacuum cleaner lawnmower from something going out in the field in agriculture, because they also have like a square which they clean and there may be obstacles in there in a controlled environment or a mining vehicle operating somewhere in a larger site. And this is also the fundamental principle of an autonomous driving car, because in the end, your vacuum cleaner is an autonomous driving vehicle, just on a smaller scale. And these architectures are very similar. And this is also what we with it going that fast. Yeah. What we saw with other communities. So when we discussed about the systems work group, the idea was basically to have an industrial work group first. And it was not an industry use case as such. When talking to the Xen people, to Zephyr, especially with Xen, we figured out, oh, there is a similar strategy currently from Stefano Stabilini. So he was presenting something last year that's in June timeframe in Boston, I guess. Yeah, on the Open Source Summit. He also created a reference system, so I have the slides later on, just the information for it, which exactly is a similar setup which we used here for our reproduction. And also checking then with, especially I come from automotive, that's why you will see the automotive examples in there. With AGL, Sophie, SDV, they have quite comparable architectures with complexity of having heterogeneous systems and not only Linux in there. And this was a strong concern for us because our work groups within ELISA mainly concentrate on Linux, and there's a strong risk of forgetting what's left and right of it. And that's why we said it's good to have a real system set up, share the ideas, to get a better outreach and see which other communities also share the same problem. To give you an idea, I took a screenshot from the Sophie architecture version. So you find high compute CPUs, you find safety CPUs with hypervisors involved, Arctos, multiple OS, Arctos being then also on the hypervisor. So you find these system elements in here. And in a little bit smaller scale, we figured out, well, let's try to build one of these things. And this is basically the story which we had with Stefano. He also said, the people are listening to my talk since years, but it's very hard for them to reproduce whatever I've done. So this year, and it was last year, I will present how to reproduce the system. So that's what he did with a static partition, and he actually had Xen, Linux, RT, and Zephyr in the system. And this is where we also based our work on. But yeah, the presentation he gave was mainly concentrating on what can be done with Xen and was less on really like creating a complete system. He just grabbed a Yocto, Peter Linux, whatever they had from where he could find an image. And for Zephyr, he also just said, like, I don't care, I just get an image. I concentrate on the Xen work. And we said, okay, we want to have the full flow. So we want to build a Yocto Linux, a Debian Linux. We want to have Zephyr built, and it should be all reproducible, that someone can take it up. And it should run on real hardware, because the work was on QEMU with Stefan. He was quite clever in doing so. Because when you look into real hardware, you typically end up with a bunch of challenges. So you saw that we have some graphics involvement. This was actually the killer point which we had at the end for our systems which we looked at. This was proprietary GPU drivers, and we wanted to share them with a CI build with the community so that everybody can download. We failed. And other parts was also, well, you need to have good support when you have embedded hardware, how to get things on. Is there actually community support available? If you have sometimes community support, it may be tools where you rely on which are not in a very healthy state. So better look for which project to utilize. What do you do with the images, proper handling of it? Is it safe to just upload them somewhere? Which OS distro to choose? And then at the end, we're still on the way on it, create a full SBOM on it, because we want to make sure that the licenses are used properly and we want to know what's in the system, why it's in there, and which version. Right. Here I give a big thanks to Thomas and to Sudip, because they are the two people which mainly create the system and playing forth and back currently. So Thomas typically does the prototyping, he set the things together, he writes the guide, and then Sudip picks it up and tries to understand what Thomas does. And by this we get a documentation for the things, and Thomas is doing it on real world, and Sudip brings it into the CI. So what we found as major challenges during setting up such a Xen system was how to get a good hardware support for Xen. Not every board is supported in the same way. Is there documentation there? Do we have license compliance? Then another thing, which Yocto to use, because Xen comes with a Peter Linux Yocto, but there's also the Yocto or Yocto Poke part with the meta virtualization layer. So this is something then, how much resources you use. Yocto has shared resources, but this turned out to be some issues for parts of the community which said, well, yeah, I would like to do a build, but it's just taking too much time because my PC is not strong enough. Or they said, well, I have the computation performance, but I don't have disk space anymore. So these kind of things, then, yeah, this was all elements which we had during, from a software perspective of finding a starting point. we also check different targets. So we start with the Renesas R-car because we know there's good support for Xen in there. We also have the Xilinx in there because there's good Xen support. The Renesas hardware was also in the AGL as a reference hardware. Xilinx was discontinued, but was basically also in. So, but I said we had issues with proprietary graphics. So there you can have a click-through license for the normal drivers, but if you go for virtualization, virtualized drivers, you get on thin ice. So we said, oh, let's take the Xilinx one. We get a good start, and then we figured out the hardware which we used does not support proper graphics hardware virtualization. So we can do soft rendering and so on, but that's nothing which we wanted to have as features. Right, then we checked other options. So we went with QEMU, but QEMU performance is a bit slower. You don't have all the devices. Graphics rendering is even more slow. Still a very good option. So I always recommend to have also QEMU setups. The Raspberry Pi we considered because it's more community hardware, a little bit cheaper. But if you want to go deeper and have a real use case, you may want to go for system MMU levels. You want to make sure that you can really partition things. We had a short look at the i.MX8 system. They were looking quite good overall, but they were, from regarding Xen, had less more community support and were also not that available at the time when we started looking at it. So we ended up with the XU hardware and brought things then into an example system. This is actually quite small also from my side, but you can see on the blue boxes what are elements from different BSP perspectives. So we had parts where we used the Xilinx Yocto directly because it was not all available in plain Yocto Pokey. You see a purchase build. This is something which is an embedded industrial Debian derivative. It's basically in there because it's something which we have in Bosch together with Collabra. And Thomas, who does the system, knows by heart since many years how to do Debian distros and images. So that's why you also have a patch support there. Interesting to see is that due to the Deathfire part, we could directly take one-on-one from the R-car. So this was something very nice to see because it's a plain Zephyr. It runs on top of Xen, and it just is there for the Cortex-A support. So you just take the image as such, and it does what it should. So this was quite nice to see. Yeah, and there was also just the alternative to just take a Pita Linux. We are now in the process of getting it plain Yocto Pokey to get independent of the Xilinx work and have a more direct relationship. Then you need to attach a lot of devices and so on. And I'm not sure if I left this in the presentation, but there's a bunch of example configurations, a lot of links to click through so that you really can see. Oh yeah, here it comes. So everything, I use this as a kind of documentation. You will find what are the sources, how we created the image. If you are on the GitHub page, you also see the guidelines, how to set up such a system and where you find everything. So we use this as a pre-stage for documentation before we have everything in GitHub. Right. On that said, it should also end up in a CI. So we already have set up a GitLab CI. And in this, we split jobs for having the build and then the packaging of it. And it runs on a daily basis. What you may see on the right, we have artifacts for download, but we only have the latest artifact available, the latest images. Sometimes you see 2 days, but the idea is that if you came across development, at least I had it when I went somewhere and said, oh, can you show me? I have an issue. Oh, where does the issue come from? Yeah, it's in this area. So what build are you using? I use this build. And I said, oh, that's a few weeks old. Oh, but I modified a lot of things on it. So this is something which you see. And we said, you always get this latest one. if we end up with an issue, let's make sure we are running in the same environment. We have a reproducible setup, and that's why you don't find last downloads. And this also means if someone implements a feature, it gets into the CI, and you will the next day have the latest setup on it, and only the latest one. It's kept longer if it breaks. So it broke 2 or 3 times already, not in the systems workgroup, but in the other setups, typically due to the CAN controller. So there was CAN stack changes, there were certificates expiring, and so on. This was really important to see that we had a booting system and also QA checks at the end and have a full flow. And this is something which I guess comes from that slide. Yeah, this was a step which we said we came from Meter ELISA. This is our automotive use case. And we wanted to have an environment where everybody can start at the place where the person would like to start. So you can say, I really would like to see the starting point from just following guidelines. You read through it. Then you figure out this was something by learning that people say, oh, I cannot build properly. And in a while discussion, the one person was on the Ubuntu, the other one was using OpenSUSE Tumbleweed because his CPU was not supported by Ubuntu properly. So he went to the latest greatest thing, and then the infrastructure was not proper. So we ended up with saying, let's take a Docker container on this, do containerization, because then we have a reproducible environment. Avoid this. Resources we already said, so we have an S state which gets updated once a week to make sure that it still builds. Otherwise, we just build deltas, and we have binaries to download. This is also important because not everybody wanted to build. Some just said, I would like to see the system booting, try out, add maybe something, and by this we have multiple entry points where you can just get in. This is all in a fully dependency flow, which means whenever the documentation change, the Docker file will pull the new Meter ELISA layer, creates the image, and the actual Docker image which you will download for your development is also the image which the GitLab takes. And the generated QEMU image you can also download, and exactly this image is also taken by the OpenQA for testing. So it's not that you download anything which is not in this flow, which should mean when you change something at one part of this queue, it will potentially fail, and then you can observe it. The idea is that if someone takes it up, like starting with a QEMU image, it shouldn't be the point that the QEMU image still works while the documentation of the Meter ELISA is no longer matching. So it should be fully dependable and rely on each other, that you can identify worst case with a failing test case that it's caused because of changing in the Meter ELISA or somewhere in between. So you get a fully dependable flow on this. Why does it running like fast? Yeah, you have the motivation and full description in our blog post on this. What we see now for the example system with exciting soup, we don't have all sources yet in Meter ELISA because we grab a lot of things around. It's not directly, so it's other sources from different places. So we getting them together, but still the Docker image is the same image for the automotive use case from before, and the one which is built here. We also have a generated image, and what we currently miss is the testing because there are certain features which are not that easy. I said that there's no full graphics support. The OpenQA relies on graphics, and then also the cost is 3.5K, I guess, for a Xilinx board. So it's very, very expensive. So we look for alternative hardware. We're currently considering to have the QEMU next to it, because one really brilliant thing is that the Xilinx implementation is very close to hardware. So you miss, of course, some devices that will not be nice for a C bus, which you can check, or certain SD card for the peripherals also. But the whole setup of the Xilinx 2 part is reproducible. So basically the images which you produce for the real hardware also run in QEMU. It gives a few errors if you have an improper configuration because not all interfaces are there. But in this way, in the next step, we will be able to have also our images tested with QEMU. Still, we would like to get more diversity in. I think it's on the, what the intention was of this system composition is also it should be reproducible. We're on a good way on it. But if we have reached this reproducibility, I'm pretty sure someone said, but I'm not using Zephyr. I'm using FreeRTOS. Oh, I would like to go with another hypervisor. Or someone says, I'm not a Yocto guy, I'm more a Debian person, or the other way around. And we would like to have at least always one alternative. And the idea behind is, if you have an alternative, you really figure out what is the interface between the different systems. So how do I interacting with Linux? What makes a differentiating part? What are commonalities if I change from DevWire to FreeRTOS? If I take a Xen and a KVM or a Jailhouse or whatever I have. And also for hardware, we know that some things behave quite strange if you go for Yocto. You know, if you have one Yocto build for, say, we have TI here. So if we have a TI Yocto, it most likely does not behave exactly the same way like the NXP Yocto, maybe due to versions modification or something. So we said, let's take also 2 hardware versions in there. And if we are really able to just create variations of these hardware, you can start to learn how do I design my own system. And this is the one side, so everybody can learn which systems get in. The second side on this is we want to bring in the functionality. So if we now have our preempt RT work done and have certain configuration there, if we update kernel configurations, we all bring this in the reference system so that you can experience also results from our analysis, which we've done in the work group. For this, need to change the order. So I put a little bit of overview on topics where we are working on and where we could also just need a little bit more of support. So I showed you the workload tracing. This worked very well. We have this upstream. Still, the scripting is on Raspbian. We don't have an SBOM on this, so we have still a lot of work to do. So it would be quite interesting if there's someone who is willing and say, oh, I have experience. For me, it's just straightforward to just bring this workload thing up and get a Yocto build for the Raspberry Pi or for an alternative hardware and run this workload from the medical devices on it. So this would be very helpful. For preempt RT, I mentioned it already. We had good discussions also with Daniel Bristol, who was supporting us, giving us some information, Linotronics people telling us more about RT, preempt RT, but to have also user perspective in there and help to get the upstream documentation, this would be really nice. And my original starting point, basically, from this system here, if you say, oh, that's my favorite hypervisor and this is well supported, I know this virtualization brings graphics support with this hardware, or this is a really good supported community board. This is something which I would love to hear. Then we create it more and get another run on this on our CI system so that you can download things. And then the last part of this was like more on this core components to get more technical deep dives. They were very useful for us. We also did deep dives, for example, on the watchdog subsystem, and we figured out that the standard watchdog in the Linux kernel has a 1-second granularity. We would definitely need to go down for a 10 milliseconds to 100 milliseconds granularity for watchdog if we target automotive use cases. Well, this is some discussion which we had like 2 years back, and may need to continue on it again to just see how does it fit. But at the point when we started, we saw that we break interfaces from the existing watchdog, and by this we would need to end up with a new discussion, how to not break the interfaces, and do we see someone who already said there's a good value in it before we just upstream something so tremendously. Right. And this part would end up with kernel patches, documentation in the admin guide man pages. Some part may end up in our GitHub repo if it doesn't make sense to have it directly in kernel. And what we bring from the LISA project is really that we have a bunch of people which have strong expertise in safety and systems engineering, and they are good in analyzing these things, asking the proper questions, and get a good understanding how things should operate, but they are not kernel developers in the first role. And there it's really good to find this exchange, bridge a little bit, enable the conversation on it. So this is where we would like to get more support, also a little bit where there's willingness. It can be just starting smaller sessions or so, giving a kind of seminar, webinar. It's something which we did in the past, and that we have more and have a pause for more upstreaming. And I believe that this will be very valuable also for a lot of other work which is going on, because in the end this makes the whole kernel more robust, more reliable, dependable, independent of later use and safety. So it's just like higher quality to already high quality environment. And by this, I conclude. Any questions? Get a catch box. I think there's one over there. I don't know if the one which is following people.
I'm interested in the current state of the QEMU emulation. I heard you said not all hardware is working, but is it basically possible that I download your latest image, have somewhere a QEMU command line, and it basically works? So more or less.
This one here, you can see from the pipeline, there's the Open QA, and this one really boots the system, logs in, starts the Telltale use case, and takes a screenshot and does a screenshot comparison if the safety mechanism works.
Okay.
And this you can just, if you go for the link, I think I have all links for all the artifacts in there, but this is for the plain Linux one.
That's good.
And we have this one in plan. So this is just the work where this week, next week, the 6 go on to have it also for this other system with Xilinx hardware, but then you will not have a graphical interface, but you can log in. So the test case will go up to here's a QEMU image, it boots, you can log in.
And is there work ongoing like extending QEMU to support more hardware, or are you mainly focusing on getting real hardware?
We want to focus a little bit on getting real hardware. So we had some use case because we know that peripherals will be used like USB other. There are interfaces, but we said we would try to find a more community-friendly hardware.
Yeah.
Because especially if you go for industry, they use QEMU for testing, but they typically don't want to see it. And we want to get it a little bit more close to reality, seeing industry adopting it. And by this, we were looking for hardware and putting it in a fancy-looking case that it doesn't look like in Raspberry Pi.
But I'm very interested in your image. Thank you.
That's cool.
Have you tried any of the TI platforms like Beagle Play or something like that?
If you say it's good one, then we're interested. So I guess the Xilinx came from the good Xen support, right? So that's why we started, and the Renizers came from AGL. So we were more like event-driven. Like whatever event popped up to show us it's the hardware. And as there was no TI starting point, I guess currently I saw the talk yesterday, so this would be something where it's like, okay, maybe I should consider the TI work more and see what functionality is supported, which hypervisor you have, and so on. Yeah. So I definitely would like to see, but my criteria is in best case, I have virtualized graphics because a lot of use case requires something to display. And even more, it should be community friendly. That we find hardware which is below a certain, like, say, $300 range or in this range of it, rather than 3.5K for this Xilinx hardware.
So BeagleBoard has come up with Beagle Plays that are based on the AM62 SoCs. I think there would be something in the price range that you're looking for.
Yeah. And I know they also fit a bit of bunch of use cases, and they have also chance to combine safety and performance, right? So from the setup of CPUs and SoCs. At least an argumentation pass in there.
Sorry.
There's good argumentation to use such hardware.
Yeah.
Thanks. Yeah, cool. There's one more over there.
So we should talk afterwards on running plain Pocky on Xilinx hardware, Xilinx QEMU. But so what is your criteria for graphics? You said virtualization. So there's lots of ways to do that. Are you talking about hardware virtualization?
In best case, yes, this was something where the Xilinx XU hardware based, the old one, doesn't have full virtualization support in the GPU. We may need to find compromises and say we need to change our idea on the use case and narrow it down. But we need to have a certain performance, and best case have two guests, which can, from two guests, share graphics. It would be.
I mean, do you consider a VirtIO based, either VirtIO GPU pass-through or
could
virtual?
be an option, yeah. We would discuss it and then potentially say this is a use case enablement, and this is why it's may not be a final good use for safety, or where you need to be careful in the argumentation. This we would document then. Okay. Good. Thanks a lot.
I mean, slides are there. You can use it. Click through. That's basically all the magic.
Good afternoon, everyone. First of all, let me thank everyone for attending this very last referee talk. I am tired, so I can understand that almost everybody will be tired. So thank you, everyone. But let me assure you, we have a very interesting topic today. It's about one of the issues that we found on our VMs regarding latency and how we went about fixing those issues. So me, Vineet, and my colleague Joel, we work on Chrome OS team on the kernel performance, virtualization, etc. So yeah, so the agenda for the day would be I'll explain the problem, then the root cause of why it happens, and the solution that we came up with, and some performance numbers and some future work that we are planning to do. So the problem, on a loaded system, we were experiencing latencies on the VMs. That's the basic problem. And by a loaded system, the host has a lot of things to run, especially on Chrome OS. It's a busy system on a low-end device. So as you know, Chrome OS runs Android apps, and these apps run on a VM. So latency sensitive things like audios and video playback was experiencing glitches and unsmooth playback. So obviously the reason should be vCPU is a task on a host and it's not getting time to run. That's why you are seeing latencies on the guest. But when you dig deeper into it, the main issue is something we termed as double scheduling. So you have two operating systems running. You have a host operating system, which has a lot of tasks to run, of which a couple of them would be vCPUs. And then you have a virtual machine. Inside that, you have its own task to run. And the host doesn't know what a vCPU is running, but it schedules based on its priority and vRuntime. And the VM doesn't know what the host is running, so it might make ineffective decisions when it selects a vCPU and select bots to run. So this blind double scheduling ultimately boils down to issues like latencies, power consumption, resource utilization, etc. So I have an example here when an issue happened. I'm really sorry we don't have a good picture, but I'll try to explain the rows. So the second and third row is the vCPU thread, and followed by two rows, which is the physical CPUs, and followed by two rows, which is the virtual CPUs. And on the second and third row, the dark green color is when the vCPU gets to run, and the light green color when it's runnable but preempted. So as you can see, when we were experiencing a video lag, a considerable amount of time was spent on the run queue but not able to run. So yeah, these two are what you have. Are you able to see my mouse? Okay, cool. Yeah, so these two, as you can see, the light green color is runnable but preempted, and the dark green color is when it's running. So a considerable amount of time it's spending in the run queue without able to run. So okay, now let's think about, we know the problem. So let's think about some solutions. Okay. So priority is the issue. It's not getting time to run. So let's boost it to RT. So we have vCPUs boosted to RT. vCPUs are happy. It gets to run when it wants to run, but now the problem is reversed. So you have latency sensitive applications in the host, which wants to run, and you don't have you have normal task on the vCPU, but it's boosted to RT, so it preempts the host, and then you face latencies on the host. Not ideal. Okay, let's take a step back. The issue is priority, but ultimately the issue is double scheduling. So blind double scheduling. So let host and guest talk. Let them share information. Let them share the scheduling parameters. Let them share the scheduling state. So now the host knows what the vCPU might be running, and the vCPU knows what the host is running. Now you can make some educated decisions about what to run, where to run, and we can possibly fix this issue. So now let's come to our problem, where priority is the issue that it's not able to run. So this is a very specific use case of the cooperative guest and host scheduling. So what in this specific case, in this specific issue that we face, we only need to communicate the priority requirements of the guest to the host. So the guest basically says, okay, I need to run something important, please let me run, and the host can take actions based on that. By the way, if you have any questions, just break us in between. So we'll be happy to answer. So this is basically this complete feature is about, the project is about. So if the host really knows that the vCPU is going to run something important and latency sensitive, the host can proactively boost it. For example, interrupt injection. And if the host doesn't know, and then if the guest wants to run something priority latency critical, then the guest can basically request it using a hypercall. And once it the guest can let its intent know to the host, and then the host can take action. And now we come to safety mechanisms where there can be rogue or buggy kernel, and the host should implement throttling and a forceful unboosting if it sees that there is something bad actor on the guest. Okay, now let's come to what are the latency critical or sensitive context. So these are the things that we identified. NMIs, interrupts, and soft IRQs needs to be serviced fast. Then task with priority higher than sched others. So sched RT or above should be given importance. And whenever you disable preemption in the guest, that also needs to be taken care of immediately. I wanted to discuss one issue related to priority inversion, because with this dynamic boosting, some vCPUs might be running boosted and some might be running unboosted. And if it occurs such that a unboosted vCPU is taking a spin lock and it gets preempted, and you have a boosted vCPU which blocks on that spin lock, then you have an issue. So there is a bounded priority inversion issue which happens. But luckily, as I showed before, preemption disabled, we consider preemption disabled as a latency sensitive context, and spin locks disable preemption. So this is also automatically taken care of. Okay, now I hand it over to Joel to explain the implementation.
Thanks, Vineet. Just for anybody who came late, so basically the idea that the problem that we're trying to solve is that if you have something latency sensitive inside a guest, there's, we're not aware. If we're not aware of that in the host, then we might not be able to do scheduling properly. So continuing what Vineet was saying, so I'll go into a little bit of the implementation. Our proof of concept currently is only for x86, but it's portable to other architectures. We're about to post an RFC to the mailing list. We've been working on this stuff for 8 months or so now. So Vineet mentioned the sharing of information between the guest and the host. So right now what we have is a per CPU structure that the guest has allocated, and it shares the address of that structure with the host using an MSR. So it writes into the pointer into that MSR, and now the host knows where that structure is. And currently the boosting that we do is to RT, sched round robin, and at priority 8, but this is tunable. And the unboosting we do is to sched other. In the POC, our unboosting is is only to sched other, but we're planning to make that tunable as well. So you can boost and unboost to whatever you think makes sense for your system. We go to the next slide. So we also made it such that these features can be enabled per VM. So let me go over first how a guest is made aware of the availability of this feature. So the host uses a CPU ID to advertise the feature to the guest. So the VMM basically queries KVM for what are all the features that are available, and and then enables the feature. In our POC, we always advertise it, but in the final upstream implementation, we would not want to force this feature that way. And then we have knobs to enable and disable the feature globally as well on the whole system. Okay, so for this, so there's synchronous boost, unboost, and asynchronous boost, unboost. So the synchronous part, we have hypercall mechanism. So synchronously, the VM would issue a hypercall saying that it needs to do the boost or unboost right now. For the boost, actually, we only implemented the synchronous part, but we're not planning to use it because we actually boost asynchronously because we can avoid a hypercall a lot of the times. And for the unboost, it has to be synchronous because we want to make sure that as soon as we're done running the important stuff, we don't want to continue running the unimportant stuff as RT or high priority. So that has to be synchronous. Question? And just to go over the unboosting part, when we unboost, we have to make sure that the context that we're about to run is not important. So if we switch to sched other in the scheduler from RT, then from the scheduler, we issue a hypercall saying, we're about to switch into normal tasks, like please unboost us. And then we have other parts of the guest kernel, which we also, like for example, the interrupt exit path, we unboost there as well. If we are exiting into a context, like for example, if there's no software queues pending and the interrupt happened in a preempt enabled section, and there's no RT tasks that were interrupted, then we know that on the interrupt exit, we're about to run unimportant stuff, normal tasks. So we request an unboost there as well. We don't do boosting and unboosting on local IRQ disable and enable. That's still TBD. We don't know if that's required or not, so that we're still working on that part. So one of the things we were concerned about when we started looking at this stuff earlier this year is what's the hypercall overhead like? Like, can we make hypercalls often and get away with it? So we did some tests, and we see that on today's hardware, hypercalls are very, very fast, unless you have nested virtualization turned on. And the latencies that we're fighting are like tens or sometimes hundreds of milliseconds. And so a 10 microsecond or 20 microsecond overhead for hypercall is not a big deal. And like I said, we don't do the boosting as soon as we know that as soon as we start something important. Our POC does the boosting only when needed. So what we did is we hacked the VM exit path to detect that. So first of all, the guest sets its intent in the structure that is allocated, saying that I'm running something important now, or I just what the preemption state is. So if preemption is disabled, that's also stored in that structure, and that's all in memory. There's no boosting that has happened yet. And on the VM exit path, we check that state, and we realize, oh, we just VM exited while the VM was running something important. So we then do the boost at that time. So that avoids us doing boosting all the time, and we do the boosting only when needed. Did I get that right? Right. So that's the asynchronous thing. So we have to do proactive boosting as well in certain cases. So let me go over the two cases. One is when we inject interrupts into a guest. So say a vCPU is not running and the host took a guest interrupt. It now has to boost the vCPU before it can start running the interrupt. Because the interrupt is important. So we boost the VCP in advance. So that's proactive in the sense like the host proactively knows that the VM is about to run something important, and it does the boosting. Another case where we do this kind of proactive boosting is when the guest vCPU halts. So when it halts, we know that when the vCPU resumes, it's resuming because it's running like an interrupt handler or something like that, or an IPA handler. And so we know that that is important. So this is a very clever idea Vineet came up with, where let's just boost it when we go idle and we halt, because we know that it's not running anyway when it's idle. Let it stay boosted, and then we don't have to unboost it when we wake it up. Did I miss anything? Okay, so let me go over the interrupt handling part. Like I said, we have to proactively do boosting when the host injects interrupts into a guest. The two cases that this can happen is, one is if it's an emulated device interrupt, where the VMM has to handle the interrupt and then inject it into vCPU. Another case is with VFIO pass-through devices, where if the vCPU is sleeping and you received a VFIO pass-through interrupt, you have to now handle that in the host, and then you have to wake up the vCPU and have that handle it, right? So let me go over this timeline here.
Can I ask a question quickly at the back?
Yeah, go ahead.
So yeah, you're doing this by boosting the priority of the vCPUs. I'm wondering if you could achieve a similar thing, maybe more simply, by instead having more vCPUs. Basically having a set of vCPUs which are your low priority vCPUs and a set of vCPUs which are high priority. And you basically have a contract with the guest that says, if you've got real-time work, you schedule it on the high priority CPUs and we'll always prioritize those. And if you've got background work, put it on the other ones.
Yeah, that's a good point. We tried that and it doesn't work. And it requires the guest to be configured. Like with this stuff, we're calling this feature parabot scheduling. Like just drop the same kernel into the guest and it just works. It doesn't need to know that these CPUs are RT or these, it's fully like, it just works. The other problem
Surely
is
the guest needs to know, like, this is a high priority application. Like, it needs to be able to reason about its applications and its interrupts.
You have interrupts and stuff. What you have to then do is you have to take the interrupts, assign them to CPUs that are important. So there's some configuration to do that. The other problem with that is you can have a RT vCPU preempt a CFS vCPU, and CFS vCPU might be in the middle of a lock. And so now you kind of stepped on your own foot, because so in our design, what we do is if that CFS vCPU was holding a lock, it would already be boosted. So we would never run into this situation where they can step on each other. And so we've been trying this for a number of years, and we've tried that already. And this is the first time we're at a point where it works. So.
Since you're interrupting, I thought I'll continue the trend. So just from experience of trying to use hypercalls for our other needs for VM CPU freak and whatnot, the impression was the KVM community hated it. They're like, get away from hypercalls.
Community hated it?
KVM community. And in our case, it was easy. This is use MMIO.
right? Emulate a device, it works. But could you use kind of some kind of like shared memory to indicate this externally?
Yeah, we do use shared memory already. The thing is, during the unboost, we have to make that synchronous. So, but during boost, we do make it only shared memory.
Yeah. So boosting is like a fast boosting is like a fast path where you update the shared memory and let the vCPU run as long as it can run.
So you update a shared memory on the VM side, and the host side you read it.
Host side will not read it until the next.
Correct, correct.
Yeah,
Whenever it
exactly.
needs it. Okay. Maybe I don't know, send a useless interrupt or trigger a switch to host instead of hypercalls. Maybe where you make it look like a device. Anyway, you can. I'm sure. Anyway, you'll know it when you send it out. But that's the first.
Yeah, it's not pretty, but it works really well. And we presented this before, and there were KVM folks in the crowd, and nobody threw any tomatoes or anything.
That's good to know.
At us.
Cool.
Nobody was jumping in joy, but
Do you think there would be any security concerns for this? So if you have a malicious VM, it could just keep on asking for boost, and then the other VMs will get blocked.
that to some degree the VMs have to be trusted, but we do have protections where VM cannot just request a boost and not unboost. We implemented guardrails for that kind of stuff. We have timers that take away the boost if you don't unboost soon enough. Yeah. So yeah, there's definitely some concerns are in that area, but but we have to do something about this problem. So maybe people who have trusted, run their own kernels and guess they could benefit from this, so they turn it on, and the others like the cloud guys don't turn it on. That might be an option. That's why we made it fully configurable and tunable and all that. So now, okay. So let me go over interrupt handling. So this timeline, we have an interrupt that's injected into the vCPU, and what we realized is that we have to boost the vCPU thread as early as possible. We can't make the vCPU thread boost itself in the VM enter path, because it's a chicken and egg problem. Like the vCPU, when it's doing the VM enter, it's not running at high priority. So we have to boost it before we actually run the vCPU thread. So the VMM boosts the vCPU thread and wakes up the vCPU thread, and vCPU thread enters the guest mode and starts running the interrupt. Once we're in the guest, we do the interrupt. We're already boosted at that point, and then we in the interrupt exit path, we check the need resched flag, which tells us if there's something else that needs to run. And if that flag is not set, or we're exiting to CFS, then we synchronously do an unboost. And then we return, once we deboost, we go back to the VM. And posted interrupt handling is similar. Posted interrupts are basically the guest directly services the interrupt without the host ever knowing. So as I mentioned, we have to do something inside the guest on the interrupt entry path to make this work. So what we do is we set the shared memory with the request, but we don't do a hypercall like I mentioned. But while we were in the post interrupt handler, if we had a VM exit, then again in the VM exit we would boost. I should mention that if the vCPU was already boosted when the interrupt came, then we just directly go and execute the interrupt. But if it's not boosted, then we set the status that this is like we need to run as boosted if you ever VM exit in the future. And then once the interrupt handler finishes running, then it has to do a deboost. If there are no soft IRQ spending, because after the interrupt exits, you might run soft IRQ, and those soft IRQs also have to run at high priority. So in the interrupt exit path, we check that no soft IRQ spending, preemption is enabled when we're exiting, and there's no RT task that we interrupted. So if all those conditions are true, then we know that, okay, it's time to deboost now. Otherwise, we depend on the scheduler. If let's say an RT task was interrupted by a posted interrupt, then we don't deboost on the interrupt exit. We let the scheduler, when it switches from RT to CFS, at that point we do the deboost. So here's some info about the shared memory implementation. So basically we have 3 fields in the structure that the guest allocates. We have the boost request, we have the PM disabled field, and then we have whether the vCPU thread is actually boosted or not. So for example, if the vCPU was already boosted, then we don't request, we don't need to do anything, in different paths. Like for example, if it was never boosted, then we don't need to do the unboost hypercall. So it basically keeps track of whether the host has boosted us or not.
Yeah, so the boost status is set by the host and read by the guest, but the guest schedule info is set by the guest and read by the host. So that's why we have kept it separate.
Yeah, that's a good point. Okay, so I'll hand it back to Vineet to tell us why this stuff really matters, and we should totally upstream it.
Cool. So we have taken some performance numbers. We have some synthetic test, and we try to simulate some real world workload. For the synthetic test, we use cyclic test running as an RT task, both on the guest and the host. On the guest, we wanted to see if this feature improves the state, and on the host, we wanted to see if it doesn't regresses the current state. And we tested it on idle host and a busy host. Busy is being simulated by StressNG. And for cycle test, we used 100 microseconds and 1000 microseconds. Just randomly try to test how it looks like. And this was done on a very low-end device in Intel N4020 with 2 cores and no hyperthreads. And on simulating real-world workloads, we used an app called Obo Tester to see if, how the audio glitches looks like with and without this fix. So this is a lot to grasp in, but I'll try to explain. So we have cycle test running as RT sched RR, and on the on the left side you have the VM data. On the right side you have the host data. On the first row you have the average latency reported by cycle test. On the second row we have the max latency reported by the cyclic test. And we have 3 cases. One is the vanilla kernel. One is VCP boost is our feature, and static RT is the ideal case where you have VCPUs running always as RT. So you use CHRT to set the VCPU threads to RT. So this is on an idle host, and as you can see, the average latency inside the VM for vanilla, VCP boost, and static RT is comparable. And on the host also it's comparable. But on the max latency, it's not as good as RT because you don't always boost to RT, but it's much better than vanilla. And so this is an idle system, remember. So it should be as good as RT. What we suspect is migrations, because RT does very aggressive migration, and it might be the latency caused due to migration, but we are yet to do more investigation on that. But if you see the host side of things, static RT is really detrimental to the system. So VCP boost and vanilla performs more or less the same, but putting static RT, the VCPU takes over and the host, it hurts the host. Now let's move to the busy host. So StressNG is running on the host, cyclic test is running on the host and the guest. So the vanilla, again, on the average case, vCPU boost is as good as static RT on an average case. And on the host also, it's more or less the same. But when we come to the 99%, the maximum latency, it's on the VM side, it's in between vanilla and static RT. It's performing much better than vanilla, but not as good as RT because it's not always boosted. And if you see the host side of the things, the static RT is hurting performance. So VCP boost does a much better job for not hurting the host. Next is we try to simulate a real world workload using the Obo Tester app. What it does is try to count the audio glitches that happens while playing back audio. So we tested with multiple buffer sizes. So there is a 2 millisecond, 5 millisecond, and 10 millisecond. So what happens is there are multiple entities in the audio stack, starting from the app all the way to the device. So 2 millisecond means every entity gets woken up every 2 milliseconds, and it writes 96 frames to the next one in the stack. So here a wake up happens for all the entities. And as you can see on a no-loaded system, like it's an idle system, VCP boost performs better than vanilla. Similarly, for a busy system which is simulated by speedometer, it's performing much better. So this is like simulating a real world workload. And again, I apologize for a very shady, vague image, but this is the same video lag example that I showed initially with the fix applied. So you have, this is the vCPU that's running, and as it comes here, there is the surface flinger. I'm sure you will not be able to read it, but what runs is a surface flinger, and it's a RT priority. So it gets to run. It gets to preempt what is running on the host, and it gets to run through its completion. So, and while playing the video, there was minimal lag. It was a loaded system, and there was minimal lag. So real world also seems to improve things with this patch. Okay, now let's come back to the generic case. So this was a very specific case of boosting the priority to reduce latency. But this idea of cooperative scheduling can be extended. We have a lot of use cases that could benefit from this idea of cooperative scheduling, where the host can share information with the guest and the guest can share information with the host. So a couple of things that we have identified. One is the host can share the physical CPU load, pressure, placement, etc. And then based on this data, the guest can basically decide where to run what. Similarly, the guest can share its information with the host, and the host can decide where to place the vCPUs based on that.
One of the things I was thinking about for the first point was Vincent has been looking into how to take into account pressure from different sources in the scheduler. So I was thinking, like, if we could reuse that mechanism in the guest scheduler, if we were having if the host CPU that the vCPU was running on had like a lot of it was crowded and had a lot of tasks on it. If we had that information in the guest, we could do better placement decision. And we really have that problem. We're getting traces where people are like, that's a horrible vCPU to run anything on in this situation. Like, why did you select that? So because we don't know what's happening on the host. So
just a tiny
yeah.
Pinned?
No, we don't do pinning. We don't have enough.
So what does it mean, vCPU physical placement? Because a vCPU can just move off to some other physical place if it's not.
It could move out.
So the host can make a educated decision about where to move it. That's what we mean by vCPU placement. So if the guest says that this is my current workload, the host can make an educated decision about that. That's what.
Yeah, so this is just like we're thinking like in the future, what can we do? We're not done that, but in theory, since in CFS, we take into account pressure from different things, like if RT is running or IRQs, so why not also have a pressure signal for whether what's going on the host vCPU? Yeah. Go ahead.
For letting the host know about the workload inside the vCPU, wouldn't our talk about the vMCP freak kind of take care of it, because we update util? Or
kind of.
You try and update util there at least.
Yeah, I think
that
we
should take care of that.
We should coordinate on some kind of interface where
And
maybe we
then
can,
for the other direction, I was thinking, and David's been thinking about it too, is to emulate the host load as a thermal pressure. Right? It's not thermal, but we don't need to care
yeah,
about that.
that's
right?
fine with me. But
Emulate the thermal
where-
pressure or whatever.
Some kind of
thinks is the right
pressure.
pressure.
Sounds to me like you're somehow making the scheduler more and more. Almost sounds like you're making it transparent between the
Yeah,
guest and the host.
that's
kind
the
of-
problem,
And to
right?
me, like the only fair enough. I don't know much about VMs, so whatever. But it would make a lot more sense if you had like a pluggable scheduler where you had like, my thing is with the CFS scheduler, it's kind of a
That
very
sounds good.
generic.
Like that sounds good to say, and we talked about that as well. It's very hard to do because you have a VM boundary, so you have two schedulers, and it just we have looked into that, and it just doesn't make sense. But we could talk about it.
No, the only objection that I don't have an objection because I don't maintain anything in this area is that this is a very generic sort of scheduler, and it seems like a very special use case. How likely do you think this is going to be upstreamable?
I think our job is to show the data, show that we need this for our products, and do our best to upstream it, right? Yeah.
And we can do it like we'll not be integrating it to the mainline. Like what the idea is to use as a paravit ops, so it will be only used when a VM is in action.
Yep.
Like when the VM doesn't send any information to the host it's a no op on the host.
Yeah,
So yeah, so that way it'll be still a very generic scheduler, but it might it transform itself into a different scheduler when it needs to. That's the idea that I envision.
Yeah, and I just want to mention another use case is actually RCU. Paul just walked in at the right time. So basically, this is a real problem we are seeing where in Android we're not able to, we're having RCU problems because we're not able to leverage RCU priority boosting and the RCU-K threads that are set to RT, like for expedited RCU. Like those, like when the VM does all those things, the host has no idea that, and so we have RCU stalls and stuff that are happening inside the guest. And I'm looking at bug reports right now. So this stuff, I strongly believe that we could make use of it. Yeah, Paul.
Just coming back on this thermal pressure, you have to take care about, we're speaking probably about two different things. The thermal pressure, it's about performance capping, and what you have in mind, it's about cycle used by someone else outside your VM. And in different talk, I have seen a confusion between stealing some cycle or asking for cycle to run and at which performance level, which are two different metrics. The other point is that normally in the VM, in the CPU capacity, we are tracking the stolen cycle in the VM. So I don't know how this can be used and how this can be reflected to you about how much cycle, how much capacity is really available. But normally, just like IRQ can steal some cycle to the CFS, we are tracking the stolen time by other VM in the VM. So you should get get this feedback somewhere.
But so you're saying it's there right now?
We are tracking normally the capacity. We can report how much capacity is available for CFS after removing the RT thread, the IRQ, and the stolen time if you're in a VM.
Yes. Okay. So you're talking about the steal time stuff. Yeah. As far as I know, that's not implemented in all architectures, but yeah, but it's there. Okay. So we should look into that.
Yeah.
Maybe. But yeah, we were thinking that mechanism also could use this stuff, right?
Yeah.
Like
on the
another thing we have is the preempt if the vCPU is preempted. Yeah, go ahead, Paul.
So there was a earlier effort that was much more special case than this, but it was an academic effort and involved the RCU CPU stall warnings, where a vCPU preemption would happen in the middle of an RC read side critical section, and the thing would stall. And they did something similar where the where they had the RCU grace period mechanism hint to the hypervisor. I think you have a more general solution where you're relying on the fact that the priority boosting comes in and does it for you. But there's at least another proof of concept of that part of what you're doing in the past. If I don't send, there's Unix papers published on the problem statement. If I don't send that to you, bug me.
Yeah. Great. Do you know off the top, like what they were doing, like kind of?
It was specific to the power hypervisor. And so they had a situation where they just made the grace period K thread when it would have otherwise done the priority boosting, or in addition to the priority boosting would go and they made a new hypercall. And the hypercall said essentially, you know, get this guy going.
Okay.
This vCPU needs more time.
Okay.
And I don't know the details of what was in there. And if I did, I probably wouldn't be allowed to talk about them, but
Yeah, no worries.
that was more or less what happened.
Yeah. We started doing that and then we switched to the BMX.
The thing is that the priority boosting makes up that funny RT mutex and then acquires it, and it's got higher priority, and then pretends that the other guy already holds it.
Yeah.
And so,
but on the
because
host,
of that,
it
that
doesn't.
means what you're doing just works automatically.
Yeah, exactly. That's why
That's
I'm
the thing
so
on the side.
excited about this stuff because we
That's
get
why I
all
say we have
the-
proof of concept in the past. Now, the reason that didn't go anywhere was that on the IBM hardware, it was theoretical. We didn't see that problem happening. So as
Okay.
I said, it was an academic effort.
Okay. Sounds.
So from what I understand here is that you're using MSI to let the host get communication. And all the test is based on a good assumption here. But from a security perspective, like, yeah. So if there's an attacker or some guys keep fake some of the workload there, so it will keep the host to do like, you know that.
Yeah, so that's definitely a concern. So in one of the first slides we had that. So the host should have throttling and forceful unboosting mechanisms if it sees patterns that look like a rogue kernel or a buggy kernel.
Yeah.
So we have implemented it partially, but that should be there in place. Otherwise, yeah, you're right.
Yeah, but also like I just wanted to mention that in our, like, it depends on your system, like how much control you have over the guest. Like in our case, we provide the guest kernels and everything, so we would turn this on. But if we were running random VMs that we had no control over and that was using this feature, then we'd probably turn it off.
Okay.
So we can get away with it because we control the stack much more. That's how I look at it.
Yeah, I'm thinking like public cloud, probably
Yeah.
no. Yeah.
You probably
private
don't
cloud.
want to do this
Yeah.
Unless there's a better security model.
Yeah. Well, do you want to speak, Joey? Okay. I think you're probably going to say similar things. Here we go.
Okay. Have you tried boosting with nice value or latency nice?
Not yet.
Not yet, but we on a different scenario, like we were expecting, Joel was expecting this question. So on a different scenario, we found out that boosting to CFS might not always give you the result that you want. For example, CFS is not strictly priority aware. For example, if a vCPU is boosted using nice value, it gets a more runtime. But once it exhausts its runtime, and then an interrupt comes, there is no way that you could get it to run. So only a strictly priority-based scheduling will get you that. So it would work, and it would work for your use case. Based on your use case, you can either use it as a ZFS boosting or a RT boosting, and we are planning to make it a tunable.
Yeah. Whether you can turn it on and off, which VMs you want it on, what priorities to boost, what to unboost, we'll make all of that tunable. And that's how it should be, like a system design usage than anything.
Just coming back to the kind of security model in the public cloud aspect, I think that this definitely is interesting for cloud providers as well, because, you know, customer VMs at some point care about latency and at other points don't care about latency. And if we can improve that, that's great for our customers. So I think that whatever you end up doing here should have a clear path to making it secure, you know, where you've got a good idea about throttling and protection mechanisms and all that sort of thing, so that it can be used on a public cloud to give customers good latency.
low
Okay,
latency.
sounds good.
One other thing was maybe if you did the setting and boosting and unboosting, you're probably using skate set attribute to set it. As long as you're calling it from the context of the thread you're affecting, then existing mechanisms of preventing threads from boosting themselves to RT would apply. But I think some of the cases you're talking about, you don't necessarily call the set attribute in the context of the thread itself.
We call it in the context of the thread because it's VM in the VM exit, and the hypercall is
No, in the
also-
VM enter, you said they had a chicken and egg issue, right?
Yeah,
You
that's
might not
true.
be calling it from the context of the thread. As long as you call it from the context of the thread all the times, all the security issues are taken care of.
Like, how is it taken care of?
Because like you can set like, hey, like the sysadmin can set whether an app can boost itself to RT, right? Like not any app can set itself to RT, for example. There's a limit on what nice values you can change yourself to in the default system. Nothing to do with VM, right? Even in a normal context.
Okay.
Like for example, in Android, like any random app can't set itself to RT because it's limited.
Yeah, in this specific case, we don't go to userland to do the setting. So
No, you don't need to. That's what I didn't say go to userland, right? Set it in the context of the thread. It's fine.
okay, yeah, understood. Yeah.
Okay, thank you.
Okay.